It's working? Okay.
It's working? Yes. Okay.
Good morning, everyone. Please take your seat. Good morning. I hope you all had a bit of salty coffee and you're awake. It worked for me, anyway. Please take your seat, and then we start with the third day of this workshop. The third day of this workshop, we are thanking our hosts, Isa, for this excellent workshop so far. The third day of this workshop starts with a panel. All right, yes. So today we start with a panel on Copernicus uptake for agricultural policies. My name is Marijn van der Velde. I'm working at the Joint Research Center of the European Commission in Ispra, where I work in the D5 unit on food security. And we have this panel today, so as I said, on Copernicus uptake for agricultural policies, together with Uzue. Uzue?
Hello, good morning, everyone. Thank you very much for the organization of this workshop. As I told Marijn, it's a nice coincidence. Today in Spain, we would be celebrating the Saint Patron of agriculture. Just a fun fact. My name is Uxue Donezar. I come from Spain, and I work at the European Environment Agency. I am the project lead for Copernicus at the European Environment Agency, so leading the implementation of the Copernicus Land Monitoring Service and the Copernicus In Situ.
Thanks a lot, Uzue. So what we'll do, we'll briefly introduce the panel, and then we have two presentations, one by Uzue and one by me, after which we go in questions that we have communicated already to the panel, and we'll hope to have a bit of a discussion on the use of Copernicus products in the different policy areas, what the colleagues in Brussels and Luxembourg see still missing, and how this could be improved so that they can benefit from this for their different policy monitoring tasks. So I'm just going to state now the panelists. They are online, so all four of them are online, but we will see and hear them once we start with the questions. So we have with us from Eurostat, Carla Martins. She's from Eurostat E4 unit, where she's also leading their project on Earth observation for statistics. We have with us Bruno Combal. He's a policy officer at DG ENF in the unit that works on nature conservation, not conservation, but conservation, yeah, I always mix that up. And he is also guiding the EU Grassland Watch project. And we have Koen Mondelaars, who is Deputy Unit Head in A4 at Agri, working on data governance. And finally, of course, from DEFIS, we have Tim Lemmens working in the Earth Observation Unit at DEFIS. And the first thing we're going to do now is for Uzue to give a short presentation.
Okay, thank you very much. I'm going to give quite a short presentation, more an introduction to the Copernicus Land Monitoring Service products that are related to agriculture that we are producing at the European Environment Agency. So as I said, what is the service? For I guess that everyone knows here, but just a recap. The Land Monitoring Service is the Copernicus service which is giving geographical information on land cover and land use changes, vegetation status, water cycle, and energy surface variables. We are implementing the service together with the GRC, the GRC being responsible for the implementation at global level and we being responsible for the implementation at European level. We provide consistent and harmonized information across the area of interest, which in our case is EEA 39. And in short, our data, of course, as all in the Copernicus service, our data are free and open. You can access them in the link that is up in the presentation through our portal. And we have 6 main areas, or our products, the services that we are providing can be divided into 6 main areas. We first have the land cover and land use mapping, what we call priority area monitoring, which is land cover and land use specific to certain areas. Satellite data, because at the EA we are responsible for giving access to the very high resolution mosaic provided by ESA. At the GRC, they are responsible for the Sentinel-2 global mosaic. We also have biogeophysical parameters that are depicting vegetation and water status. We have the ground motion monitoring service, which is implemented only in Europe. And finally, we are also responsible for reference and validation data, such as EU Hydro. But in my presentation, I'm going to focus on the 2 groups of products that are related to the agriculture, namely the land cover and land use mapping and the biogeophysical parameters. For the biogeophysical parameters, there was a presentation yesterday on vegetation phenology. We have a product on high-resolution vegetation phenology and productivity. This gives, ever since starting in 2017, annual processing of phenology and productivity metrics together with near real-time vegetation indices. We are now working in the evolution of this product. We frame this in the continuous evolution of our products, in a continuous conversation with our users, and that's why we will include in the future, in the near future, when we start implementation of the new contract, tree cover disturbances. As a minimum, we would like to include the timeliness, the magnitude, and duration, and recovery of regeneration of the tree cover disturbances. And also, the goal would be in the future to be able to say if the cause of these disturbances is made by anthropogenic causes or biotic or abiotic. And we will also include biomass productivity on an annual basis. As for the land cover and land use mapping, we have grouped our production on what we call the high resolution layers, which were also named by my colleague from the GRC, Magdan. They have been grouped among the vegetated, non-vegetated, and then the water in our production. But this is, for you, the users, this separation is not that interesting. What is really interesting is that within what we call the vegetated land cover characteristics, we are giving continuity to the former high resolution layer forest and grassland, which were already being produced since 2012. And we have introduced the crop type, for the first time, crop type monitoring for the whole EEA 39. So for the high resolution forest, we have moved from 3 yearly to yearly updates. This entails, of course, a challenge when we talk about having consistent and harmonized time series, by the way. We will have status layers, tree cover density, and dominant leaf type every year, as I said, although change layers will still continue to be every 3 years. We have the crop type classification, yearly crop type classification. We are currently working on the production of the bulk time series from 2017 to 2021, and then from then onwards we will produce them on a yearly basis. We have a legend which is based on a previous Horizon Europe project named ECOLAS. But it's not only that, we are also mapping what we call the cropping pattern layers. And these include information not only about the duration, emergence, and harvest of the main crop, but also information on secondary crops, on the duration of bare soil, on fallow land, and cropping seasons. All these products related to crop types that are been currently, well, we have granted access to some of our colleagues, such as the people from the GRC. Also, they are currently being verified and will be published still in Q2, Q3 this year. And then we have the grassland. The grassland product was in the previous updates in 2012 and 2015. It was a product that we had a status layer, and we also had a plowing indicator based on a six-year moving window. We have moved from that way of producing to being able to give more, try to give more liberty to our users on deriving the information they need for their specific purposes. And that's why we have created now, we are publishing a layer which is called herbaceous layer, and we are also publishing information on mowing events. And in that way, we hope we will be able to, expert users will be able to derive grassland in different ways. One of the reasons why we have merged all the production related to vegetated in one single contract, and this is purely administrative, but it does have also a thematic sense, is to make sure that there is coherence between the different products that are depicting vegetation. And that's why you see in this slide the crop types and how how we treat the permanent or the non-permanent grasslands with respect to crop types. And finally, a product that is also included in this, it's a high-resolution small woody features. There was a presentation about the small woody features yesterday, actually. We are now starting, this is a product fully based on very high-resolution imagery, so 5 meters resolution in opposition to the previous ones, which are all at 10 meters. We are now starting the production for 2021, and we will soon, next year, start the one for 2024. It was produced for 2015 and 2018. It's also true that from 2015 to 2018, a lot of, part of the specification changed, and this was to be able to give a product which was more valuable for our users. We now have specifications that are quite consistent, that are quite robust, so we are going to keep them in the next updates. And we are trying also to see if there are options to operationally map other landscape features apart from woody features. I want to highlight the word operationally. We don't do research, and we only produce once we know a product can be done operationally for the whole area in a consistent way and with a similar accuracy for the whole area. And with this, I finish. I would encourage you to follow us on LinkedIn or on Twitter and to check our products in the Copernicus website. Thank you very much.
Great, thanks a lot, Uzua. Then it's my turn, if we can put up the next presentation. Great, okay, so we are at the Joint Research Center, European Commission, and I'm going to give you a little bit of a flavor of the type of work we do and our role, let's say, in this context. So more a role of R&D and thinking about future applications. And so this is several pieces of work from our colleagues. So you saw that Uzua was presenting the high-resolution layer on crop types. And if we want these layers to be used, we also want to know how good they are. So we need to have a proper benchmarking of these products, because then these Copernicus products can become the basis for higher value development. We can extract other information from them relevant for different policy contexts. So for this purpose, Martin Claverie and colleagues have actually created a single, easy, accessible database where we have been harmonizing all the publicly available GSA data sets. This now covers nearly 48 billion hectares for 2021, the countries and regions that are included have multiple years where this data is available. And the interesting thing is that following the work at the University of München by Maya Snyder and team, we have mapped this to the HCAT, the hierarchical crop taxonomy that they developed. So this means from every national GSA legend in the native language, translated and map it to a common standard. So that's why we can compare the HRL and the GSA data from those 3 countries that you see there in the picture. This is important not only to be able to do that task for the HRL crop types, but also at the European Commission, at Eurostat, we have other crop lists that are important for market production monitoring at Eurostat, AgriProd, we also have Lucas, and so also for those purposes we need to have an possibility to exchange this information all the way up from parcel level to either Earth observation products or reporting on crop statistics, also involving crop production. And so that's why I think this sort of work is important, and we of course also have high hopes for the high value data sets that should be created. They will have to tackle these sort of issues. It's maybe a boring task, but it's very important if we want to do something that is harmonized at the EU level. And in the end, we should all benefit from this higher value development. And we have an interest in this, and we have some expertise, because in our team, Raphaël Dandrimont, Astrid Verhegen, and colleagues have been actually doing this first European crop map, where we had the benefit of using Lucas Copernicus data. So this was a specific module covering 90,000 points in 2018, and using Sentinel-1 radar satellite to make this crop map that we published in 2021. This is important methodologically speaking. This is a sort of a one-shot exercise, but then we know what we can expect from these sort of products. And currently we've been doing the same for 2021, combining Sentinel-1, Sentinel-2, and also thermal layers and other biophysical properties in collaboration with Boco University in Vienna. There, the other advantage was that in the Lucas Copernicus module for 2022, we had now 150,000 points and also some information on permanent crops, fruit crops, for example. So with these sort of proof of concepts, we know what we can expect, and we also know what we can then develop from these sort of products. Very important, these are one-shot activities, so they're not comparable as easy as the HRL crop types will be. And that's of course an added advantage, which we will see here. Because once you've mapped your crops, that's of course very nice, but we're also looking for other uses. We are looking for ways to monitor how the agricultural policy is actually affecting the landscape and is affecting how crops are managed by farmers. And one of the obvious things that you can think of, that in 2014, in the CAP, the greening was introduced, and in this greening, crop diversification was one of the elements that was stimulated. So you had to diversify your crops in order to receive payments. So the first thing we did was using the crop map from 2018 and try to calculate in a coherent way across scales what that crop diversity was. So, okay, you can identify areas where there's a lot of monocropping, and you can identify areas where the crop mix is more diverse. But that's the picture looking from the top down. If you look at what is relevant for policies, you also have to think about the other way, because the policies affect, of course, the farmers themselves. The farmers operate at holding level or even parcel level. So there we made comparisons also to the farmers' declarations from the Netherlands, and we intend to do the same from the information that is collected in the so-called Farmer Structure Survey, collected in 2020 for all 9 million farmers, where we will have similar thinking, similar metrics that we develop then at holding level. And you want to confront these different viewpoints. They all have different purposes, in-season monitoring, accounting for how things have changed. But if you want to use the Earth observation, you need this annual product. So that's where the HRL crop types will come in, because then we can see how are things changing 2017, 18, 19, 20, etc. Very important, especially so if we do not have a European database on farmers' decorations easily available. And so this is the type of thing we are thinking about in the context of developing indicators, also within the performance monitoring and evaluation framework, for example. Finally, we're also looking, of course, at the grasslands. They are going to be very important, but we also have colleagues that are trying to think about how can we use the small woody features, or how can we combine this very high resolution-based layer with other information. And that's one thing that we're doing is using the small woody feature mask, combine that with Sentinel-2 observations, and basically evaluate the stability of the NDVI signal in the mask. And you can see that this actually works. It's sort of promising. You're dependent, of course, on the original quality of your mask. Your Sentinel-2 is coarser at 10 meters, but we can sort of detect where trees are lost within those small woody feature patches, as you see on the orthophotos there. And from there, we could do a sampling across different countries to try to see how much of these small woody features are actually lost. Numbers are very low, which is also exactly the problem that you want to detect something where the change rate is so low. But we believe that this is an important activity to continue, but we also know that in the outside academic world and in the commercial world, a lot of other activities are ongoing. The group of Martin Brand, for example, in Copenhagen, they've mapped all trees outside of forests. And so these are the type of developments that we have to keep track of so that we can, in the long run, also improve the Copernicus products that we develop. In the end, that will lead to better services and policy uptake for everyone. That's what I had to say. We have now the chance to move to our panelists. So we're going to talk about different topics. We're going to talk about DEFI's ambitions, engaging policy users for Copernicus uptake. We want to know a bit about the current use of Earth observation in the various policy areas. And we want to hear what sort of applications actually integrate Earth observation with other types of data for the different policies. And finally, maybe the million-dollar question, how can Earth observation help us to develop more coherent land-based policies? And with that, I would like the panelists to appear on the screen, if that can be arranged. And then I'm going to give the floor to Uzua. Okay.
Okay, can we have the panelists on the screen? Yeah, there they are. Thank you very much. So the first question, the opening question, is going to, I'm going to ask it to our officer in DEFIS to set up the scene. So we talk a lot about different policy users and stakeholders, and also about increasing the use and the uptake of Copernicus data and products. But I would like to know from, I would like our officer in DEFIS to give us some highlights on what are the ambitions of DEFIS in this context beyond the current multi-annual framework. So this is beyond 2028. So Tim Lemons, please, could you please introduce yourself and then answer the question?
Yes. Hello, can you hear me?
Yes, we can hear you, yeah.
Okay, good morning. Good morning, Frascati.
Tim, hold on. Have you switched on your camera?
Yes, I have.
Okay, hold on a second, because we need to make sure you appear on the screen. Just a second. Yes, excellent. All right.
Okay. So now you can hear and see me. Unfortunately, I could not be there. I would have wished to be among you in Frascati. But I'll do the speech from Belgium. So I'm working in DEFIS in the Earth Observation Unit. We have to underline that Copernicus is an operational program. So it's operational. It will remain like that. You will be able to keep on relying on the products and the data that Copernicus is providing. So also in the next multi-annual financial framework, DEFIS will continue to deliver Copernicus data and products, and this will still be on a full free and open basis in support of all of you, so support of the EU policies, member states, and also the research sector. At the same time, there is evolution needed, of course. So we have to keep up with new technology, with changing user needs. As Marijn already said, there is a lot going on. They also have to check what is going on in the scientific world. And parts of this evolution have already been initiated now, or are being initiated, but they will continue under the next one. And if I can mention a few of those, one of them is the user uptake. Copernicus is an operational, but it's also a user-driven program. Users are really the central part in our program. So they are actively participating in user needs assessments, consulted during product development, during research. And it's one of the assets of Copernicus, and we will even stress it more during the next MFF. So the current structures, we certainly want to keep them, to reinforce them. And one of the things I'm thinking of is the national collaboration programs, which are being rolled out in all services and which are a very important mechanism to have the connection with the end user. Technology-wise, the ambition of DEFIS is to continue with the initiatives that have been started, and as you know, we have many satellites under development. I think in this symposium you have had presentations on LSTM, on CHIME. There is the new generation series of Sentinels coming up. And if all goes according to plan, you know, we have now 6 satellites in orbits. Beyond 2028, we will have at least 12 satellites, if not more, in orbit. So this goes with an expansion in itself already.
Great, thanks a lot, Tim. So let's move to the first question to the panelists. So this is a bit about what is the current use of Earth observation and applications in your respective policy area. And so I'm going to give the floor to Koen Mondelaars, and I'd like him to tell us a little bit about, given the increasing operationalization of these Copernicus products, as we have just seen, and any of these applications that we can develop, what opportunities do you see, but maybe more importantly, where do you see still significant gaps that should help for policy uptake? Please, Koen, the floor is yours.
Yes, thanks for the questions and good morning to everybody. Koen Mondelaars from DG Agri. So thanks for the opportunity. So in Agri, we are of course dealing with the land-based activity. So we really welcome the Earth observation data. We've been using it for many years, and of course we are a major client. Lastly, in Brussels, we saw, but also across Europe, we saw a lot of protests from farmers about let's say, the policy not being, let's say, sufficiently adapted to what's happening on the ground, and also a lot of reporting burden. And especially here, we see that Earth observation can also play a role in the future, how, let's say, to tackle both elements at the same time. So it can definitely help us to come up with, let's say, more result-driven and more evidence-based policy making. So we have a very established collaboration with many of the institutions around here. What for the moment in the CAP, one of the major uses of Earth observation data is, let's say, our area monitoring system, and it's in fact part of our integrated administration and control system. So member states are obliged to implement this area monitoring system so that let's say we can monitor the claims that are made by farmers for area-based payments. And for that, of course, the Copernicus Sentinel data are crucial. And many initiatives have been taken over the years to ensure a good implementation of this area monitoring system. I just named, for example, the project Send for CAP or the NIVA project. But our main concern, in fact, relates to what Tim just explained. For us to remain operational, it's really important that we can keep the flow of data. We understand that now with Sentinel-1 there are some issues, and also for Sentinel-2, let's say there are currently only 2 satellites. So for us, it's really important that we ensure this continuity of the data provision, and we welcome all initiatives to further enrich this. So that's a really important point for us. And then we have under our CAP, Common Agricultural Policy, we also have other, let's say, areas where Earth observation data are important. One example is the Farm Sustainability Tool. It's a tool that member states need to offer to the farmers, and that farmers can use to optimize their nutrient balances on the farm. And this tool can also be fed with information from Earth observation. So advances, let's say, how to integrate the Earth observation data in such a tool is of course something, an area where we can further progress. In our CAP, let's say it's a performance-based policy with result indicators, and we see for the moment, to a limited extent that the Earth observation data is really used in those results and impact indicators. So that is an area where we really want to further improve, and we need to cooperate together. How we can ensure that from, let's say, the raw data up to, let's say, the kind of tests, Marijn, you just showed, we can really come to stabilized indicators that allow us to monitor year after year at a granular level how, let's say, the policy is implemented and how it is impacting and changing practices on the ground. So that would really be a call to come to, let's say, to square the circle and ensure that we have, let's say, end products which are trustworthy. Just to give an example, grassland or the landscape features, those are areas where we, let's say, we are really looking forward to let's say, make better use of the Earth observation data and all the advances you make now. We are, let's say, also thinking about how the Earth observation data can, let's say, complement and even replace some of the more costly data collections. Think about Lucas, which is a costly data collection. If Earth observation can take over part of let's say, the required data collection, we have 2 gains at the same time.
Thank you, Koen. Let's move. Thanks for this first intervention. I would like to give the floor to Bruno Combal from ENF and give his thoughts on this first topic. We'll have time to discuss a bit more later on. Please, Bruno, the floor is yours.
Okay, thank you, Marijn, and good morning from Brussels. So I'm working in DG Environment in the unit dealing with the Birds and Habitats Directive and the network of protected sites, Natura 2000. Our legislation, so the Birds and Habitats Directive, have many hooks requiring geospatial information. And basically, we need to bring support to the member states in their effort to designate protected sites. Where are the habitats to protect? We also are much interested in monitoring potential degradation in those sites. And for us, the word degradation is not only about the destruction of habitats, but also in the degradation of their value in terms of biodiversity. So this is quite a complex exercise, and Earth observation alone cannot address this question. So we are already here in entering the question of connecting Earth observation with other source of data. And there is a last third important provision under the Habitats Directive, which is about the obligation for the member states to report on the conservation status, the health, if you wish, of the species and habitats. And this exercise for the member state is very costly and actually is mostly done by in-situ visits up to now. And the meta-information which are attached to those reporting efforts show that there are large uncertainties on the in-situ visits and a lot of unknowns for many habitats. So all those aspects shows us that Earth observation might be an excellent complement to these efforts because we have a wall-to-wall capacity to observe. The costs are certainly much more affordable than in-situ visits, but it's very likely that the details do not compete with in-situ information. This said, we have been working now in my unit in developing what we call last mile applications. The idea is that the users, so either the policy officer in the environment who are checking the compliance or who are checking the designation of sites, or the national experts in the member states would appreciate to get information derived from Earth observation. But those persons are not Earth observation specialists, so they cannot just go to the CLMS portfolio and extract data and process it. If we really want to provide a service, we need application that will reprocess this information and this data, and present it as information that will quite directly help the people in charge to address the different questions I was talking about: site designation, compliance, and reporting. So we have started to work in this direction with the first project called EU Grassland Watch. The idea was to monitor grasslands. I'm talking about natural and semi-natural grassland. I'm not talking about production grassland. I say that because I have a lot of colleagues from agriculture in the room. So we have been working on this type of application, trying to go beyond what is currently in CLMS in terms of time coverage. The point is the Habitats Directive is from 1992. We have an obligation to try to monitor any degradation since the designation of sites. And as you know, when we talk about natural grasslands, the intra-annual variability is something extremely important. Of course, natural grasslands might change in terms of quality due to natural events. I'm thinking meteorology, weather, etc., but also under human activities, either the pressure, for example, intensification or abandonment of grassland. That's something we see a lot, or the effort of restoration too, which is something that we eagerly want to see happening. Okay. What I'm trying to say is that the timeliness of the products is certainly an aspect that we still need to work on in the Copernicus activities. We have seen a lot of progress in the last decades in terms of resolution, spectral properties. Now we have access to radar, optical data, etc., in a very direct way, level 3, which is absolutely excellent. But the timeliness is still a problem.
Bruno, I'm sorry, yeah. I'm afraid I need to cut you down here. I'm really sorry that this has happened. Thank you very much for your input. I would like to now give the floor to Carla Martins from ESTAT on a second question, which is actually pretty much related to what you were saying, because we are going to talk about data integration, which was what you were actually talking about. So by integrating data from diverse sources, land-based policy making could be improved in different phases of the policy cycle. At the same time, and this was also mentioned by the ESA representative in a panel discussion yesterday, there is a mismatch between Earth observation people and policymakers, where we sometimes see that we don't seem to be speaking the same language. Carla, and first, if you could also introduce yourself, what are the challenges you face in this integration process, and what improvements would you like to see in the Earth observation data services to better serve your needs? You are muted, Carla. We cannot hear you, I'm afraid. No.
Hello?
Yes, we can hear you now. Perfect.
Okay, sorry about that. Good morning, everyone from Luxembourg. My name is Carla Martins, and I work at Eurostat. I'm the lead for the Earth observation for new statistics. And basically, we are implementing the Warsaw Memorandum on Earth observation, which aims at the uptake of Earth observation data for the production of official statistics. And we have already some projects ongoing for working basically on agriculture statistics. We have a project on grassland, a project on crop type, and a project on wind turbines, all related with agriculture statistics. And on the topic of data integration, I would say that there is a big challenge ahead of us. What Mahain just presented on the LPIS or the GSA data that is being compiled and I think in a very big work that is being done by JRC, that it would be great to have access to all this data on a yearly basis. I mean, that would be a dream to have all the data on LPIS and even on the 8 applications. If we could have that and cross that with the Earth observation data, that would be just perfect. And for that, there are, I think, maybe 3 great challenges. First of all, the anonymization of the data. So we have to make sure that data protection and confidentiality is secured. The other would be the harmonization. So having standard nomenclature, the ontologies, making sure that when we're talking about one classification, everyone is talking about the same thing. Here I think we are making some progress. Recently, we have the corporate reference data management of the crop classification that is being launched by DG Agri that Eurostat is co-chairing, which is promising to have, in the end, a common classification for crops. And this is the type of thing that we have to work on, the harmonization of standards. And then the third would be what has already been talked about by Bruno, was to keep the flow of the data, to make sure that the data we have next year will match the data we have last year. And making sure that there's a sustainable time series of compatible products that we can use for reporting. That would be my answer.
Thank you very much, Carla. Marijn?
No, thanks a lot, Carla, and thanks also to the other panelists. I mean, time is going very quickly. We will soon have to end this session, and my apologies for this also to the panelists. I mean, much appreciated you are with us online. We have one moment to think a little bit, maybe with some short replies. We can start with Tim about policy coherence. I think that Earth observation as a tool, as something that is coherent across time and space, is the ideal thing to use to have maybe common design of indicators or what we want to do with our land and how we want to track it. How does DEFIS see this? Do you see a process or a mechanism that could be designed where in common together with different policy DGs, indicators could be designed that derive from Earth observation? But short replies, please. Thank you. Tim.
Okay, short reply. We would love to give you policy-ready information. all DGs, but of course that's not an easy. It's easily said, but not easily done. So we are very well placed in the middle of the Commission to listen to all other DGs' needs. But unfortunately, we still don't have a satellite sensor that observes the needs. So really have to go and talk. And we invite the other DGs also to go and talk about their needs, their legislative initiatives, and to see where we can help and assist them. Maybe one thing I want to add, because the reply has to be short, is that we have set up an initiative together with the JRC, which is called the Knowledge Center on Earth Observation. And they're really specialized in gathering needs and analyzing them and see how Earth observation and how Copernicus can support that. So this KCO, I guess there are even people in the audience from them, they focus on a certain topic and they see what the needs are. One of the most recent deep dives, as they call it, was a deep dive on biodiversity. And this is one of the tools that we are now using to see how we can further support the biodiversity policies.
Great. Okay, then I would like to ask maybe Koen, your reflection on this last part.
Yes, I'll keep it short. So I think for DG Agri, the solution to all this is cooperation across the different institutions. And let's say we need to overcome the hurdles of interoperability. We have many data, we're sitting on interesting data, but the problem is how to combine them. And let's say how to have a common base also across different institutions. So for that, let's say we need to overcome the hurdles of interoperability, not only, let's say, the ontology or the semantics, but also legally. Can we share data? We have issues around confidentiality and so on, so which we need to respect, of course, but also from a governance perspective, how do we organize all this? What we do from Agri side is invest in projects. For example, Carla just mentioned the interesting part of LPIS and so on. So we have an initiative together with the GRC, and colleagues from DGM also follow the Spatial Agricultural Information System, setting up a huge database where we couple Ajax data together with the data from Earth observation and from Lucas, and around several case studies, and that could be something which we can scale up further and where we join forces all together. So that would be really the call to invest in this kind of collaborations across institutions, and of course for DEFIS a major role to play as a coordinator in the Commission. So maybe I stop there. And we need resources to do all that.
Great, a great intervention. Thank Koen. I want to give also the word to Bruno first, and then Carla.
Okay, so 3 brief points. So to ensure consistency, our approach was to develop a last mile application, putting around the development of the application all the stakeholders, member state experts, DG Environment, GRC, and CLMS, the EA. And we thought it was a very convenient way to let all the parties contribute to developing the tool they need on top of Earth observation. That's one approach. Another point is, I think that we really liked the deep dive proposed by the Knowledge Center of Earth Observation. That's something new, and we learned a lot. And it's helping us currently to develop equivalent to grassland monitoring, but for wetlands. It's invaluable support because us in DG Environment, we cannot do research. It's impossible. So we absolutely need that. And I would encourage to continue providing this type of effort to support us, but also it's a way for the KCEO to collect information from all the policy sectors and to have a broad view of the problems, but also on the overlaps that we are not aware of sometimes. And the last point, which is a bit technical, I would advocate for developing maybe what I would call a geospatial natural habitat register to identify our habitats and be able to share about across all the nature conservation project the same objects and be able to assess, attribute information to the same object and exchange in between policy files information, which is still something a bit difficult, practically speaking. And I stop here.
Great. Thanks a lot, Bruno, and well understood of this geospatial habitat registration. Carla, if you have some final thoughts.
Just some last thoughts on, I agree with Cohen, what he said on interoperability and sharing and cooperating. Very interesting project on the information system on agriculture. I will look that up with you. What I think from Eurostat's point of view is that the Earth observation products from Copernicus need to be clear, need to have clarity. They need to be credible. They need to have good quality in situ data. They need to be transparent. And from the statistical point of view, we need to have good metadata on the data and to prove that it's accurate so we can use it as official statistics. And for that, we can make it understandable for the policymakers. And so I just underline what Cohen said from DG Agri on the interoperability and making sure that all the data is used in the same way and that can be reused maybe in some cases. And I would just like to thank you for the invitation for being here, and I pass on the word to the hosts.
Yeah, thanks a lot, Carla, also for your final thoughts. I want to thank the panelists for being with us this early. And I think that the common thing that we've seen, there is a big need for this continued integration. But with all of you also being here online, I think there's also a willingness to do this. And this is important because we need to put energy in this further integration, as is always the case. But that should help us then to increase the Copernicus uptake for agricultural, but also environmental policies. So thanks a lot for your attention and your participation also online to the panelists. And have a good day. Bye-bye.
Have a good day. Thank you. Bye-bye.
Have a good day. Bye-bye.
Good morning. Yeah. Okay. Yeah, you can give.
Hello. Good morning, everyone. Welcome to this session on yield forecasting. We have talked already about yield forecasting the first day with a keynote presentation on yield forecasting at the subnational level. Today, in this session, we will delve more on a finer granularity, and we will see examples of use of Sentinel-1 and Sentinel-2 for estimating crop yield at the parcel or field scale.
Okay. Yeah. Also, I ask please the audience to come here closer to us, because people when it's arriving is going just to the back seats, and it's better for participation and also to allow people that come later. So please move closer.
Good. Do we have, we can start right away. Do we have our first speaker, Javier Tarin-Mestre? Thank you. Javier will talk about using Sentinel-1 and 2 for estimating yield in the Nile River Delta.
Hello.
Keep the timing in 10 minutes, please.
You want me to come?
Hello everyone, good morning. My name is Javier Tarín. I am a PhD student from the Universitat de Valencia, and I'm here to show you my most recent advances on the EU-Africa project. But let's start with a little bit of context. Climate change, as all we know, means increasing temperatures, which has a especially negative effect in Africa, in African agriculture. And add this to the fact that the population growth rate is increasing in these areas, and there you have the need to develop variables that help these farmers. So the objective of the EU-Africa project is the sustainable adoption of the Earth observation techniques and technology in Africa. And our contribution in this project is to apply the models that we developed for Spain in the Garbia Governorate, region of Egypt in the Nile Delta. And Egypt is the fourth most populated country in the world, and the 60% of the people that lives here depends on agricultural sector. And our main challenges in this project were the small average size of the fields and the poor quality reference data that we had. Okay, so let's move to materials. As I said, we are working on Garbia Governorate. We had more than 400 points with reference yield, reference crop type. But this is not all our data set because of the bad labeling and other matters that I will explain later. So after filtering, we had an amount of more than 100 for rice and 74 for wheat. Another problem of this data set is the low yield variability that we have. As you can see on the histograms, we have like 6 possible values to yield for wheat and rice. Our remote sensing sources are Sentinel-1 for synthetic aperture radar data, and Sentinel-2 for reflectance and its cloudless product, and ERA5 land for the daily average temperature. And here you have our full workflow for Sentinel-2 processing. But before processing Sentinel-2, we needed to digitalize all the parcels that our collaborator in Africa gave us. So this was a tough thing, and it was a tough thing to interpret all these points. And the main point of this workflow is the filtering, as you can see at the middle plot. When you plot all the parcels that our collaborator gave us, you can see that there's noise from close, there's signal from other crop types, there's even bare soil signal. So you have to filter all these signals, and you end with the plot we see at the right. On the right, in which all plots, all parcels follow the same trend, the trend of the wheat crop type. And this is the key of our work, the thermal normalization we performed. When we were developing the models for Spain, we saw that the different parcels had a temporal shift due to different phenology states or its location. So to correct this temporal shift, we had to use the GDD, which means growing degree days. So we take the temperature of the day and we accumulate it, and then we use it instead of the day of the year. So with this procedure, the plots get more normalized, and this improves the model accuracy and transferability. But for accumulating temperatures, you need a starting point. In our case, it's the start of season. I took it from my colleagues, Kate work. She explained it yesterday. And finally, the Sentinel-1 workflow. We just follow the Snap toolbox. And here we have the models that we developed in Spain. The RISE model is one that we developed in Valencia. We train it in Valencia. And it uses 3 bands of Sentinel-2, band 2, band 3, band 6. And for width, we have 2 models, one only for Sentinel-2, which uses 2 bands, band 3 and band 5, and another for the Fusion, which uses band 7 from Sentinel-2, and the ratio between BH and BB from Sentinel-1. These models were developed in Valladolid. And the 3 models depends on the GDD method. And finally, we have the crop type mask. We need crop type masks to perform a governorate study. So I took it from my colleague's work. The production of these masks is on his poster that you can see later on. So, OK, finally, results. Here we have the application of the width models to the reference data that we had in Africa after filtering. So on the left, you can see the Sentinel-2 model. It has a slightly better R² than the Fusion and a slightly better RMSE. But if you see the Fusion, it has a 1 slope, which means that this model does not overestimate or underestimate. RISE model. With this model, we saw that it's less transferable to Africa than the width models. So we had a big bias and a lower R². After correcting this bias, we get an RMSE about less than 300 kilograms per hectare. And OK, applying this to the governorate level, which is the main point of this work, the yield estimation at governorate level, we see that on the scatter plots, the 3 models overestimate, and they have a higher RMSE errors because of this. Going to RISE, it has lower R², but if we correct the bias, it has a high accuracy. It can be due to the low variability that we have in the reference data. The maximum reference data from RISE and the lowest value are less than 200 kilograms per hectare. And then with width, we can see that both models overestimate, okay? But the Fusion has more linear behavior and the highest R² of 3 models with 0.74. OK, so to sum up, the GDD allows us to transfer the models that we developed from Spain to Egypt. And going to that models, RISE model at parcel level tends to underestimate, but this means that RISE is less transferable. Then going to governorate level, it has a good agreement if we correct the bias. This bias is due to the low variability that we have in the reference data. So we will keep analyzing upcoming years, waiting for higher reference value. And going to width models, at parcel level, Sentinel-2, only Sentinel-2 showed slightly better results than the Fusion, but the Fusion showed a more linear behavior. So this made that in governorate level, the Fusion shown a better correlation than the only Sentinel-2 model, but both have a systematic overestimation. This can be due to the lack of low-yield reference data. And it would be fine to have more reference data, not only for the models, but for the masks too, because these yields depend on the masks. And finally, 2 recommendations that we have if you want to work with especially Egypt data. You need quality data, And you must know that data curation is so time-consuming. And Sentinel-2 maybe is in the limit for the small holdings that are typical in Egypt. Thank you, everyone.
I think we can get a few questions. We're really in time, thank you. Is there any question from the audience?
It's one there.
Thank you very much for the presentation, very interesting. I was wondering, what are the next steps that you are planning in order to increase the accuracy essentially? Do you have a strategy in mind? Thank you.
Thank you for your question. The next steps that we are considering is to apply the fusion of Sentinel-1 and Sentinel-2 to RISE. And to improve accuracy, we keep searching for more data, with good quality data. And that's all. We need more reference.
Okay, thank you very much. So maybe we can step to the next presentation. So, okay, our next presenter is Piet-Emmanuel Buecki. He will be presenting combining Sentinel-1 and 2 data with machine learning to improve field-scale crop yield forecasting. Thank you.
Thank you very much for the introduction, and thanks to everyone for being here. I will give you a short introduction about our project that is called GEOGLAM, which is about yield prediction and estimation using Earth observation data on a field scale and on a regional scale. The results I'm going to show here are focusing on the field scale using Sentinel-1 and 2 data. So I think most of the people here are well aware why we need these regional and field scale crop yield forecasts, but just to repeat it one more time, on a regional scale we needed to detect regions with potential crop yield losses so that decision makers have time to act and insurers know where potential damages occur. On a field scale, we can in an ideal case use them for precision agriculture, so to reduce the crop yield losses. And for both of these tasks, Earth observation are a key tool, of course, or provide key data for it, as it provides near real-time global data, which provides information about the crop yields and about the crop condition and the soil conditions. And machine learning is a valuable tool to combine all these data to provide then crop yield forecasts. But as you're all aware of this, I would rather focus on how accurate we can do these crop yield forecasts on a field level and how long before the harvest we can do so. So as always, the first step was to collect the in situ data. We have already had this many times in this workshop that this is the key part that we have to do to get use of the Earth observation data in the end. So we collected field-scale crop yield data that you can see for all the regions where we have a circle, and we have regional scale data for the countries with the shaded background. Our main crops are maize, spring barley, and winter wheat, and we have it mainly for Czech Republic. We have most data in Spain, but this is not highlighted yet on the bar plot where we have even a few thousand more observations from Spain. For the predictors we've been using, of course, we've been focusing on Sentinel-1 and Sentinel-2 data, as they are providing complementary data. From Sentinel-1 backscatter data, we have a good estimation of soil moisture in the end, or I can use it for that. And Sentinel-2 data, we use the individual bands to derive different indices that provide us with information about the crop conditions and the state of the crops. And we extracted it for all fields that we had available crop yields, of course. So the setup of the model then looked something like this, where we calculate the crop yield forecasts for maize, winter wheat, and spring barley, and we started the first crop yield forecasts 4 months before the harvesting season. and used different models to do so, so extreme gradient boosting and random forest first of all, but compared it as well to a crop yield model called Hermes, and we're planning to use as well, of course, some deep learning algorithms further down the road. The results I'm going to show here are all for maize and winter wheat and are the monthly updates. So I have one lead time for 4 months, and then the next update is 3 months before the harvest. These are some of the results that we have for maize. So on the x-axis, you can see the lead time from 1 to 4 months, and on the y-axis, the performance. In this case, we are looking at the explained variance. So in the ideal case, it would be 1. If we have a model that is predicting more or less the same performance as a dummy predictor, it has 0, and everything below is even worse than this. What we can see here is, of course, that we have 3 months before the harvest already quite a good performance of around 0.5, and then it's further increasing when it comes towards harvest. So on the different power plots, you can see the blue one is when we use the model only with Sentinel-1 data, the orange one is Sentinel-2, using only Sentinel-2 data, and the green is using both Sentinel-1 and 2 data. And we can see that using both satellites always provides the best results here. In addition, we can also see that Sentinel-1 data is a bit better for the long-term forecast for 3 and 4 months before the harvest, while Sentinel-2 is outperforming Sentinel-1 for the lead time 1 and 2. I think this is quite intuitive, because when we look at Sentinel-2 data, we see the state of the crops, and 4 months before the harvest, they're just not evolved enough to really see a difference in the Sentinel-2 data. Whereas in Sentinel-1, we see the crop conditions, as for example with surface soil moisture, which is already a key impact, or which has a key impact on the crop yields in the end. So this is why Sentinel-1 is a bit better for the long term, I would say. When we look at common winter wheat, we can see similar tendencies. So starting from 3 months before the harvest, we get more or less accurate forecasts. And still here as well, we can see that Sentinel-1 is a bit better for the long term, while Sentinel-2 is getting better afterwards. But I would say the results here, they are based on a random cross-validation for 30 runs. So I would say this is, of course, a good tool to get some first information how well our model is performing, but it is not in the end what we want to show. Because if we want to have our model in use it really for an application, we want to know how well we are able to predict the crop yields in a year where we don't have data. So for example, now we would like to forecast the year 2024, where the crop yields are not yet harvested, and so of course we don't have the crop yield data neither. So to simulate this for the validation, we did a leave 1 year out cross-validation as well. And when we look at this, we see that the results are getting significantly worse. So here on these plots, you can see the performance of the crop yield models for the combined Sentinel-1 and 2 forecasts for the 3 crops. So if we focus again on corn and winter wheat, are the bars on the right. And on the x-axis, we now have the years which the model is tested on. So for the training, we left this year out and only tested it on all the fields of this year. And you can see that the performance is generally below 0.2 or 0.3 a bit later in the season, which is definitely not a performance that we can work on for now. So we were, of course, interested why this is the case. And for this, we were looking at the crop yield data itself. So here on this plot, you can see the distribution of the crop yields for the 3 main crops again for the different years. And what we can clearly see, if you look at the example on maize, so the orange bars, is that we have significant differences between the years, but the variance within the years, so between the different fields, is quite low. I think this is as well quite intuitive again, because this was the data from only one farm, about 100 or 200 fields of one farm, so they have a high spatial autocorrelation. So if we have good conditions in 1 year, of course, we have high yields everywhere, and vice versa. But this makes it, of course, problematic for the model to correctly predict how large the crop yields really are. So if there is on one field a bit a higher crop yield than on the other, or vice versa, this is very hard to predict because they're just very similar from each other. This is one point. And the other point that we can do a bit more about is that we can see that between the different years, the values are quite different. So if we train now a maze model, without the year 2017, we can see that we don't really have this value range covered in the model. So if you look at 2018 to 2022, we have one other year with low crop yields and all the other ones have much higher crop yields, which is of course for a machine learning model not that useful or not enough data to really predict something in between that then. So with this I already come to the conclusion and some points how we could get rid of this or further improve the model. So the first point is that it is hardly possible to differentiate between different fields from a similar farm because they're just very close from each other, but this is in the end where we want to get. If we want to provide some irrigation or fertilization advisory, we need to know where the crop yield are a bit lower than on the other fields. And for this, the good point is that it will improve just with waiting for us from a modeling side, because with the longer data availability of Sentinel-1 and 2 data, the machine learning model will be used to a larger difference of crop yields, and with this it will definitely get better. So we just need to collect, we still need to collect the crop yield data, of course, but I'm very optimistic that in the upcoming years we can improve this just by the longer availability of the data. And in addition, of course, we already get as well other data sets like for land surface temperature and evapotranspiration, which will help a lot to differentiate between the different fields as well. So with the upcoming LSTM missions and with the increasing availability of eco-stress data, this is as well a point that can help a lot for this. Still, one positive point to finish with the conclusions is that definitely Sentinel-1 and 2 data provide an ideal basis for the crop yield forecasting, as they provide really complementary information about the crop yield, about the crop conditions, and the conditions of the soils. And with this, I would like to come to the recommendations. I think most of the points are already covered or have been discussed before, so I will leave them out. So we will get more precise high-resolution land surface temperature data and more regular optical data with the upcoming LSTM and Sentinel-2 data satellites. Crop yield data for sure is a clear limiting factor, but it is on the table and we will further discuss it, how we can exchange the in-situ data and make it more efficient. So I would like to focus on this point about the data distribution, because I think we still can do progress there. As for example, for eco-stress, I'm using the eco-stress hub, for Sentinel-1 data, Sentinel hub, and for Sentinel-2 data, the planetary computer. And I think from a modeling perspective, it will really help to just have one location where we can get all these data from. And as a last point, I think common validation strategies will be required to really make the results more comparable, because as I have shown, depending on what validation strategy we're using, the results look very different. So if we want to compare our results to each other, we need to have similar strategies to do so. And with this, I would like to thank you for your attention, and I'm open for questions either now, maybe, or else in the coffee break later on. Thank you.
Okay, thank you very much. I think we have time for one question. Yeah.
Thank you for your very interesting presentation. I have one question about the first cross-validation results you showed. Do I understand it correctly that you used in situ measurements from the current year, but just not remote sensing products, let's say 3 months before the harvest?
Yes, so thank you for the question. Yeah, so for lead time of 4 months, we just use the Earth observation data that is available until 4 months before the harvest. And then it's updated every few months or every month with the new data that is available by then. But for the cross-validation, we just randomly choose of all the fields and years we have available, we just retained 20% of all these data for the validation, and the rest was used for the training. Thank you.
Just a comment, so perhaps if you observe also interannual variability, meteorological data could really help in positioning the current forecast in the live 1 year out settings. So using meteor as well would be probably helpful.
So if meteorological data will help. Yeah, I definitely think so. So similar to the setup as was discussed before, I think ERA 5 Land will have a valuable contribution for this. We have been testing it very briefly in this project. Yeah, but there is the problem a bit that the fields are so close from each other that we basically have one point for all the fields. But still, for the interannual variability, it provides good information. But yeah, we don't have done the full validation of it yet. But I'm optimistic that it will help as well to further improve the results.
So one final comment. So you mentioned that you focus the study in 2 different areas in Czech Republic and Spain. How do you deal with the model? I mean, you integrate all the data sets all together and you calibrate the whole model like in both regions at the same time using 1 year out? No.
No, so the results I've shown here are just for the Czech Republic, so this is just one farm there.
Okay.
And we set up a different model then for the Spain data set, because I think the conditions are quite different. We tested it as well, how well we can transfer the results, so by training it with Czech data and then applying on Ukraine data or Netherlands data, but this did not work out that well, so I think we still need to train it per region individually.
Okay, thank you.
Thank you.
Thank you. Yeah. So we move on with the presentation of Belen on, again, yield estimation using Sentinel-1 and 2 data.
Okay, thank you very much. Okay, so I'm going to start my presentation talking about the global scale. So we know that yield estimations, forecastings at global scale are critical, especially to mitigate price volatility. In that sense, within the NASA Harvest program, we developed ARIA. ARIA is a model trained or like empirical model using MODIS data at core resolution and applied at national and subnational scale with errors around 10%, 2.5 months before harvest. So that is like our work until now. We are continuously improving ARIA. We successfully applied it to forecast yields in Ukraine, and Imbal later will talk about it in her presentation. But in this work, like we wanted to move from the global scale to the field scale level with the purposes of understanding better how things work at the field scale. So with those models at field scale, we can go back to the global picture and have a better estimations. So for that, we have different challenges. It's extremely challenging, and we mentioned it several times during the conference, of having accurate and reliable yield estimations at field scale. Also, there's a huge diversity and crop management across the different regions and areas of the world. And our question mainly is, can we train a model in a limited area with very accurate measurements and expand it or transfer it to a different area where the data quality is not so good or it's harder to get? So for that, we have data in Valladolid. It's very accurate data from 2018 to 2022 seasons. A farmer weighted the production after the harvest, so it's very accurate. And then we tried to evaluate it over different regions in Spain. We had contact with a private company that provided us this data, and we tested it over a given season in 2022. For that, we have as materials Sentinel-2 data and Sentinel-1. We explored SLC products, not just focusing on GRD. And we managed all the data sets. Imagine that in Spain we had to download 14 different tiles, so it was time consuming. And also we downloaded air temperature from Agra 5 to account for the thermal normalization. So on that, I'm going to skip directly to the method section. Javier already talked about the GDD normalization. So I'm going to emphasize that we use this approach in ARIA to account for the model transferability. We kind of normalize like all the different years and regions by accounting for the thermal accumulation of the plant. We know that the crop phenology of wheat is driven by the temperature accumulation, so that's why GDD is important. But the problem that we had in Spain is that wheat doesn't fully go into dormancy, so it's very critical to account the start of season very accurately. For that, we took into account the crop calendars from World Cereal Phase 1 that we developed. We have the reference of our work there. And also we developed our own LSP model to have a better accuracy, especially on the regional level. And for that, small parentheses, I suggest to have more information on crop and World Cereal, I suggest you visit Christoph's presentation later, and also Italo presentation, poster in this poster session this afternoon to talk about this LSP model that we use in this study. So for that, going to the calibration sites. This is the same site in Valladolid, but across different seasons. When we consider like the day of the year, we can see a shift, okay, in the start of season mainly, and then the peak happen at the different times. That when we use the thermal normalization, kind of everything gets standardized. So good job, World Cereal, and good job, LSP metrics. However, when we are looking at the different regions, the GDT normalization improves a little considering the day of the year, but neither World Cereal or the LSP model are able to really normalize well. And for saying it, it's like you don't have a clear same day of the peak or ranges dates of the peak and a good end of the season that really aligns well that. But even like that, we continue using the GDT normalization. Keeping that in mind, how we proceed with the model, we had limiting data. That's what we have when we are working at field scale. So we used a simple linear model, like following like area basis. We wanted to keep simple. We wanted to understand well the correlations between the different spectral bands or spectral regions. So we just trained the model for each GDD. Okay, so each GDD is like kind of an acquisition. So here we have heat maps with the RMSE on top and the R-square correlation. And the best combination that we found was using band 11 and band 4, so SWIR and red bands. Based on that, if we plan to apply it over a different region, given the limitations that we see with the GDT normalization, it's really hard and it's not stable. So what we propose in this work, it's just analyzing the weight of each parameter across the season and focus on the timing of the lowest error, okay? In that timing of the lowest error, we defined a new vegetation index combining these two parameters that we detect as sensitive to yield, with yield, and like analyze the weight of each band. So in this plot, we see the temporal evolution of this index over the different fields of the calibration site. And we can identify, like the top line is the field with the highest yield, and the bottom line is the yield with the lowest yield. And we can see that how these crops or these fields go into the senescence has an impact on the final yield. So this parameter is pretty sensitive to that senescence rate that was cited long ago in some papers, old papers that we used to read. This was not captured by the DVI. I just wanted to include the same plot, but for the DVI, and even that with ARIA, we were working on this parameter, just near infrared minus red. This at field scale is not working so well. For the Sentinel one, we try to combine different, different products, different bands. VH and entropy, degree of polarization, etc. But the combination of two of them didn't have an added value than just considering individually each one of them. So in this case, our top parameters, combination of top parameters are like band 11, SWIR band, and the VH. In this case, the pattern of the vegetation index proposed, it's very similar to the optical, the Sentinel-2, and we kept the same structure, like linear relationship, like linear regression of the evolution of these parameters after reaching the peak. So, as results, so we first focused on the calibration side. We did live 1 year out validation. Okay, so every year, as the previous presenter explained, was extracted from the training, the calibration, and evaluated alone. Okay, so the first plot shows the Sentinel-2 vegetation index proposed, and we have errors very similar to Sentinel-1, so around 1,000 kilograms per hectare, and R square that for Sentinel-2 it's better than for Sentinel-1, but the key is combining Sentinel-2 and Sentinel-1 with errors of 600 kilograms per hectare, so it's very low, and very good R squared of 0.94, so that is really promising result. But when we go to the regional level validation, okay, so applying the same model calibrated in that limited region to other regions, well, Javier already presented this model applied to Egypt. In the case of Egypt, I have to say that we didn't use exactly these parameters, this band 11 and band 4. We had to use the calibration in Valladolid, but applied to other bands because band 11 was not showing well, and maybe it's because of the spatial resolution of band 11, that's 20 meter, and for smallholder farmers farming, it's too coarse. But when we applied it to Spain, so I'm not going to go to Egypt again, the results are not so good when we go to a different region. So the transferability, it's much harder than we thought. Even combining the current technology that we have, like Sentinel-1, Sentinel-2, is not so straightforward when you try to apply a model in a limited region to a different one. Maybe it's related to the GDT normalization that needs to be improved. Maybe it's just we need to train the model everywhere, and, well, let's see. But also I wanted to highlight that the transferability is more stable in the optical domain. So Sentinel-2 has better performance metrics, lower RMSE, and higher R squared than when we are using the fused product. So in conclusions, we established a methodology to integrate different spectral ranges and proposed a couple of new vegetation indexes that we are going to explore in future works, their potential. The GDT normalization is critical, especially we saw it when we were working at global scale. Here on field scale, we still detect that it needs some improvements, maybe integration of other climate variables. Regarding the comparison between Sentinel-2, Sentinel-1, or fusing both, at seasonal live 1 year out validation, it outperformed individually Sentinel-1 and Sentinel-2, but the regional scale validation, it needs more work, the transferability is not so clear, and optical seems to be more transferable than the combination of both. For recommendations, SWIR data shows a good potential. That's the added value of having these linear, easy models that we can understand well what's happening. It makes sense. SWIR is related to water content, and during the senescence, the water content is what is really driving that senescence. So it's really good results. So for the next generation of Sentinel-2, I think it's very critical to keep these bands in mind and have a better spectral and spatial resolution. Sentinel-2, we have challenges of Sentinel-2. I have to mention that after its failure in December 2021, we don't have so much frequency of data, so please, Sentinel-1C, come soon. I wanted also to highlight that simple models, when we are working with such a limited data set, are still the only option. Machine learning models are very nice, they provide very nice results, but at the end of the day, it's really hard to replicate those results, especially if you don't have access to that data. And as challenges, I would say that cloud mask of Sentinel-2 is still an issue. I mean, okay, we use cloudless product, but still we had to apply some filtering to avoid some variations. And for sure, it's been mentioned several times, but data availability and quality, it's really a key. It's not just having data, it's to know exactly the accuracy of that data, which is driving us crazy. It was really, really time consuming, and I have to say, we've been working really hard to get all the data collected, and like getting that data, it's really hard, and then managing that data and finding out that it doesn't make any sense, it's even more frustrating. So please, as international community, we have here GEOGLAM, we have here European Commission and so on, we have to advocate for a public peer-reviewed data set of field data. I think that's the way to go, to invest more time on building nice models rather than thinking, okay, this data set makes sense or not. And the transferability of the models is still an issue, so we still have to work on that. So I wanted to finish thanking my very nice team at the University of Valencia Global Change Unit, especially Italo, that has been working really hard on this project.
One quick question from the audience.
Thank you for your presentation. I'm Peng Yu from FAO. And I have a question about the physical principle of your WYVI.
I didn't find a nicer name. Well, yeah, in reality, you can see that the SWIR band has a higher weight in the band, okay? So the SWIR band has a big importance, and then you have the red band that also is related with the chlorophyll content. So as you go into the senescent, the water content decreases, then you have the signal of the SWIR affected by that. Also, the chlorophyll content decreases, you have also an affection on the red band. So that's why you can see that that senescence that happens to happen like much faster in crops with lower yields than in crops that stay greener, like healthy, during much longer. So that's why using the combination of those two bands, I think that's the models told us that that's the way to go. That's the way to look at it. On the structural part, on the combination with the SAR, the VH is very structural. So for sure, you're combining the SWIR and a structural band. VH, you're combining the vertical and the horizontal. So it's sensitive to that changes in the patterns of the wheat due to the kernel appearance and so on.
Thank you. So we can go on with the next presenter, Jonathan Pound, FAO JUICE, talking about the use of Earth observation for agricultural monitoring at scale.
This one. Okay. Good morning, everybody. I'm Jonathan Pound, not a scientist, but an economist working at FAO. And I'm here to present results of some work that we're doing, but looking more at the application of research, including Earth observation-based yield forecasts, but not only that, but also importantly, the collection of field data as well. And I want to try and illustrate with this work, an example of trying to bridge the space between science developments and policy processes, but in the context of improving crop monitoring capabilities in the Ministry of Agriculture. So this is a joint work between ourselves and NASA Harvest, and it's based on a USA project that finished last year. And we implemented the work in Malawi, Namibia, and Kazakhstan, but for the purposes of this presentation, I'll just be focusing on the results in Malawi and Namibia. So just to give you a background, so at FAO, one of our key tasks in our team is to monitor global crop production prospects, also food security conditions, and food market situations. And this is all with intention to try and identify imminent shocks in the agricultural system, which countries are going to be most affected, and with this information, support responses. So a particular challenge that we face is a lack of in-season information on crop conditions. This data is particularly sparse in, let's say, highly food insecure countries, but also countries where rain-fed smallholder agricultural systems dominate. And so these populations are particularly susceptible to shocks in the agricultural sector, and they require external assistance. So this in-season data is critical to inform policy responses and also to help design longer-term resilience-building measures. So together with NASA Harvest, we collaborated to design and test several products to form like an integrated approach that can kind of bolster crop monitoring capacities in the ministries of agriculture in Malawi and Namibia. And we focused on 3 areas. The first is looking at crop assessments to understand how crops are growing, the conditions, if they're being impacted by pests or lack of access to inputs. The second area we wanted to tackle was to try and improve the data on the identifying where crops are growing as well. And that is developing cropland maps. And the third area, which is more of the interest for this session, is on looking at the crop outputs, so the perspectives of crop productivity. And I think what I want to stress, and maybe this is very simple and rudimentary, but it's our close collaboration with the governments at the start of the project and this whole process as well. And I think that is key to making data more usable rather than just available. And so from the start of the project, we actually co-developed all of the tools and methods with the ministry colleagues as well. So yeah, just to look at the first area in terms of the crop assessments. This data in Malawi and Namibia is often being used, well, the data is collected from the farmers often on paper-based forms, and it's also based on farmers' perception. So in that sense, there's a tendency to have higher errors or less accuracy, but also it's costly in terms of collecting that data. So we designed a collection of different mobile applications that could collect data at the field level. And in essence, we digitized much of the Ministry of Agriculture's existing surveys. And the advances for the ministries using these applications is it speeds up data processing both at the field but also at headquarters, and that can quicken decision making. All the data is geolocated, and that obviously helps enhance the use of observation analysis. And the data we made available on web-based platforms, as you can see in the bottom right as well. And I think this is quite an important logistical point or aspect, being able to see in real time the data coming in. You can also correct, let's say, errors that are occurring in the field during data collection. For example, in Malawi and Namibia, we often noticed that there was a clustering of samples that the enumerators were collecting. And so with this information in real time, we could call up the enumerators and ask them to change their sampling methods and spread out the data collection. So the data we collected was, it ranged from weather performance, input use, conditions of livestock and crops, and also food security indicators, but the data is largely qualitative. So we wanted to introduce 2 new aspects, 2 new quantitative measurements to make the data more, let's say, robust. And the first is on GPS area measurements. And although this is not new at all, but for both Malawi and Namibia, integrating GPS area measurements during their crop assessments was quite a novel concept. And just to highlight quickly the benefits, obviously with better area measurements, you improve crop statistics. But I think another important aspect is that you also can help support farm management practices as well. So just to highlight, on the bottom left-hand corner is a graph of field data measurements that we took in Malawi in 2023, 2024. And on the y-axis, the GPS estimates, and on the x-axis, the farm estimates. As you can see, there's a tendency for farmers in Malawi to overestimate the area of their field. And that can obviously lead to inefficient use of inputs and potentially higher the costs as well. The second area is on yield measurements, and we designed an application that guided enumerators to collect yield data using crop cutting techniques, which is like the gold standard of yield measurements. The application included several steps to input data, and we also automated the provision of random plots within the field as well after taking the area measurement. The application also provided the immediate calculation of the yield at the field. And yeah, having both the GPS area measurements and also the yield data at the field, we were able to give that information back to the farmer. And I think that's a critical point in terms of making, let's say, innovations more inclusive, not just for institutions such as the Ministry of Agriculture, but also to the farmer as well. And then, yeah, it builds trust or fosters trust in these new developments throughout within the agricultural sector. So the second area was on crop location to try and improve the cropland maps that the ministries use. So we conducted more than 10 field campaigns in Malawi and Namibia, and we collected over 10,000 data points in those countries. And all this information is available online. And in addition to collecting the field sizes, we also include the crop growth stage and the crop type as well. We developed several maps, including a crop-specific map for Malawi. And this map was actually used by the ministry last year to try and quantify the impact of the floods after Cyclone Freddy as well. And it was also used to help guide the ministry in terms of identifying the areas that are most affected due to the floods as well. So that, I just want to illustrate a real example of using these maps by the ministries. So the third area is on the provision of remote sensing machine learning-based in-season yield forecast estimates. And here we use the GeoSIF model, which is a model developed by the University of Maryland and NASA Harvest. Normally in Malawi and Namibia, they have yield data close to the harvest period or at harvest time as well. And so the intention with this work is we wanted to provide, let's say, early indications about potential crop productivity of the main cereal crops at an early point in the season. And that provides early warning signals in terms of national food security, can prompt anticipatory actions. And with that, you can lower perhaps the negative impact of the shocks and lower cost of interventions as well. This data was also used by both ministries in the countries to validate their traditional crop assessment surveys as well. So we're giving them an extra layer of data from which to validate their field data. Just to briefly go through the steps of the GeoSIF model. So all the Earth observation data was spatially harmonized. There was a wide range of data used from precipitation, temperature, soil moisture. We applied a crop mask and crop calendar to get time series Earth observation data, so everything is crop growth and region specific. About 60 climate indices were created, and this was used to train a machine learning model based on a gradient boosting technique. And we gave all the model results to the countries, and throughout this process, we had several meetings to explain the methodology, the reliability, the uncertainty of estimates. And yeah, again, perhaps this is a very obvious point, but I think that close dialogue with the ministries to help them understand what the actual results mean, how to interpret them properly, and what the methods are, really helps build trust in this work as well, and helps integrate this kind of these new, let's say not new, but these techniques within the ministry's own reporting systems. In Malawi, we went a step further, and this year, and it also emphasizes a strong need and demand for this type of data early in the season. The Ministry of Agriculture requested that they receive the yield data also during this year as well. The project closed last year. And so since January this year, we've been providing yield forecast estimates to the ministry. We have monthly meetings with them, and we go through all the results, the method again, and what are the underlying influences driving those results as well. And this is particularly important this year because of the El Nino event that's causing dry conditions throughout the region, and there's a great uncertainty in terms of the impact or the magnitude of the impact on crop production. And an encouraging result is actually the ministry made an official request internally to make the GeoSIF results become, let's say, an official part of their crop assessment exercise as well. And so they want to use this data as an additional source to help inform their production estimates. Because of the El Nino situation as well, we were also requested to expand the model results to all of Southern Africa. And so, these are the results. The larger map shows the results of the primary cereal crop as of May. This is data as of May, and the smaller crop is data from April this year as well. And as you can see, we're expecting lower than average yields across the region. This information is very important. I mean, it's used to inform, let's say, FAO, our offices in the field, and that can encourage opens dialogues with the ministries to run out more assessments. Also at our level in FAO, we actually use this data to inform our cereal demand and supply balances as well. And as you can see on the right-hand side, the table is one of our balances for Zambia. And we've used the yield estimate for Zambia to come up to try and better understand what are the import needs for the country. And given the situation in Southern Africa with the drought and the likely increases in import needs, to have a better quantification of what that impact would be helps both inform our offices to support governments and inform responses, but also at the regional level, that this kind of information can really provide beneficial terms of policy coordination, and to support early planning. Just quickly to go over the recommendations. Again, I think these have been touched upon already. But yeah, no, it's really to understand what we found was very beneficial to help integrate the results, was really to work with the ministries right at the beginning, or the institutions you partner with, and co-develop all the tools. And the second is on expanding ground data collection as well. And obviously that's crucial to build trust, to validate the model results, and also maybe to harmonize the methods to collect that data so that information is available to all and can be a wider audience to uptake that data. So thank you very much.
Time for one question from the audience. No? I have one curiosity. How many crop cutting samples did you collect? Because they're really time and resource consuming. And if you're planning to use for yield forecasting as well in the future?
So over 2022, 2023, in Malawi, I think we collected more than 600 samples, in 3 regions in 2022 and 1 region in 2023. And we looked at the results comparing to the official statistics, and there's discrepancies between what we saw in the field and what the government is reporting as well. But there's consistency in the differences as well. So.
Thank you, John.
Thank you. Thank you.
Okay, so I give the floor to the next presenter, Solveig Blocker. Resilience under extreme circumstances, harvest and yield estimation for Ukraine 2023.
All right. Okay, my name is Solveig Blocker. I'm from Vista Geoscience and Remote Sensing in Munich, and I'll be sharing you our results on our harvest and yield estimations in Ukraine in 2023. Okay, so at Vista, for those of you who don't know us, we use digital twins of agricultural landscapes to do our yield estimations. And we use radiative transfer modeling to get our LAI time series from EO data, so specifically from Sentinel-2 data. And this LAI time series is then assimilated into our crop growth model PROMET, which is a physical-based model, not an AI model, just so you know. And then PROMET can actually simulate environmental processes as well as crop growth through the season. With every update of EO data that we get, we can also update our simulation, which is really important because, of course, I'm sure you're aware, the agricultural season is highly dynamic. We need continuous updates to actually get proper results. What you can see here really well is the phenological development in Europe, kind of reason why we need the updates. So the phenological development always starts in the southwest of the continent in Spain and then moves northward. All of our analysis is always done at field level, so we can simulate everything based on every field and every pixel in every field, but we can also do this on a much larger scale. All of our analysis always begins with the LAI of the fields that we simulate. which is combined with meteorological information, soil, topography, and crop type information, and goes as input into PROMET to produce information on water stress, irrigation needs, nutrient needs, and plant development, and eventually yield. All of these data, all of this field level data is usually aggregated to a higher level, so to regional and national level, like in this case, the Orion level in Ukraine. Whenever we do our analysis, we continuously update it through the season and usually until harvest has been concluded. We obviously validate our data every year, which you can see in the plot on the top right. So what we can see there is our yield estimates for all the crop types that we usually simulate at national level against the official Ukrainian statistics. The first step of our analysis is always our in-season crop type classification, where we first identify crop groups, so major crop groups like winter cereals, summer cereals, and summer crops, using an unsupervised approach based on LAI profiles. And then within those groups, we do a crop type classification based on spectral information and spectral indices with a random forest classifier, where we get specific crop types like grain maize, sunflower, and soybean. Once we actually have our crop types, we can get our yield estimates. For the season 2023, our yield estimates look like this. What you can see here is the yield in tons per hectare at oblast level for the 6 different crop types that we did our simulations for. So winter wheat, winter barley, rapeseed, spring barley, grain maize, and sunflower. As a side note, all of this data has been delivered to the Ukrainian Ministry of Agriculture, like we already did in the 2022 analysis. The darker green tones show higher yields, and the orange and red tones show lower yield. And what you can see really well is that, generally speaking, we see lower yields in the south and east of the country and higher yields in the west, which is actually quite normal because it's due to environmental conditions in the country. We generally estimated that there was an increase of yield in 2023 when compared to the long-term mean. This is actually different from what we saw in 2022, where we saw a yield decrease, but that was mostly due to dry conditions, so low precipitation and high temperatures. We also estimated the production and the production deviation, so the deviation from the long-term mean. We monitored the harvest progress for each of our crop types. What you can see here is all of the data on national level, but we also did this on sub-national levels, so oblast and raions. And what we did as well was to estimate the potential production for each of our crop types in the frontline area if it had been used for agricultural production. So this table gives you actually quite a bit of an overview of what we did in Ukraine in 2023, but obviously there is more. So when we started our analysis last year, or all through our analysis last year, we kept seeing the impact of war in our data, like in the summer crops classification, where you can see this pink belt running its way in through the east of the country. We see that the war has actually changed the dynamics of agricultural production in some areas in Ukraine to the point where you can see it really clearly in RBG images. And so from this, we can actually see that there has been a lot of land use changes in this zone, so that we see vegetation developing, but actually not that much agricultural production happening. When we go up on scale, we can actually see the full impact of the land use change. As I mentioned earlier before, we did our harvest monitoring for Ukraine for all of our crop types, and what you will see here is the harvest progress for winter wheat in 2023, and each of the green points represents a single field that has been harvested in 2023. All of our harvest estimations are always based on Sentinel-1 coherence data. And what we can see here really well is that we see a dynamic that we see virtually every year. So harvest starts in the south of the country and then moves northward. But what you can also see is that not that much is actually going on in this frontline area. And based on our analysis of optical information and UNSAR information, we actually estimate that 6.5% of the agricultural area in Ukraine was not used for food production in 2023. This analysis on Ukraine data was quite extensive, and we think we did rather well, actually, but just to give you a bit of a teaser, we always try to improve our analysis, improve our estimates, and just become better at what we do. So in our Horizon Europe project Stella, within our use case, we plan on improving our input data for the crop growth model PROMIT by using data fusion, improve our field segmentation, improve our time series imputation, and testing different kinds of meteorological inputs to be able to have robust yield estimates even early in the season, meaning that we want to have robust yield estimates as early as 10 weeks before harvest. But to do this, we need more data. We need proper data availability, and we need to decrease systematic undersampling due to arbor constraints. This is something that people have said before this week, so this is not exactly new. But what we see in our data is actually when we use all of the pixels that we find for a crop type in Germany, for example, versus the ones where we have good data availability, we see that when we use all pixels, we have an increased error rate when we compare our final results to the statistics. So in the plot, you see the number of valid scenes per pixel. So with this in mind, pretty sure I went through this presentation, but anyhow, we have come to the end, and if you have any questions, let me know.
Questions? Thank you. It's in the middle.
And thank you for the presentation. The results that you have shown are based on the modeling, I expect.
Sorry?
The results that you have shown for 2023 for the crop yield are based on the physical model, right?
Yes.
Yes. And you know that there was the dam that was destroyed.
Yes.
And in the southern part of this area, now because we have done a study, and so I was wondering if you find some important decrease in crop yield in that area or not.
I don't have the numbers on me right now, but what we saw was that we did not see that much of a yield difference in winter crops because they were largely done by the time the dam was broken. As far as summer crops go, in the area we're speaking of, it was mostly concerned with sunflowers. I don't have the numbers on me, but I think we did see a decrease in yield. Come find me in the coffee break later, and I can probably talk to you a little more about this.
Thank you.
More questions? No, maybe a question. Your model, if I understand well, is in full prediction. So compared to the other presentation we have seen, you are not calibrating anything. You don't need ground data, basically.
We don't need ground data. Our model is transferable, so we don't need any training data. We use the LAI information that we get from Sentinel-2 data and meteorological information and soil, and then we use this as input for PROMIT. Yeah.
Thank you. Very interesting. Yeah. Yeah, we move to the next presentation. Etidal Amin predicting in-season crop yield at the field level with Sentinel-2.
Oh.
Thank you.
Thanks for that. Okay. Yeah, so hello everyone. I'm going to present our work where we propose a workflow for crop yield, so for in-season crop yield using Sentinel-2 time series. So one of the main challenges in cropland monitoring is to be able to timely assess the crop performances, and ideally to be able to provide or to estimate, to anticipate how productive the crop will be in the future. So of course, as we saw, that the remote sensing time series-based models usually are able and capable of providing like reliable estimates, but once we are like around harvest or even after harvest. So of course, what could be greatly like more beneficial and more interesting is to be able to provide like crop yield estimates within the growing season, so as the crop develops. And this could be really useful also for like supporting management decisions, and also to evaluate potential yield losses due to external factors or so on. So the objective of this study was to propose or develop an in-season crop yield forecasting modeling at pixel scale. So here you can see like an overview of the workflow proposed. So basically, the input data consists on field data, so yield data that was collected on the field, and together with optical remote sensing time series, so particularly of Sentinel-2. So from then, we trained different machine learning regression algorithms. So there were Gaussian process regression, kernel-rich regression, and random forest. So the yield field data dataset was used for training and validating the models. So once these models are developed, their performance is basically assessed continuously through the growing season. And finally, once the models are developed, they were applied for in-season yield mapping. So regarding the study area, it's located in a farm in northwestern Switzerland, where the main cereal crops cultivated were wheat, barley, and triticale. And the yield data was collected using a combined harvester, so the data refers to a 10 meters pixel size, and the available data covered from 2018 to 2020. Regarding the satellite imagery, we use Sentinel-2, and we processed 2 vegetation indices, NDVI, and also a recently introduced index, which is a nonlinear enhanced version of NDVI, which is called kernel NDVI. And finally, for calculating the growing degree days, air temperature from the MeteoSwiss network was used. Okay, so finally with that, we have like the original time series, and this corresponds to the satellite image acquisition dates. But the gap filling is like a really important step. Why? Because by that, we are able to reconstruct a continuous time series of the crop, so we have no more gaps due to, for example, other recurrent factors such as cloud cover. And for doing that, we used GPR, so we basically optimized that method so that we can reconstruct the time series at any year and at any point in time. And so particularly the performance of 2 different time series were compared. On one hand, the regular time series, which is based in day of the year, and on the other hand, the cumulative temperature time series, which is based on the growing degree days. So the reason or the rationale of using that was already explained by the previous speakers. And so with that, meaning that it's based on GDD, so it means that the temporal axis of the reference of the time series are the GDD values. So then the workflow for the yield modeling consists in continuously training and testing the different machine learning methods at regular steps during the growing season at any point in time and at different crop stages. So these crop stages basically refer to the successive values of the GDDs along the season. So at each point in time that we want to predict, we basically take the time series until that point, and then we train and test the model. So for each one of the years, the yield field data was split into training and testing. And yeah, for the training, up to 900 pixel training samples were used, and for testing were 400 pixel samples. So here are the first results, and what we can see is like a comparison of the evolution of the performance of the 3 different methods used in terms of accuracy and error. So the first row on top, we see the evolution of the accuracy, the error square, and the error where the models are trained with regular time series. So overall, we see that, of course, most likely and most of the time for all the years at the end of the season, the accuracy tends to be higher usually and the error lower, but we don't see any clear pattern. But meanwhile, the models that were trained using the growing degree days time series, we see a consistent increase in the accuracy. So this usually happens around 1,300 GDD values, which in the case of the cereal crops, corresponds to the flowering or the anthesis stage of the crops. And after that, the accuracy basically remains kind of stable, so no greater improvements are achieved afterwards. So just to have like a closer look to this, to the performance of these models, what you can see here is so we extracted the statistical metrics at different crop stages, let's say, so at different GDD values along the season. So 900 is like early stages of the crop stage, and then 1,800 GDD like corresponds to later stages closer to the harvest. And so overall, the main message here is like usually when comparing NDVI and KNDVI, what we observed is like KNDVI slightly performs better. So the final accuracies, you can see they are like really similar in terms of accuracy and an error. But the good thing about using KNDVI is like it was able to achieve higher accuracies earlier than just using the regular NDVI time series. And overall, so these results refer to the scenario where the training and the testing was performed in the same year. And so there's no great differences between the three different models, so they tend to perform similar. And the general trend, in line with I was showing before, is like as we progress, as the season progresses, so we have an increase in accuracy and a decrease in the errors. So, but what happens when we change the scenario? So in this case, we train with data from 2019, and the testing was performed 1 year before in 2018, and 1 year after in 2020. So overall, and I think this is in line with the previous presentations, what we can see is like a general decrease in terms of accuracy and errors, like in absolute and relative terms. But still, we still observe the same trend. So as the season progresses, the accuracy tends to increase and the errors are lower. And again, no greater differences between the machine learning methods tested. So then, once we have any of the yield models developed, we can apply the model to any gap field time series to make a forecasting at any point in time or at any crop growth stage, meaning the GDD value. And here you can see a yield map obtained at this flowering or anthesis stage, which is more or less up to 2 or 2.5 months before harvest, corresponding to 1,300 GDD. So that's before harvest. And yeah, so overall, this is an example of 2019. And so the absolute mean errors are like below or around 0.7 tons per hectare, and in relative terms, around 8%. Again, this is the same analysis, but when we change the scenario, so the training was in 2019 and the testing 1 year before, in 2018. So yeah, again, we see this, decrease in accuracy. So at the same crop growth stage or point in time, we got higher errors. But still, when we perform like a yield seasonal mapping, we see that we can still see like a consistent improvement in accuracy across the growing season. So maybe it's later, but we can still have like a reasonable error of 0.8 tons per hectare and 30% of error. Okay, so then finally, to have like an overview of this proposed yield forecasting workflow, so we present here like a validation of yield estimation just after harvest to see how it really performs. So in this case, only the results of GPR are shown, and so you see like a comparison between the estimated and the reference yield data at 2,700 GDD. And again, so in the scenario where we train and test in the same year, usually higher accuracies, and when we move to unseen years, the accuracy obtained is slightly lower. And with this, two limitations can be highlighted. No? So on one hand is the limitation of the machine learning regression methods to be able to like generalize, because of course they are purely data-driven methods. So as soon as they are applied to data that it's unseen for the training or really atypical, they tend to perform poorly. And also a second point is regarding the field data availability. So here you can say the distribution of the yield field data set per year. And yeah, so in 2020, it was an exceptional year with really high yield values. And this is, was not, so the models are struggling to be able to predict in this.
Sorry, can you wrap up?
Yeah, sorry. Yeah. So, and then this finally, so this is the final almost slide. So we wanted to test the transferability of this workflow in another test site that were not used for before. And in this case was data from Valladolid in northern Spain. Okay, so in this case, the yield data didn't refer to pixel size, but it's rather like parcel aggregated data, so one value per parcel. And we slightly modified the workflow so to make it like more faster and more efficient. So instead of GPR for gap filling, we applied Whittaker. And also the GPR model was reduced using active learning techniques. So yeah, so here you see two examples of the workflow over width and over valley. And yeah, so we obtain like a distribution of the yield per pixel, and then we basically aggregate them, and then we sum them up. And on the left, on the right, you can see the comparison of the parcel total yield, the predicted against the reference, and the deviations are in case of width of 40%, and in case of valley of up to 6%. So that's the final slide. So to conclude, I would say like so vegetation indices time series based on GDD. With this, it's possible to make forecast of crop yield within season, like before harvest, up to 2 or 2 months and a half. And the reliable and accurate yield estimates were obtained around the peak of the season, let's say, and afterwards, like no remarkable accuracies can be obtained or achieved. And so, yeah, either with the limitation, machine learning, with machine learning, it's possible to obtain like a consistent forecasting accuracy along with the development of the crop phenology. And yes, as final message, I don't want to repeat and make it longer, but it's just saying that, yeah, again, as the previous speakers and presenters and chairs were saying, the data availability is a key point in order to provide reliable and robust models. And not only the yield data, but also the management practices information, like when was the sowing, when was the harvesting. And then one last point would be about the standard accuracy that are expected for this type of product. So maybe the end users or the institutions that are interested in this type of products, they want like a certain accuracy or certainty. So maybe they say, okay, beyond this uncertainty, the product is no longer useful. So maybe it could be useful to have like a general guideline of the uncertainty thresholds in order to deliver the product with a certain standard. Okay, that's all. Thank you. Sorry.
Thank you. And good questions. We are a bit late, but let's open the discussion and questions and reaction from the audience. Maybe also recommendations that were not made by the presenters. Yes?
One question.
Okay. Sorry. Thank you for all the presentations. I think it was all on yield forecast, looking at it at various ways to do it. I thought this was quite interesting to compare. But you saw in all the machine learning algorithms that they had problems to transfer it from one year to the other into extreme events. And that's my proposition to you. You should really look into process models, because that. Hello? Yeah. This is the strength of the process model, that it understands that the weather conditions are now, that it is too dry, too hot. And this allows you to transfer it from year to year. And I think that is why we succeeded without calibration of incident data. That was a presentation of Ukraine, that we really can transfer it from Europe, where we learned our model, to Ukraine without any adaptations, and from year to year. That is really the strength of it, combining both.
Any further comments? Oh, yeah.
Thank you. Martin Clavry from the GRC. So the clear added value of observation in yield forecast is in season, because after the season, the statistics are quite reliable, and so the observation is for early season and if we focus on statistics, I think it's very important to clearly describe the experiment. We have seen some explanation of the limb 1 out. I think this needs to be a clear reference and the good practices, including the way you design the model and the way you calibrate the model. And sometimes it's also good to compare the performances to like a baseline model, which you can get the 5 years average at a subnational level, which sometimes may give you better performance because the year-to-year variation of these regions is lower than your prediction. So I think this is important, and this is important to account when we conclude on this in-season forecast. Thank you.
Definitely. Also, there was a request from presenters on, let's say, common metrics and statistics, and definitely they should be live 1 year out, or I mean, good split between calibration and validation data.
Some graph with a spatial variability, which is not the one we want to target, and even seen some spatial and crop variation on yield, which I think we should really avoid.
Any further comments on? Yeah.
Hi, Jonathan from CSR. Thanks very much for all those presentations. I think Yannis presented about the ag MIP machine learning effort, and I think that resonates a lot with what is being discussed here, particularly on validation practices, metrics, and benchmarks. So I would further encourage his comment from, when was it? In the beginning of the thing, to join the AgML group to discuss that, so we can have a cohesive way of doing that. And a second point is, I fully agree with Heike, we should be looking more into process-based modeling. A lot of agronomy has been developed and is encompassed in those models that we should take advantage of it. Just a general comment. Thanks.
Yeah, thanks.
Thank you. If there are no further comments,
we
might close the session.
Close the session.
Kind of late. Thanks to presenters and to the audience.
and we put the clicker there, so you can present from there. I think. No, it's you can follow on the TV.
Yes, but the remote, if you click in that sense, it's working, or you need to.
Thing there.
Okay.
So we are sitting in the presentation, or are we standing here?
Sitting. It's going to be faster, because otherwise we lose too much time. If you guys are okay with it, I thought it would be more. Okay, that's good. So we want to be opposite or what?
Please take your seats. Okay, welcome back. Please take your seats. You know, like Sven, thank you. Apologize, we had to reduce a bit the duration of the coffee break, but we tried to catch up the delay. So it's our pleasure today to have this quite numerous panel that we have here to discuss about the in situ data. So I'm Raphaël Dandrimo from the Joint Research Center of the European Commission. And together with Sven Gilliams from GEOGLAM, we will briefly introduce the panel, and then we will let the floor for the panelists to have a short presentation, supported with some slides. It would be quite short, so I will ask to try to fit to the 5 minutes you have. And then we will have some question with you. We've heard in the previous day, basically, that the in situ data is crucial. I think it was in most of the recommendation. And this is a topic that has emerged because the other problem have been kind of solved. We have plenty of free and available data. We have computing power to handle it. Of course, there are still a lot of questions remaining. But that data in situ data gap is still very important. And yes, several years ago, I think in the Living Planet Symposium, the two previous sessions, we initiated to have with the GRC a session specific about in situ, which was about novel approach to collect in situ data. And so I think this community has grown a bit, but it's not a community per se because we all need data. And so we are very happy to share this session, this panel, sorry. And I'm happy to give the floor to my co-chair, Sven.
Okay, thanks, Raphaël. Yeah, from a GEOGLAM perspective, I think, like what Raphael just said, LPS was an important one. Even the previous workshop, in situ data, was in the recommendations, how to collect and gather and share. And from a GEOGLAM perspective, I think what we really want to do is bring together the community, or several communities. It's a large community. We saw the session before on yield, also crop type mapping, but there is a number of different in situ data needs. Try to bring together the community within GEOGLAM, try to harmonize the data set, try to make it fair. There's lots of research data available, but it's hard to find. With the GEOGLAM, we're trying to see how can we build this database and how can we make it available to push research and, at the end, operations. And the idea of this panel is bringing together a number of experts in the in situ data domain. We have policy, we have private companies, we have research, and we thought, okay, let's get their ideas on the status of in situ data, what are the challenges, and see if we can find some recommendations for ESA and the European Commission to take the next steps in situ data. So today in our panel, I'm taking too much time, we have José Miguel from EEA, we have Inmal Becker-Chef from NASA Harvest, GEOGLAM, and the University of Strasbourg, so she has several hats. We have Grégoire Tombé from Green Triangle, Sophie Bontemps from the University of Louvain, La Neuve, Luca from, I'm not going to even start with your family name, Luca, from EFTAS, and then Stefan Fritz from EASA. So with that being said, I think we need to be strict in time. I already took too much time, so Jose, the floor is yours. I think the mic should be working.
Hello, good morning, everyone. I hope you had a good cup of coffee. Yeah, let's see if I go to my slides. Yeah, perfect. My name is José Miguel Rubio Iglesias. As Sven has said, I work at the European Environment Agency, and why I'm sitting here is because I'm responsible for what is called the Copernicus in situ component, and now it's called cross-cutting coordination of Copernicus access to in situ data. We have heard a lot about in situ data over the last 2 days, and I have prepared a very short presentation, which I think I will only repeat and insist on things that have been said. How important is accessibility to in situ data, in this case for the Copernicus program. When we speak in Copernicus about in situ data, we refer to anything basically which is not captured by satellite. We are speaking about environmental observations, we are speaking about maps, any kind of auxiliary data. And among these, of course, we are referring as LPIS, or the aid application data, which also discussed here. And as we have heard in several presentations, this data is essential for training the algorithms, for validating, calibrating Copernicus products. And without in situ, Copernicus, the program, cannot deliver on its main goals, on its data, products, services. And that's a fact, and I think that's important that we keep this in mind. But Copernicus doesn't have, we don't have let's say a Copernicus data provider network, so we need to rely on a myriad of institutions, data providers at national, regional, global level, which makes this is a particular challenge because we need to speak to many institutions, and there needs to be a sort of a coordinating effort. That's why EA has this role of cross-cutting coordinator. Copernicus is implemented by a number of entrusted entities, and they are all in charge of getting access to in situ data, but there is a need for particularly key aspects on accessing in situ data that someone, in this case is the EA, having access or providing, facilitating access to in situ data. Very quickly, how we are supporting the entrusted entities and where the agricultural data enter into place. We set up and operate Corda, which is a geoportal where we provide to the service providers, those who are creating Copernicus products, access to the origin where the data is hosted by the national or regional authorities of geospatial data. We, of course, combine and provide access to a number of in situ data, among them LPAs and GSA data. We have heard about before in several panels and presentations the difficulties to have access to this data and that there are several data going on there. What is now available in Corda for the service provider is what you see on the slide. So we have data from 2003 on LPA's data. We don't cover the full European, and we still, this is just Europe actually. And we have even less data for GSA in particular. The use of this data is very relevant for several products. In Copernicus, I could not give a full overview because we don't have time and I need to pass the micro now, but particularly, and again, you have heard about this product, which is one of the star, let's say, of the CLMS portfolio, which will be available soon on the crop type map. And two particularly sources of in situ data or two in situ data collections are essential. One is what I have mentioned about LPAS and GSA, which we have the issue of not being available for all countries, not being available for all the reference years, which implies difficult or try to find out a new validation approach. Of course, we need to harmonize. It's a job that it takes time and money. And we, of course, have to use, and we use as well, the Lucas dataset, which now with the change of the reference year has also implied some challenges. I will stop here because I want to pass the floor to my fellow members of the panel, but of course, happy to discuss then later how we see this in the future.
Thank you, Jose. And now we have Imbal presenting.
Great. Hi, everybody. It's a pleasure to be here and an honor to be on this panel. I think this is not, these are not the right slides, but that's okay. I had a different, so the title slide that I had on here, or maybe you don't see it, it's in white. It says, is it the last hurdle? And I would argue, hurdle to what? Right? And so, yes, I think we've heard so much that this is absolutely critical, and we've known that, we've been advocating that for a long time. But I wouldn't say it's our last hurdle. I would say it's one of the key hurdles that we have, because if we're thinking about in terms of the impact, right? And ultimately, I think that's what we're all here for, is how do we inform decisions, whether it's to do with insurance, whether it's to do with early warning, or whether it's to do with whatever that application is, has to drive what we're doing. And I think the gap to get that data and really thinking about, we have a lot of challenges around, what we've heard today. How do we better work with those end users and making sure that where we are in terms of the state of the science is reaching to where we are in the state of applications? And I would argue there's a really large gap there. And so, but anyways, let me get into a little bit more. And I think we were asked to give a quick introduction of the organizations we represent. I'm here wearing two hats. One is NASA Harvest, which is NASA's Global Food Security and Agriculture program. We sit in what used to be Applied Sciences and today is Earth Action, where our main mission is to advance the adoption of Earth observations across the agricultural sector to ultimately benefit decisions in food security and sustainability and overall agriculture and agricultural markets. At the same time, this is NASA's contribution into GEOGLAM. NASA Harvest very much builds on the relationships and what we've built as a community in GEOGLAM. NASA Harvest would not exist without having had GEOGLAM exist. And one of the things we do in terms of the program is to always start with the end users and making sure that the work we do is driven by end users. And I think these are the different application areas that we're focused on. I would say largely these are the application areas that a lot of us in the room are focused on if we would look at those in GEOGLAM. But these are what has to drive when we're thinking about the in situ data, right? Are we talking about providing estimates at a global scale of yields for informing agricultural markets? That has some requirements. Are we talking about early warning systems? Are we talking about insurance? Are we talking about application of nitrogen recommendations or management? So there are a lot of different questions that I think we need to be thinking about. Now, in terms of one of the questions I think to address is how are we collecting ground data under NASA Harvest? And I've put here a few different categories. And I'll talk very briefly about some of them. One of them is work that Catherine Akalemba has been called Street to Sat that she's developed with trying to innovate on how do we collect more data, right? And putting cameras on helmets or cameras on cars, and then going and interpreting those photos automatically to look at where are the crops, are there photos with crops, and can we identify those crops, right? And then geolocating those. But I would argue a lot of the way we have to be thinking more and more about is through partnerships. And whether that's partnerships, in our case, we build a lot of partnerships with ministries of agriculture. And I think Jonathan gave really nice examples as to how to do that and how can you collect a lot more data. But also partnerships with the private sector. And I would say we haven't done as good of a job as we should be doing on doing that. Because if you think about how much data exists, it's tremendous, right? You think about all the combines, all the companies, all the insurance, I mean, a lot of that data does exist, but how do we articulate mutually beneficial propositions so that we can have access to that data, right? It's really easy to say it's IP, or it's really easy to hide behind a lot of different kind of, privacy. But if you get at and you can show that your application is actually going to advance what they're doing, then that becomes, and I think we've worked with Green Triangle and started to do that, and I think that's a good example. But we have increasingly found that actually the barriers that seem that you can't cross them actually become very crossable when you really start to partner and work together, and you start to really adopt that co-development and ownership and being driven by end users. We have different programs on educational programs on citizen science, and this is an example from Argentina. We have run our own field campaigns or campaigns with different organizations and governments. And we also do some visual annotations, and I think that's an area that in some cases, okay, I've got 1 minute left, that is also, pseudo in situ data or where we don't have any data, we're able to do that. In terms of the types of data that are collected, again, I think it's a very wide range. Okay, well, that's a way to finish my time quickly. I've listed a lot of different data sets that we are collecting here. I won't talk about all of them. I think some of the ones that coming off like the previous session is around yield, for example, right? And is ground, our ground data, is that ground truth? And there are enough studies and from our own research and a lot of people, right? Like, how do you collect yield data from a field? Is it a full field harvest? Is it crop cuts, and how do you sample to get representation? Is it from the combine? Well, we know with working with companies that they say they don't always calibrate the combine. And so we've found that actually getting the truck data, that is weight, and that's what they're then selling at the, or delivering to the elevators or to the grain silos, becomes actually the most accurate data. But again, I mean, that's very difficult to collect and to have access to, but I would just argue that we have to also think about that between ground data and ground observations. So I'll say, why is this important? I think we all agree this is important for all these products that we're talking about, that ultimately are the building blocks that when we bring them together is how we get to information products that are then going to answer the questions that, that we need to. And I don't know if I'm out of time, so I'll stop there and leave these up as the challenges and opportunities. I'm sure a lot of us will come back in the discussion.
Okay, thanks, Imbal. A very good presentation. I thought you would make it like 27 slides in 5 minutes. It's normally your way to go. I think on your opening statement, there was a big question mark about the last hurdle. So that's actually, it was a bit provocative, and that's actually what we wanted to have here. But in the interest of time, we can go to Grégoire for a presentation on Green Triangle.
Yeah, thanks a lot. So my name is Grégoire Tombe. I'm a co-founder of Green Triangle. And at Green Triangle, we provide an end-to-end crop insurance claim management tool to help insurance company to gather data on the crop stage and the crop states and on yield. So originally we started to argue with the insurance company that we should provide yield forecasts directly on Sentinel-2 data. But as you have seen, the error that is remaining in this kind of models at field level is too high for the insurance sector. So we keep sending people on the ground, taking sample and gathering information about the yield data. So what you can see on the map is where we are active currently. And we collected so far 136,000 samples, but collecting 1,000 samples a day currently. So we are on an exponential pattern on the amount of data that we are collecting. The data that we collect is reviewed by the farmer, so it's always signed by the expert who does a crop cut experiment and the farmer, because it's a basis for the claim indemnification. So there is a lot of interest around the yield which is collected. So we do this for insurance company at two different levels. One is the farm level. So when the indemnity is paid based on the crop of the farmer, the yield is established at the farm level. But we also do it at administrative level. And at administrative level, we use an approach which is called a stratified random sampling to optimize where we get the sample from. So we analyze based on remote sensing where we should send experts in a specific region, and then we push this data to a mobile app, and expert can just go on the zones that we define on the mobile app based on the condition of this specific year, and sample, do the crop cut, and enter the data. So this way we can make sure that the data we collect is representative of the area, because it makes a big difference if you collect it in good or bad condition fields. The interesting part is because we push this to a mobile app, this data is available in real time, so we can monitor during the season if something is wrong, if somebody is entering the wrong units, so we can do some quality check on the go, and we can still act based on this quality check. So this is an example of the data we collect. So of course we collect the geolocation, the field boundaries, the crop type. Most of the data is transmitted automatically by the farmer himself. And then the expert goes there and he makes the pictures, it collects a lot of information about crop type, crop stage, sowing date, crop condition, potential and residual yields. So he also checked that the average yield provided by the farmer makes sense based on the condition he sees on the field. And we also collect a lot of information about the losses. So what was the reason of the yield drop, and how much was the yield drop for which causes. So if you have a hail, we would collect this information and the loss, or if it's a drought as well. So we also collect a lot of information on practices like herbicide, pesticide, fungicide application, irrigation, and so on. So of course this sampling approach is very costly. You need to drive a lot in the field, in the area, so it costs a lot of money for the insurance company. So we still think that the way forward is the yield estimation, but we need to fill this gap in the fact that the yield estimation should be closer to the actual yield of the farmer. So from a scientific perspective, R square of 90% and a square error or a mean square error of 10% is encouraging, but in practical for the insurance industry is not enough. We need to move closer to the actual yield. So currently the model we have is similar to what you have seen before. We have a root mean square error of about 10%. So this is why we combine the modeling approach with the in situ data and to provide the final yield of the farmer. So of course the day where we have this kind of yield model at field level available. It will drastically simplify the crop insurance process because we can generate synthetic yield history, so we can calculate the risk more accurately. We are able to detect if there is any error from the experts, and of course we can use this data to automatically pay the farmers. So we still think that yield estimation is the way forward. Yeah. Thank you.
Okay, thank you, Grégoire. And then we can move to the next expert. Sophie, the floor is yours.
Thank you. So my name is Sophie Bontemps. I'm working in the Université Catholique of Louvain in Belgium, university close to Brussels, and I belong to the Earth and Life Institute, so belonging to the research world. So our geomatics lab has diverse expertise with remote sensing, land cover mapping, tropical forest monitoring, biodiversity monitoring, land use modeling, but of course, a key expertise in agriculture using optical Landsat data. Over the last decades, we developed and designed the Sen2Agri, Sen4Cap, and Sen4Stat open source toolboxes for those who already know it. So these are systems that allow generating a lot of EO products relevant for agriculture, maps, metrics for crop growing cycles, agricultural practices monitoring, and now also targeting the yield estimations. We are also, of course, active in Belgium, and we are contributing to GEOGLAM and co-leading the GCAM network. So to carry out all these activities, of course, we need in situ data. And we are working in different ways, a bit like Inbal explained. So when there exists in situ data, and there are a lot, we try first to rely on what is existing and what is collected by national stakeholders. So in Europe, we have been working with the CAP information, so LPIS and Farmers Declaration. But we, in fact, are trying to get as many data as we can, if they are of quality, of course. So this is an example here in South Africa where private companies collect agricultural data using very light aircraft. So with this data, we try to leverage the use of EO data to map and monitor cropland and crop type. And another example, we collaborate with national statistical offices. Here, this is in Spain, where we again use the surveys to map the crop types, and in this case also to improve the statistics in terms of crop type acreage. When we do not find the in-situ data that we need, we also try to carry on our own field campaigns. So this is more for research or demonstration activities, but this is what we are doing also as a university. So I will show two examples, one in Belgium, when we have designed and carried out a field campaign to monitor the grassland intensity. So you can see the transects, so a lot of points that were visited 11 times during the season, and each time looking at how the grassland was managed. And another one in Pakistan, where we had to estimate the wheat acreage in the Sindh province, and then we started from scratch and we developed a new protocol with the Ministry of Agriculture, and we went there to also build capacity and work with the Ministry of Agriculture. So when we have the data, the first thing we do is the quality assessment. I think that this shall be mentioned, that quality assessment is part of the data collection process, because there are a lot of data, but not all of the data can be easily used. And so in terms of quality assessment, there is of course the visual check, but there are a lot of things to do also to automatize the process and make it more efficient. We are also working with stakeholders to adjust their protocols to make the data more compatible with remote sensing data, because of course they are collecting data for their purposes. It doesn't mean that the data are then easy to correlate with remote sensing data. So this is an example in Senegal where we try to adjust the protocol to have information more inside of the parcel and not at the border. When there is no protocol, we try to develop new ones that meet the needs of the different stakeholders, and we are also on that topic focusing more on the yield data collection, because this is really a challenge. And when we are working with existing data sets, we also try to combine different data sets, even if they are not collected for the same purpose. So here, this is an example where we combine data from the NSO and the CAP. So these data, in fact, are collected by two different ministries, but the two ministries are not in contact between themselves. And so this is an example to show the added value of just really making the best use of existing data. The last slide, I will be very quick on that. So getting in situ data, which is EO compatible, even for the crop type and area, remains a bottleneck. So ensuring the quality, a good geographical distribution, georeferencing, avoiding any crop bias, meaning that we need information on even the minor crops, not only the major one. It's something that still needs to be focused on. The yield data, we already mentioned it a lot. And for the sustainability of in situ data collection, of course, we cannot rely only on us. We should work with national stakeholders by working on their practices, building capacity, and having a long-term vision. And so the last but not least, field campaigns shall not be the only solution. We should really take advantage of other means, mobile devices, new technologies, scientific progress, for instance, model transfer and active learning, and promote in situ data sharing, which probably will be easier between scientists than with ministries, but we should at least try. Thank you.
Thank you very much, Sophie. We can applaud. I think it's a good practice, no? Thank you. And now we have Luca, who is working for EFTAS and has been collecting ground truth data for a while. I'll let you the floor, Luca, to explain.
Thank you. Yeah, my name is Luca Kleine-Willinghofer, and I work at EFTAS. And EFTAS is a private service provider specialized on Earth observation and GeoIT services. Our domains are basically agriculture, forestry, environment, landscape, and nature, to name the most important one. And my role there is I'm the coordinator for geostatistics, and I'm project leader and team leader for landscape monitoring. So where have we been involved in data collection? Raphael already said we have been in many projects where we have that task. I have listed some of them. I will not explain all, but I would like to highlight three. The first one is the IX in Germany and some federal states, where we have been since the 90s, collected reference data and also done rapid field visits on the ground to verify farmers' declaration. The second one, you all should have heard it by now, LUCAS, the land use, land cover area frame survey, where we have been involved since the early beginning, more than 20 years ago. And since then, we have been involved in each campaign. In 2022, we have managed 15 countries with our partners and surveyed out of those 4 countries with our own teams. And the last I would like to highlight is EMBA, the European Monitoring for Biodiversity in Agricultural Landscapes, where we have been together with our partner IFAB, designing the field protocol and doing the rollout the first time in the last 2 years on 3,000 sample plots across EU27. Some of you might have visited me the last days. There was a poster on EMBA, but of course you can ask more questions later. How do we use in situ data? We're also an Earth observation company, so we also need to use in situ data and use it, for example, for upscaling from field observation using drones, airborne images up to sentinel data, to, for example, in the Bush Information System project in Namibia, where one of the tasks was to develop a bush encroachment map on farmland. And of course, we also use in situ data for calibration and validation of our own products or of other agricultural monitoring products. For example, we are involved in the IX monitoring in several federal states in Germany, so we validate our own data and calibrate, of course. And a recent project is the validation of the CLMS HRL products, where we, of course, will apply reference data in situ data for validation. We also apply in the field artificial intelligence to classify photos for agricultural monitoring. For example, we have an EFTAS crop analyzer, which allows to analyze crop types based on geotagged landscape photos. And this, of course, increases the efficiency of field survey a lot. Challenges and opportunities. I don't have to repeat that we all need adequate and Earth observation compatible in situ data. This has become quite clear. From our perspective, we see that data collection is not yet always adequately integrated in the project planning. So even in the call for tender. So I refer to the timing, to the purpose, what exactly has to be calculated, and also, of course, to the budget. Then, as a statement here, short-term survey projects entail high logistical challenges. So from our perspective, it would be more efficient if there are in situ data campaigns to roll it out over several years so that you have not such high peaks in the logistics and also more efficient efficiency. A big issue when you survey in the field, especially in agricultural land, is the access to land. So a challenge for us is the cooperation and the acceptance of the farmers of what we do. Usually there is no or an unclear legal framework to collect data, and I refer to Europe here. In Africa it can be quite the opposite, what we have learned. And also access to existing agricultural data is limited, either for the purpose of survey planning or for direct use of the data. Opportunities, of course, are the new technologies which are available for utilizing and making more efficient data collection in the field, but also using already existing data sets. For example, the Lucas landscape photos from the past campaigns. We have analyzed them in how far the crops extend in the cardinal directions, making it thus more compatible for Earth observation applications. Right now, a challenge for us, methodological challenge, is ground truthing, especially of phenological stages and specific agricultural management practices. There's something we need to see how we can improve in that area. And with this last slide, which basically combines what we are doing, I would like to hand over to Steffen.
Okay, thank you. Go ahead, Steffen. The floor is yours.
Thank you very much. It's a great pleasure to be here. So last. Yeah, I'm from the International Institute for Applied Systems Analysis, and we've been doing a lot of work in the last 15 years on in situ data collection and remote sensing, but IASA as such is relatively old. We celebrated last year our 50th anniversary. I think it is important, more important than ever, because it was founded by the former Soviet Union and the US for science diplomacy at that time. We are known as such for the powerhouse for integrated modeling, specifically on mitigation and adaptation scenarios, working on the IPCC. And now since 15 years we are working on Earth observation and in situ data collection. We've had a paper out in 2009 on using crowdsourcing to collect in situ data, and that was really novel that time. It's not so novel anymore because a lot is done now. Citizen science is all over the place, and citizens, as we know, can contribute quite high quality data. We have been involved in many projects. Also, I had a European research grant where we did some testing on the quality of crowdsourced data, the quality of citizen science data, which is really important in this respect to understand what are citizens really good at and for what do you need experts and where do you need experts combined with citizens. And I think this is a very interesting new research field, and there is big potential, and I think there is a lot of unanswered questions still in this field as well. We're also involved in a lot of projects. We are also leading and I'm one of the co-leads together with Hendrik Bogart from Wageningen, the GEOGLAM in situ group, and we are very much welcoming anybody who wants to join that. And as Sven has said, we are really trying to foster making data fair. So there is, I think we need to be very clear. There is a difference between fair and open and publicly accessible data versus what I've heard here many times, exchanging data between scientists. We need to exchange data, we need to have some friends, we need to have some kind of club here. So these are really two different things, and I think we need to decide as a community where we really want to go and if we are serious about free and open data or not. And I think that's still an open question. We're also involved in the world cover, and we are providing a lot of training and reference data in these projects, both on the EU level but also on the ESA side. And we're also involved in the World Serial project. And in the World Serial project, we have been building this reference data collection. Most of the data is open, but we were also asked by ESA to put a private repository for those where we are not allowed to share the data by the provider, though we are trying very hard to open up as much data as we really can. And this is ongoing work. There is now the second phase of World Serial, and we are now making this data cloud optimized, and we are putting it in the OpenEO stack catalog, so that ideally anybody can use this data then and also run the data in some cloud environment. So I think these are the next steps where we need to also go with in situ data to make them cloud optimized and to provide them available in the cloud, that it's not anymore this cumbersome process of downloading. We've also worked a lot on data collection on the ground. So there is this Crop Observe map, app which some of you might have used already, and there is continuous data coming. And the difference, again, I think, of this app with other apps is that the data becomes available. So if you go and collect data with Crop Observe, you can one day later download the data yourself. And I think this is the way, and this Crop Observe app collects not only crop type information, but also the phenological stages, and many times requested damage management activities and so forth. These 2,000 points is quite old. Sorry, this is a bit of an old slide. So there's much more data now available, and I have to stop here, so thanks. Okay, 1 minute, thank you. Let's see if there is something else, yes. We've also looked into using Street View and Mapillary. So Mapillary is really open. So on Mapillary you can do AI, you can do crop detection, and we've built an interface where you can then delineate the field so to make the data Earth observation compatible. Sophie used the right term. Anyway, this is really important that the data then can also then be picked up by remote sensing and by the classifiers. And it's not just a point as, for example, Lucas still has, now it's moving into the Lucas also compatible with observation, but it's a big issue that Lucas could be not compatible with Earth observation, for example. So yeah, we're trying to do those activities. This 1 minute is over. Thank you.
Okay, thank you. And before opening the floor to questions, I just want to point out we have like different views from different organizations. There was one organization that wanted to be here, OGC, talk about in situ and situ data standards, but our speaker, Marie-Françoise Voidreau, couldn't come due to personal reasons, so that's why she's still in the agenda but not in the panel. So I just wanted to point it out. So with that being said, I'd like to thank all the speakers, very nice presentations. And if there are questions, feel free. I see there's a question already there. Where's the question? There.
Thank you for the discussion. I'm Monica Pepe from CNR, and I'm collecting actually a lot of field data. And so I think Stefan pointed out a very key factor, because usually we are paid for field data collection, but we are not for managing them. So there is also the problem of a lack of funding, because one thing is that I have to manage my own data for my own calibration and validation, and one thing is I have to create a structure, and I have to find a way to metadata for traceability and so on. And this is a needs for professionals to do that, and need a lot of time and resources. And some digital supports, for sure, are welcome to help it out. But I think in some projects this is foreseen, in some other it is not. And I think the policy must be that for a real open data perspective, this should be funded as well.
Okay, thank you. It was an excellent point, and indeed, it's not only costly to collect in situ data, but the management, the harmonization, I think it's been mentioned already, is also something that needs quite a lot of effort, and I think that's partially why some of the very good research data ends up somewhere in a drawer in somebody's desk. If there's anyone who wants to react on this statement, Stefan, I think there, you still have a mic somewhere there.
Yeah, I think these are very important points you're raising, and of course it's understandable. A lot of people who work in the field, they work day and night very hard. Many times it's not very well paid. It's not so easy then to do all this work and then to make just the data freely available to everybody. And I think one solution to this, indeed you mentioned it, is that it's very clear in the contract that there is enough money for this data collection, but then the condition is that this data is openly shared as fair data. And this is a good sign also we are getting now from the Commission, from ESA. Increasingly, all contracts now have this clause in there, and this will help a lot to free up data, because it's not anymore a voluntary decision by the researchers, which is very rare. We get this very rare. We have to be just realistic. But if it's in the contract, if it's clear, then it's really going to change. It's really a game changer. And I think by now, this is happening increasingly. Also now for the first time in the Copernicus land, in the CLFM contract we have, all the reference data will become available, the validation as well as the training data. And that's, I think, the way we have to go.
Other comments, remarks on that question?
Yeah, maybe on the framework on how to collect data. So nowadays, mobile apps helps to structure the data straight from the time when we collect it. So there are tools to help loss adjuster or expert in the field to collect AO-ready data straight from the field. So I would say this kind of frameworks exist. And especially now with embedded GPS in the mobile phone, it's really easy to locate on the map and to enter data.
Okay, thank you. Other questions? I think Christophe, and then we go to...
Yeah, okay, so there was a question mark indeed, whether it's the last hurdle or not. I think Imbal already hinted that she may not really agree, so maybe that's a bit the question for the panel members. If it's not the last hurdle, what will be the next one that we need to conquer, let's say?
Go ahead, panel members. Who wants to go first?
Yeah, I don't think it's the last hurdle, but with machine learning techniques that are now available, data is the model, so to speak. So the more data we can collect on the more crops, the better will become the models or the predictive models. So I believe that collecting data is a first step, but to have sufficient data to cover all scenarios, all the cases will take a lot of efforts, especially if we think about the minor crops or specific scenario of extreme drought and so on. But I still believe that the data makes the model nowadays. Yeah, it's a big part of it. But yeah.
Okay, thank you.
I think we should change the title from the last hurdle to the marathon in front of us.
Jose wants to, can you pass the mic?
Yeah, I can speak a bit from the perspective of Copernicus. I mean, in situ in itself is hiding many issues. We are speaking here about the availability of the data, but we also agree that there is already a lot of data, but then is the data available in terms of is restricted, is free and open, then is it EO compatible? In itself is too many. There are several issues there to address. But then, I mean, there are many other aspects that we need to consider. Is that there is an increasing demands of new products as well. Also higher frequencies, in particular when it comes to our portfolio in the Copernicus Land Monitoring Service. And this increases the demand of more in situ data. So it's not that just we will get the data and that's it. We still have to consider that the new products come with their own demands on in situ data. And that's why I think some of the colleagues here have mentioned the importance of planning in situ data as an essential part whenever we start a project. And also this also involves us in taking into consideration the importance of in situ data whenever we plan a new product. What I can also say, in case I don't have more time later, particularly when it comes to Copernicus, the EA is planning now to have a discussion with the different trusted entities to see how we should address these issues up to the point that is possible in the next phase of Copernicus beyond 2027, because we see that there are a number of issues, sustainability of networks, heterogeneity, and data policies, and so on, that we are advancing, but still we need to have a more coherent response from the Copernicus program as a whole as well.
Okay, thank you. Yeah, and now Inbal, you have to go.
All right, I'll just add a quick comment on that. I mean, I think we've got to think about it more holistically. So I absolutely think, I mean, in situ, we all agree is absolutely critical, and I agree with you that it's many different things and many different challenges. But I think if we go out and say, this is the one thing that we need to do, then all of a sudden you see perhaps funding agencies, not necessarily from the remote sensing communities, that think, okay, well now let's just put out a call for in situ data. Well, that's not really, that's a part of it, but much more thinking about the projects, same as, okay, let's have an external part about capacity building. And again, I think we need to think about all these elements that are all a hurdle together as a holistic view in terms of what are our hurdles and how do we bring together ultimately to collect the right data, to make it accessible, the sustainability of it, right? Like you can't just have one campaign. I think you were saying that, like how do you make sure that we're sustaining these kinds of data collections, that they will ultimately continue to inform and improve the products. And I think we also heard this morning, and I think from your requirements, crop type mapping, yield forecasting and estimation are not we're not there, right? Like we're progressing and we've made a lot of progress, but we've got to be honest and careful too, because again, the external communities are like expecting that we have 99% accuracy at the field scale of yield estimates and forecast, right? And so I think we have a lot more work on those parts as well. I'll stop there. Thanks.
Okay, thank you. Yeah, Sophie, go ahead.
Maybe just to continue the discussion on the accuracy, it's also a dream that with more and more in situ data, we will reach very high accuracy in the products, because for land cover mapping, for instance, when you look at the agreement between experts without remote sensing data, you get a lot of disagreement. So there is a kind of accuracy level that I would not say a top of, I would not say a potential, a maximum possible accuracy that is not reachable, but we need also to acknowledge that in situ data, even if they are good quality, will not allow us to reach dream accuracy that are of dream. And this is also the policy role when they call to not ask for accuracy level that are not accessible, because then it will be an endless effort to get better and better in situ data. Even if I fully agree that we are not there yet, even for the crop acreage, the crop type, the yield model, but there is also some reasonable view that we need to get, and that the funders must be aware also.
Yep. Thank you. Very good remark, and I'm totally in agreement with that. The question mark and the title was, as I said, a bit provocative. It's also based on a lot of, let's say, the AI community. There's like push button, and just wanted to see your reaction. AI is sure helpful, and like we said, we can do a lot with it, but it's not the holy grail that we're still looking for, even on crop type mapping and yield estimation. There was a question coming from FAO as well there. So.
Thank you, Julia Conqueda from FAO. A question especially for Sophie. Agricultural survey data remains a sort of an untapped resource of in situ data, and one of the main reasons is often we cannot share the data because of privacy concern. What is your experience on this, on anonymize that information or separate from the more sensible data? Is there a golden standard, a best practice to overcome this constraint?
This is a very good question. A standard, no, definitively no. I would say this is a country by country protocol that we have. To be honest, I never get the request to anonymize the data set. The request was more to be transparent on what we plan to do and what we are doing with the data. And if the data were too sensitive, then they share data from past years. Because I think the sensitivity is related to the timeliness of the data. And when we are doing research, pilot activities, we just want to demonstrate what is feasible to convince. And so for us, we can work with past data. So we never had this kind of request or of difficulty in sharing the data. But yeah, this is really a country by country approach, and I would also say that this is a confidence relationship with the countries. You don't get the data the first time you go. First, you need to talk with them, to show what is feasible, to get a small part of the data, and to convince, and then you will get more and more. But it takes time.
Thank you. So we will take. You want to react very quickly?
Yes, I want to react very quickly. This is a very important thing, this getting trust, not only from the countries, but also from the farmers, from whom we are collecting data. So I think this is a critical point, which is sometimes overseen, so that there should also be the perspective from the farmer side, who are in somehow checked what they are growing on the field, and not only crop types, but also yield and possibly pesticides or insecticides, whatever. So there should also be an acceptance from that side that this research is necessary and that data can be shared. Otherwise, this is a very difficult topic to disclose data which has been collected maybe under the umbrella that it's only for scientific and for a case study, and then goes into the public. So this is a good remark.
Thank you. And I think also to mention that from the European Commission, we are also very much aware of this, and we have the service working on several data sets, like the farm structure survey was mentioned this morning by Marijn, or even the FADN, which is the data that is used to assess the CAP impact, basically, with a lot of data there about yield and so on. And so there is a wish to share this data, and we have exactly this question, or to anonymize them or to aggregate them in a level where you cannot identify specific holding. And so this is a very important question. So we'll take a very, very last question. I'm sorry.
Thank you. This is Belen from University of Valencia. So yeah, definitely, I think we're in good direction. Like both the Commission, European Space Agency, it's asking to publish that data. The problem is, from the user's perspective, it's really hard to go to that particular project and see where the data was hosted and so on. So I think we should advocate for a common system with very standardized formats and very well-known accuracies and so on, so it simplifies our lives. And finally, also, I wanted to remark also the push to ESA, to NASA, to continue these missions. I think we have to continue insisting on data continuity. With Michele, we talked about that. It's very important to continue Sentinel-2, Sentinel-1, even look for higher spatial resolution, like go into the maybe a spatial resolution of planet, but being like big missions funded by the agencies, like special agencies. So I think it's good also to insist on that.
Thank you. So I will let the panel one by one react and conclude this panel. So also by giving a recommendation to the Commission and ESA, because this is, we've heard some recommendations. So if you can be to the point in less than 30 seconds, if possible, really giving the highest priority or priorities. Thank you.
Yeah, Stefan, you have the mic.
Stefan, you can start.
I was going to ask. No, I think you're making a really important suggestion, and I think this is where we have to go. So can we find a system where we can all put the data? I mean, I think the reference data module of World Serial is a starting point. So the technology is there. It's currently, of course, limited to some crops, so it could be expanded. But I think if we can find a way that people do see the benefit, it needs to be also clear what is how can people who contribute be acknowledged? What is in it for them? We have to answer those questions. And what will they get back if they put in some data? So you put in 100 data points and you get back 1,000. What about that? You know, it's a bit like you get more out what you put in. So I'm fantasizing a little bit here, but I think this is the way we have to go. But also I think we have to do something for the farmer. So if we can offer something for the farmer, to provide a service for the farmer, that they know if they put their data somewhere, they are getting something back. And there are different ways we've been thinking of, you know. They get maybe average yield around them, they know more about their other farmers next to them. Then I think we really make progress. And I stop here.
Yeah, thank you.
I would like to emphasize what you have said in terms of continuation of Earth observation missions and data, and I would turn it around and say I emphasize continuation in situ data initiatives, so that there's a continuous collection, things like Lucas, like MBAL, which provide Earth observation compatible data, and I think there's enough knowledge available, enough sampling strategies which could be quite easily to adopt and to implement.
Thank you.
Okay, I will make the link with another topic. So we were talking about data we collect or farmers are collecting. Do not forget the data that are collecting by national stakeholders. Convince them that EO data can be useful for them, and maybe to share the data on one side and also to adjust the protocol to make the use easier for remote sensing applications.
Yeah, I would maybe give an idea that could maybe help. So one direction was to anonymize the data, or yeah, and I think to transform the data in such a way so aggregation or anonymization can help increase the willingness to share the data. So maybe let the data provider build a layer of modeling on top of the data, such that the data product which is shared can be still used for calibration, for modeling, but without sharing the raw data. So a framework that would allow sharing the core information of the data and the structure of the data without sharing the data itself. So maybe it could be one way.
Thank you.
I mean, I think I'll continue to insist on part of all of the story is also the co-development and the equitable sharing and considerations that go into the data that we're collecting and the benefits that are coming out of that. I think the long-term sustainability, we can't say that enough in terms of missions, so we're not doing one-off projects. And building on that, I think we're getting better. We have to do still much, much better at coordinating and collaborating across projects, because there's so many resources that are being wasted. We have a project in Kenya, oh, you have a project in Kenya, you know, and it's like 5 different campaigns instead of really thinking about it. And I think GEOGLAM is moving in that direction, and I think we've got to do a lot more of that, because it's just a mass amount of resources, and instead we could be much more strategic about the data that are needing and being collected within different programs and projects.
Thanks. Quickly, 3 key messages. I think from the Copernicus point of view, I think we need to strive and push for more open in situ data to make sure that the data is available, to ensure that our products are traceable and that there is transparency on how they have been produced, generated, and validated. So we need to strive for that. Then recommendations for the Commission, I think we need to look, I don't think we have mentioned, at the implementation of the Open Data Directive, and particularly the high-value data sets, implementing regulation, which should enter, or will enter into force, let's say, in June this year, although the member states have some derogation possibility for a couple of years. And it includes agricultural parcels there, which need to be provided as free and open data via APIs, machine learning, readable formats, and with metadata. I think we need to look at that, and I think Commission and we need to work on making sure that this is really happening. And finally, I would also ask you to have a look and follow the activity that DG Agri is doing together with JRC on the Ajax data sharing, because I think the idea behind was to really make sure that all this data is available with the metadata and accessible, let's say, in a common entry point. So I think that's something that we can also look forward to it.
Thank you very much. I think we can all applaud the panelists, and really a warm thank you. You are almost on time, so thank you also, Sven, if you want to give the last word.
Thank you, Rafael. No, I think it was a very good panel, very good views. Indeed, I just like what Imbal mentioned on GEOGLAM. There's an in situ data working group where Stefan and Hendrik from Wageningen are co-leads, and we're actually implementing also a system where people can actually upload their data, or at least show where they're collecting data. So what was a lot of effort of people working in the same country, they can actually combine data sets and make sure that some sound sampling can be done in country, so that will reduce some duplication of effort. With that being said, I think there's an interesting next session where two of our panelists will be moderating, so I don't want to steal too much of their time. So with that, once again, thank you all, and we'll continue the discussion.
So just a short message before we start the next session. It was said yesterday evening also, please respect the official hours for the lunch break. So we are not allowed to be at the canteen before 13:45. And if the next session will last until 13:55, it's better also, of course, if you stay in the room until we finish the session. Because we got some complaints from the canteen yesterday. They need that in order to, that everything goes smooth with the other people going before. So please, not before 13:45, and preferably not before the end of the session. Thank you.
So we're the last session between you and lunch, but it also sounds like you're a captive audience because you can't go to lunch before this session is over. So, you know, we'll try to make it as entertaining as possible. We'd like to invite then the panelists for this last panel before lunch to come up and join us here. Or just come for your presentation.
So maybe we can invite, we wait for 1 minute, and then we can invite the first speaker of the presentation. Welcome. Tian Hu, who will introduce us about the European Eco-Stress Hub for Agriculture.
Yep. Please. Okay, thank you. So, sorry for taking the lunch time this last session. Yeah, I try to be on time. So good morning, everyone. My name is Tian Hu from Luxembourg Institute of Science Technology, and today I'm going to introduce our European Eco-Stress Hub project funded by ESA. So the purpose for this project is to provide some support to the agricultural water stress and water use monitoring, and also provide some implications for the future highway solutions, thermal emissions from different space agencies, CNES, NASA, and ESA. So, Okay, first of all, this is a very brief, conceptualization of the ecosystem surface energy balance process. We can see that there are three major components in this process. The first one is net available energy, which is the engine of this process, which drives the water from net surface to the atmosphere. And second one is the water stress, which is the fuel or soil moisture content, because without water content, we cannot have evapotranspiration. And also, this kind of process, they're coupled with GBB. And at the right-hand side, you can see the diagram, the diurnal cycle, two contrasting ecosystems. The first one is a radiation-limited ecosystem, so there's no strong stomachal control. We can see that the blue line and the green line, they are the radiation diurnal cycle and the evapotranspiration diurnal cycle, and are very symmetric. That means the water stress is very weak. But when it comes down to the arid, very dry land, which is a water-limited ecosystem, there's strong coupling between the net surface and the atmosphere, or let's say there's strong stomachal regulation. Now you can see there's very strong asymmetric symptom. That means we need to describe this kind of water stress situation to get accurate estimation of evapotranspiration. So in this situation, in our model or in our project, we try to use net surface temperature to capture this kind of water stress information to drive the surface energy balance process, and also in order to have a better estimate of the evapotranspiration over dry land. So this is a overview of the current thermal missions. We have different missions. For example, geostationary, they have very high revisit frequency, but the spatial resolution is relatively coarse. We also have other missions like polar warped in Sentinel-3 or MODIS. They have relatively high revisit frequency, but with a relatively coarse spatial resolution. So then, that's why we have the future thermal missions. Trishna from CNES in Israel, and SPG from NASA, and also STM from ESA. These future highest resolution thermal missions will provide us, by combining these three missions together, we can expect that by the end of this decade, we have daily revisit and below 100 meter spatial resolution thermal data. And before the launch of these three missions, we have EcoStress launched by NASA. So this mission will serve as a pathfinder for the future three thermal missions. So this is a introduction about our EcoStress, European EcoStress Hub funded by ESA. So we just, last year, in 2022, we concluded our phase 1, EH1. So in this, so for the EH1 is more about science, the model comparison between different LST retrieval algorithm or surface edge balance models. So in EH1, we implement two LST retrieval algorithms. The first one is TS, second one is SW. And for ET, we select three models, STIC, developed at least, and we have TSAB, and we have SABs. So in EH2, we are targeting at generating long time series of EcoStress products, including LST, ET, and GBP. And also we try to estimate daily ET from instantaneous scale, using the newly calibrated collection to EcoStress data. So, overall, we try to provide some, insights or support to the preparation of the future thermal missions. So, all the data of our project, can be found or downloaded on this WASDI platform. So this is the QR code. You can just, scan, or this is the URL. You can also check what could be interesting for you. And so this is okay. This is the LST evaluation in our project, and also the analysis of the LST impact on ET. So we can see that as the upper color, we have two algorithms, SW and TS. They're very consistent with the JPL TS, and also they're very consistent with the state-of-the-art high-resolution thermal missions, including Landsat and ASTA. So this paper is published in RSE. And then we have this kind of analysis in terms of LST impact on ET. So we know that we have different LST retrieval algorithms, but which algorithm we should go for? Have to have no better constraint of the surface energy balance process. So here we select two algorithms. The first one is SW, the second one is TS. So we can see that, for cropland, actually, the accuracy or the RMC for these two algorithms are very similar. Also for grassland, very similar. But because for TS, it's much simpler in terms of the process. Because for SW, we have to estimate MC30, in the first hand. But for TS, we can estimate temperature and MC30 simultaneously. So that's why actually in our EH project we select TS in the end. But we know that for TS algorithm, we have to do the atmospheric correction, so which we need a Motion or RTDOV, this kind of large rate transfer model, and also with the Area 5 atmospheric profiles to drive this kind of atmospheric correction process. But how can we combine this SW and TS algorithm to delimit this kind of, complexity? Then we propose this new algorithm driven by the machine learning algorithm. So we coupling the SW algorithm and TS algorithm through deep neural network in order to avoid atmospheric correction. So this is the advantage of SW. And we try to retrieve temperature and emissivity simultaneously. So this is the advantage of TS. So this is a brief conceptualization of our algorithm. So in the end, we don't have to do atmospheric correction. We don't have to do the retrieval emissivity. So we get temperature and emissivity at the same time. So this is the comparison with the original TS algorithm, or let's say the NASA official LST products. I mean, the first row is the simulation analysis. I mean, we can see that. I mean, the one in the red circle, the red, whatever square, is our algorithm as compared to the other, like two. I mean, this kind of simulation analysis, our algorithm has the best performance. And also the down panel is the site evaluation at 3 sites as provided by Frank Gaucher at KIT. And we can see that also our algorithm is called DL, Deep Learning Stability as algorithm, has the best performance and very consistent as the 3 sites as compared to the, the official TS algorithm. Okay, so this is the ET. I mean, for the ET, as mentioned before, we implement 3 models, STIC, SEPs, and TSEP. I mean, for a STIC model is an analytic model, which means that we don't parameterize the conductances and aerodynamic temperature in the model structure. Rather, we just use this kind of gradient equations and mountain payments, like this kind of equation to estimate the ET. And for SEPs and TSEP, I mean, we have some parameterization. For example, how can we get the aerodynamic temperature from the surface temperature? How can we parameterize the conductance? So they're very different. And also we have relatively different accuracy or performance. So we selected 19 sites in Europe from EFDC and ICOS. And then we can see that for the among these 3 models, the STIC has the highest RMC and bias. And also we calculate the KGE, which is indicator of the closeness between the model and the instruments. And across different sites, as mentioned, 19 sites in total, and have different aridity levels. We can see, when the aridity index is lower, that means it's drier. So we can see that, especially when it comes to the dry land or water control ecosystem, the STIC model has better performance as compared to the other, let's say, SEPs or TSEP, this kind of like a parameterized model. Okay, so this is ET bias analysis. As I mentioned before, when it comes to the dry area, I mean, for all the 3 models, it's very consistent, and the accuracy is much lower as compared to the radiation-controlled ecosystem. I mean, actually, you can see the very consistent trend. But as compared to the SEPs and TSEP model, I mean, our model STIC, I mean, they have they also have large uncertainty over this kind of water-constrained ecosystem, but the uncertainty is relatively lower as compared to the other parameterized model. Okay, so this is the comparison between our EcoStress ET products as compared to the NASA JPL official products. So also at 19 sites over Europe, we can see that, I mean, accuracy, especially RMC, I mean, the upper color is obviously higher as compared to the PGJPL model. And also in this Taylor diagram, our the point is closer to the observation, especially when it comes to the cropland. You can see it because it's an agricultural workshop. I mean, so that's why I highlight a cropland here. So we can see that, I mean, for the PGJPL model, I mean, RMC is around 100 watt per square meter. This is at instantaneous scale. But for our model is around 80, so I mean the improvement is around 20 watts per square meter. The reason, I mean, we suppose or we infer is because of the weak LST constraint in the PGJPL model, because in the PGJPL model they just use VBD or like this kind of radiation control to drive the model, but the LST constraint is relatively weak, so the water stress information cannot be accurately depicted in the model structure. That's why I can see here in the last figure, I mean, actually compare with the PGJPL, I mean, the PGJPL minus STIC, I mean, this is all positive. That means the PGJPL is kind of overestimated. Okay, so this is the application of our EcoStress ET products. So we just calculate the simple like ESI, I mean the effective stress information. It's very, how to say, conventional method. Actually this is another ESA project, is EO Africa Explorer project. And so this is the process. And we calculate this kind of map. We produce the map over Mali. I mean, you can see that because the spatial resolution is very high, so we can see a lot of details. Across the river, and also we can clearly, represent the dry season in July and August. Then we can reflect the wet seasons in September and October. And so this is climatology for the monthly ESI data using our EcoStress ET. And so tomorrow, because the time limitations, I couldn't elaborate on this thing. And tomorrow, my colleague also from Luxembourg, Aolinja, he will expand on this topic. So we try to look at how we can take advantage of the high. This is for temporal resolution, the advantage of temporal resolution of EcoStress. How we can, but tomorrow he will talk about how we can take advantage of the high temporal resolution. Like day and night revisit of the EcoStress data to have a new drought index. Okay, so yeah, I think this is the conclusion and recommendation for my talk. So first of all, our ST algorithm, deep learning SWTS algorithm shows promise in high resolution global ST mapping with better accuracy and enhanced simplicity. And also we can see that the analytical surface elements model exhibit advantage in ET retrieval over parametric ones, especially for models with weak LST constraint. And high resolution thermal observations facilitate accurate agriculture water stress mapping in terms of the high spatial resolution and high temporal resolution advantage. And last one is the advancements in LST and ET models will support in the future high resolution thermal missions from CNES, from NASA, from ESA, and also from other space agencies in all over the globe. So I think that's all for my presentation. Thank you.
Do we have a question from the audience? We have time for one. No question? So we keep it for the end. Thank you.
Okay, thank you so much.
So I'd like to invite my co-host of this session, Sophie Bontemps from UCL Louvain, and she'll be talking about ESA tools for agriculture, Senforstat toolbox for Sentinel EO information, supporting the agricultural statistics and agricultural virtual laboratory for agricultural science.
Thank you, Inbal. So this is my pleasure to be here to introduce you these two tools, and I will start with the Senforstat one. So this is well known that timely and accurate information on food production is really needed to address the food security challenge. And for decades now, remote sensing data is announced like the promising data that will help. But so far, in terms of agricultural statistics, the added value of EO data has not been really demonstrated. And so this is the objective of this Senforstat project, is to provide algorithm and best practices to for agricultural statistics using Earth observation data and to facilitate the uptake of Earth observation data when estimating these statistics. So we also want really to engage the national statistical offices to demonstrate the benefit for them of working with the Earth observation data and to convince them to include it in their operational workflow. So the way we have decided to work is really to work with Sentinel data, agricultural surveys from the national statistical offices. There are the two main inputs of our system. We generate maps, metrics, yield estimation, and we combine again these products with the agricultural surveys to improve the statistics. There are different ways of improving the statistics. It can be, of course, the accuracy of the statistics, but also the disaggregation, the timeliness. We can also support a better sampling frame when they decide the location of the samples in their survey. About the main output of the project is a toolbox, open source toolbox that will allow generating the EO products. So it is illustrated here on the top, but so very shortly, I will not spend a lot of time on that, but very shortly, it is processing Sentinel-1 and Sentinel-2 data, possibly also Landsat 8 and 9 time series. It makes the pre-processing of this data, and then you have different processors that will generate 5 types of products. The first one are cloud-free composites with Sentinel-2, or temporal composites with Sentinel-1, time series of biophysical indices and spectral indices, biophysical variables and spectral indices, sorry. Crop maps, crop type maps at 10 meters, crop growth condition matrix, also with meteorological data, that will feed the crop yield estimation. So this system has been designed to be operational, working at national scale, and so it can be run automatically on the cloud or locally, also manually if you want just to tune the parameters and adjust it to your own context. So a lot of flexibility, and also the system, the last thing to mention is the system is not like a full package. There are different modules, and these modules can be handled separately also. I will now show you 3 examples of collaboration we had and we still have in the project. So the first one is in Spain. So in Spain, we are working with the National Statistical Office, and this NSO is collecting each year data through agricultural survey, which is named ESIRCE. So this is an integrated list and area frame survey. So it means that you get elementary sampling unit, which are these square where you have polygons with crop type information, and also for part of it, yield information. So we have been using this survey to make the crop type map. This is an example in Castilla y León, and then we combine the survey and the map to improve the accuracy of the acreage estimates. So this is an example. This table shows the acreage estimate for the 3 main crops in the region, so wheat, maize, and sunflower. And what you can see, well, there is no pointer. So what you can see is that for each crop, you get 2 lines. The first one is the acreage estimates you get when you are using only the statistical data, so the survey. And the second line is the estimate when you are coupling the survey with the map. So you can see that for the 3 crops, we are more or less the same value in terms of estimate, but what really matters, what is important is to look at the confidence interval. The amplitude is significantly decreased when you combine the map with the statistical survey. And so you really have an advantage of making this map and using it to have a better estimates of your acreage estimate. This was for the area. We have been also working on the yield, even if we are not also advanced for the yield, but basically what we have been doing is that we have been working with data that were included in the database. We have been combining this data with EO and meteo features to develop a model for each crop. So these are 2 examples for the barley and the soft wheat, and the objective is then to apply this model in any pixel of the country. So for the moment, this is not yet been done because we are still in the phase of validating and adjusting the model. I will not go into detail because there is a poster on that topic, poster 30, later today, so I invite you to have a look. Another use case that we did in Spain with the NSO is to improve the granularity of the statistics. So on the left, you can see that we have been able to derive acreage estimate for the barley. This is an example at the municipality level with an error which is acceptable for the NSO. This is not possible if you are only using the survey because you do not have enough samples at the level of the municipality to get this estimate. And the last use case we did in Spain is to work on the generation of an irrigation map because they would like to update their sampling frame. So for the moment, they are allocating the sampling based on all sampling frame, which does not take into account the irrigation situation. The situation is changing and irrigation is becoming very important, and they would like to include this component in the allocation of their sampling units, and so they have been they have asked us to do this kind of irrigation map. There is a presentation on that topic later today. This was for Spain. Senegal now. In Senegal, we have been working with them since 4 years already. The first year we were using the data they were collected as they are. And so we identified some gaps in the data collection. And so with the NSO in Senegal, we really focus on the adjustment of the protocol to improve the quality of the in situ data to make the integration of remote sensing data easier. So I have just highlighted some key components. I will not read all of them, but clearly field boundaries and geographical information, even for non-crop plan information, is key if you want to work with remote sensing data. The second year, we implemented a pilot where this adjusted protocol over one department, and we were really able to demonstrate, so making a crop type map and having accurate estimate for the main crop with an acceptable error for the NSO. And so now we are continuing. So this is a very slow process, but efficient, I think. We are extending the new protocol over more and more departments, and we are also targeting the yield. Last example I would like to show you is in Pakistan, where really the situation is completely different because there was no agricultural survey that included georeferencing. It was only interviews and paper. And so here we really started from scratch. We proposed the Ministry of Agriculture with a new protocol. We designed it and we did the field campaign with them. So we had 2 members of the team going there to supervise and to build capacity. This was in March this year. So you can see the points that were collected during these 2 weeks. And when they came back from that mission, so we were able to do a wheat map, so for the winter wheat, with good accuracy metrics, and more importantly, because the ultimate objective is the statistics, we were able to show that with remote sensing data, we can have a good accurate estimate for the targeted crop type, and again, the confidence interval is clearly reduced when you use the remote sensing data, which is the plot on the right. So my conclusion for Senforstat, clearly the next step I would say, so we are continuing and expanding the system demonstration. You can see the list of countries where we have plans to work. I will not read it. This is of course within the ESA project, but I would like also to mention that we are really supported by also FAO, the World Bank and the Asian Development Bank, who are really working with us to move from the R&D project to an operational activities, and so this is really positive. On our side, we also continue and invest a lot in capacity building with trainings, documentation, webinars, and so on. And of course, the tool will continue to improve because we will, with more demonstration, we will have more feedback and more improvement needed. I will take the last minutes to introduce you to the second tool of the presentation, which is the Agriculture Virtual Laboratory, AVL. So what is AVL? This is an integrated data analysis environment for agricultural science. So the objective is really to facilitate the research in the agricultural community. We want to provide a simple and efficient access to relevant data sets. You can see the list of data that we have included so far. So of course we have satellite data, but we have also in situ data that were collected in previous projects. Third-party data, where we have the support of ESA to facilitate the access to third-party data. And this list is not closed, of course. It can be evolved. Any user that comes to the AVL can also upload his own data set. The idea is really to offer us a platform where you can access the data and also which will foster the collaboration between scientists by sharing not only the data but also the tool. On the right, you have the overview of the architecture of the laboratory. So basically, each user will have his own workspace and can access the data through 3 different components, 2 for the processing and 1 for the visualization. So AVL is not yet available for everybody, so we are still in the development phase. We have started since 2 months now an adoption phase with beta user. So we had an open call late 2023. Users were selected. For instance, we have a lot of GCAM sites working there. And so they will do some experiments with the continuous support of the IT team of AVL. That will allow upgrading again and again the AVL, and in a couple of months, AVL will become open to the whole community. And so you could become an AVL user. This is, of course, the objective. Last slide, recommendations. Coming back to Sen4Stat, crop yield modeling in terms of R&D challenge, or in terms of R&D remains really the main challenge. It was already mentioned a lot. R&D in terms of methodology, modeling methodology, but also in terms of protocol to collect field data. Continue funding from ground data, already mentioned, and to make the link with the panel yesterday, making funding available for pre-operational tools, like Sen4Stat, and allow the scaling up from demo to ready expansion into countries. And for the laboratories or platforms like AVL, I think that the recommendation that is very strong, because we already heard a lot from the users, is to have a long-term vision about these platforms at the beginning of the project, because it is very complicated to motivate the users to come and test the platforms if they don't know if the platform will be there 2 years or 3 years after the project. And so having really this long-term vision will really help in the adoption of the tools. And with that, I thank you for your attention.
Great. Questions for Sophie? Christophe? Oh. Do we have a microphone? Yeah, thank you.
From Sen2Agri to Sen4Stat, there is quite a range of products now, and you've been in the field for a long time. I was wondering if you have any insights into what of these products gains the most traction from end users, and if this is something that changes, or if they always get back to the same kind of products, like just the crop type map.
Good question. I think at the beginning it was really, cropland mapping looks like a very basic product, and you could say maybe the needs has evolved. I would say no, because when you go to practice monitoring, or when you go even to crop growing, having a cropland mask remains very important, because it allows you to focus on the cropland. The same for the crop type, you can be crop specific. So the basic product will remain always useful, and for the more advanced product. So I would say there is no evolution, but even if I would say the ultimate need is not the cropland remain useful, the same for the crop type. Thank you. And I will now pass the floor to my co-chair, Inbal, who will make a presentation about the rapid assessment tool.
Okay, great. So I'm going to talk about a new initiative we're starting around rapid agricultural assessments in support of policies in food security and agriculture. A lot of different partners and collaborators working on this. But I'd like to start with the motivation and why we've started this. We all know that there are more extreme weather events that are having more and more impacts on agricultural productivity, and we know that's going to continue, unfortunately. But we're also seeing a lot of regional conflicts and wars that are also having a very large impact on agricultural production and on food security. And oftentimes, satellite data in many of these situations is the only means we have to have a rapid and a quick assessment of what the implications are for food production and implications for agricultural production overall. And what we found is that we were getting on our side, on the NASA Harvest side, a lot of different requests from different governments, from different organizations, asking us if we could do an assessment of the impact of a drought. And the last one we've just gone is, for example, from the Ministry of Agriculture in Kenya around the impact of the ongoing flooding on crop production. And we also recognized that there wasn't a facility that was focused on the remote sensing side of things that was there and able to always be responsive. There are a lot of course, organizations working in this space. And so that's where this came from. I think one of the challenges, as many of you will know, is when you have a project, you don't have that flexibility of when a request comes in to say, okay, everybody off this project. Now we're going to work on this thing that is not necessarily funded, or even if there is funding, you can't grow and shrink your team very quickly to be able to address those. And so that was the logic for us for starting to think about this, of having a core team that can work on these, building very much on the international community, on the GEOGLAM community, and I'll talk more about that as I go in this presentation, but really from our side to be able to provide this kind of an information service, working very closely with those that are requesting this information. And so what I'd like to do is one, I think this is a big opportunity for the GEOGLAM and for us overall here, overall, to be responsive to these. I think it's a good indication that we're seeing more and more recognition of the value from the policy side of what we can provide and being able to be responsive to those. And so we have termed it RAPS. I'm not sure we're going to still stick to this name, but Rapid Assessments for Policy Support. And we see it largely focusing on 3 areas. One is extreme weather events due to a changing climate, armed conflict and war, and I would say we're getting more and more of actually those requests, and then also decreasing market transparency, in particular in large producers that can have large impacts on agricultural markets and prices. So I'd like to quickly go through some of the examples of the work we have done to give you some framework of what kinds of work have we done, what kind of requests have we received. One of the early ones was still during COVID times, and this was a request from the government of Togo for a loan program they had to smallholder farmers. And one of the information pieces they needed for this program was actually locating smallholder farms and fields. And ultimately, this was one of the information products that we produced a cropland map for them. And this ultimately supported around 60,000 smallholder farmers with interest-free loans. Again, this was one piece of information that went into this, into those decisions. Another one was a request from the U.S. Department of Agriculture. There was a very strong windstorm called a derecho that swept through Iowa, one of the main corn and soy producing states, had a very large impact and damage. And the request was, could we look at the satellite evidence of how much impact was there going to be on, especially on corn and soy? And so we did this analysis with Sentinel-1 data. But what we know from the insurance industry side is that the loss was estimated at around $31 million, and the loss adjustment process took about 4 months. Okay, this analysis was carried out in about 2 weeks. And so again, the implications there in terms of the rapid information that we can provide and the guidance becomes obviously very, very critical. Another request was from USAID, looking at the 5 consecutive droughts in Somalia, the driest condition in over 40 years. And the request was to map the disappearance of water bodies. And of course, in Somalia, these are not only important for croplands, but very much important for livestock. And here we used planet data to map through these 5 seasons, the presence of water, when the last time there was an actual water in a particular water body, and overall then get the full view of water and water loss or gains in some cases, but mostly loss, and that's what you can see here. I think I'll probably skip this example. Johnny gave a very nice presentation about this work with the Ministry of Agriculture and FAO in Malawi. Another more recent one, also for a request by FuseNet, is looking at the impact of the war in Sudan on cultivation. And this is work carried out by Hannah Kerner and her team, and looking here at 2 regions, Al Jazeera and Al Qadif. And ultimately what they have found is that there has in fact been, in these regions, a large decrease in cultivated area relative to 2022. We have a similar request that we're still working on North Kivu. I think there was a poster by Joseph on Monday looking at this work. Again, here, in fact, we haven't seen large-scale abandonment. So again, we've used planet data here to map cropland over 3 years, where the assumption is that there would have been large-scale abandonment. That is not, so far in our initial results, what we have found. Instead, what we have found and corroborated by different reports in looking at some of these regions, and of course here I'm just showing a very zoomed out area, is that a lot of the farmers and ownerships are continuing to farm but now paying rent or paying to landlords of the new folks that have occupied their village, and also some checkpoints where then they are charging taxation on the production of croplands. I'll spend a little bit more time talking about some of the work we've done in Ukraine. Here we had a request from the Ministry of Agriculture. I should say that this builds, and we've talked a lot about building trust and relationships. We've had a very long-term relationship with different institutes in Ukraine, including with the Ministry of Agriculture. And so when the war broke out, they asked us if we could help to run some analysis on what the implications of the war were on production, and I'll go through some of these quite quickly. Initially, we did do a winter crops versus potential spring crop area to get a very quick view of how much area was occupied early on in the war, what the potential implications would be for spring planted crops and for the winter crops that were, of course, planted before the war started. As I think many groups have done, we worked on in-season mapping then, so we were progressively going from winter crops to spring crops, then breaking out the winter cereals versus rapeseed, and then so on and so forth also on the summer crops. We have also created field boundary identification for the last 3 years. We're working on the 2024 one as well. And one of the early questions, of course, was around spring planting, and a lot of the assumption was that, in fact, crops wouldn't be planted. And what we found, and this is in Kherson at the time, was fully occupied. Here we were using Sentinel-1 coherence, but the green were the planted winter crops. The red is the progression of the planting, and in fact, what we saw, and now we're well aware, is that by and large, most fields were indeed continuing to be planted. We then brought together all these different layers to come up with a crop type map. We did random stratification to ultimately come up with our area estimates. But we knew there were 2 other components that were really important. One was the yield, and we used the Belen's model, the ARIA model, for our yield estimates. And then I think there was a presentation yesterday by Shabri, because the concern was a lot of the wheat that had been planted before the war would not be able to be harvested. And so it was very important for us not only to make estimates of planted area, but also make the estimates of the harvested area and what proportion of that planted would be harvested. And indeed what we found is that by and large the wheat was harvested except for right along the front line. And so at the time it was, while most expectations were for a large decrease in productivity from Ukraine, in fact, that wasn't the case. But what was the case is, of course, a big proportion of their production, around 22% of wheat, around 14 or 13% of sunflower, was being harvested in occupied territories. And the ministry told us that they did use that information in part to inform a decision not to put export bans in 2022, which of course has very large implications. Another piece that they asked us to look at is, of course, abandoned land and what are the implications, especially around the front line. And here we're looking at a climate image from July 26, so towards the end of the end of the growing season for wheat, peak of the growing season for a lot of the summer crops. And we don't see anything, right, in this image. 2022, we start to see a band of where the crops are not being harvested. In 2023, we see this interesting pattern that we also saw earlier this morning, is this large green band. And what that is abandoned land. And initially, we were surprised by that. But of course, if you're going to abandon land, this is some of the most fertile land in the world. And there are seeds and there's rain, of course it's going to grow. And so instead what we see is a signal of the winter crops greening up, this area greening up when the winter crops are greening up, but then they stay green throughout the entire summer season. And so when we map that, in fact, this is what we see in terms of the abandoned land. We have overlaid a layer of Russian fortifications. This is not our layer, we didn't produce that, but that seems to outline very well actually where the abandoned land are, which of course makes a lot of sense. We can see the area that was liberated by Ukraine, right? So we see that front line that moved very quickly. When you zoom in, you can actually see the 2014, that says 2024, it's the 2014 front line as well of the initial invasion. And we estimate this is around 7% of Ukraine's total cropland. We worked with the ministry to estimate the value of that, right? So we took the national prices, which are lower than international market prices for the various crops. We looked at the mixture of what was planted along the front line as well, and the yield estimates together to look at overall what the cost was of that mix of crops. And we also translated it, making some assumptions based on WFP numbers of how much that quantity of grain, how many people that could have actually fed. And that our estimate was around 25 million people. Okay, so very significant, in fact. The other requests that we've had from the ministry around the Kakhovka Dam, we've heard earlier on this, they initially wanted us to look at, they were very worried that a lot of the agricultural lands had been flooded. In fact, it was a very small proportion. Of course, we know that the large implications were in villages and cities, a lot of contamination, but also large implications for irrigation, and I think we've heard that before, and Sheila had a poster on this, looking at the impact of irrigation. This is a highly irrigated area, semi-arid area in Ukraine, and if you compare the 2021 to 2023, this is Kherson in the occupied side, there's practically no more irrigation. And so this has had a large impact, I think largely for the Ministry of Agriculture. They have been using this, and we're now working with FAO and the State Statistical Service to look at, and I think very much in line with what Sophie has presented, on how do they change their statistical framework to integrate remote sensing, both technically and also in a legal framework, to start to use the satellite data for the ministry's assessments. And so to conclude, I think we've seen a tremendous increase in demand for these kinds of rapid assessments. I think that's a very good sign in terms of both our science and our capabilities are moving, and also our communication and the awareness of those end users that could use this are there to ask for these kinds of analysis and information. And I think that the time is right from our community to start to think about how do we build on that, how do we work together, how do we leverage each other's resources to be able to be responsive. And so we're not saying, no, we can't do that analysis. We can do that analysis. And in fact, it can provide information. And we've also got to be, I think, something that's very challenging on when the request for information can often be fairly quick. We like to do to get to the uncertainties, to bring the accuracies down as low as possible. The decision makers, and a lot of times the policymakers, need to make decisions, and they're going to make them anyways. And so the question of how can we be honest and straightforward about what the uncertainties are, what do we know, and at the same time provide that information so until we continue to improve as the season is progressing, or that we can still be providing information, but being very straight about what that information is actually saying, so that this can help to support decisions. And so I think I'll stop there, and thank you very much.
Thank you, Inbal. Any question for Inbal? Yes?
I fully agree, and I wonder if you already have any idea of how this long-standing, how this collaboration could shape up in the framework of GEOGLAM, and how the different organizations could contribute, and what type of operational model you see for that, if you have that.
Yeah, so we are now seeking, the way we view this is that we would like to try to secure funding to seed start this, right? So that there is a core team, and then there's a large network that you can go to, or vice versa for request, right? Like FAO has come to us with requests, different organizations. And I think that if we're able to get that core funding to start this, then this in the future can actually be self-sustaining, because oftentimes our problem is, we're always chasing kind of 3-year funding, 4-year funding. But the idea is that eventually if an agency says, okay, I need this and it's 150K for 4 months, that covers that, but you have that flexibility in the facility to be able to do that. And I think we see this as kind of a facility that then has a lot of a network. So if they're working in Bangladesh and there's a company or an organization that has expertise there, then that's who you would go to for, the flood map, right? So like different components of that, how do you bring that together?
Thank you. Thank you again. Good. And we welcome now the next speaker, who is Christophe, who will present the World Cereal project and product.
Thank you. So I have the pleasure to tell you a bit about achievements of the ESA-funded World Cereal Project from phase 1, but also the current plans and what we've done already so far in phase 2. It's a big team effort. It's a lot of names here, but let's dive into it. So phase 1 lasted for 3 years, and it was really a scientific feasibility study to map seasonal crops from the local to the global scale. Now in phase 2, we really want to operationalize it and also really build a crop mapping community that can use a fully open and cloud-based flexible crop mapping system. So back to the basics, most of you know that already, but how to map crops from space. You of course need to start from ground data, and then you can extract your training data, your satellite information, train your model, and finally do inference and produce a map. But usually in that first step, we've heard it already often, this is already the biggest challenge. That's why a lot of the effort, and Stefan already nicely introduced that, so I shouldn't spend too much time. We really spent a lot of time in this gathering of data sets that are out there, but we need to explore this first, then collect it, curate it, harmonize it, standardize it, and make it available to the community in a fair way. So this reference data module, that's really something that that has gained traction already, and we hope already that this can be continued in the future. We use that. We really build upon this for the World Serial Project, but it also just should be used outside it. It should live on its own and help you also in your crop mapping projects. Then it's a seasonal product, so obviously we also need to know what the seasons are, and this was already quite a difficult challenge to tackle. So Balance team worked very hard on that and created crop calendars globally on wheat and maize seasons. In some regions, like near the equator, this is really a messy thing to do. But in the first phase, they already came up with these global crop calendars. It's also published, and based on these global crop calendars, they created agroecological zones that have a processing unit for which we produce world cereal products that have a specific season for that region. So these are the products that were released. This is the base product, so crop, no crop. Together with FAO, we decided on the temporary crop extent definition because everyone sees cropland as something different. Within temporary crops, we have seasonal active cropland, seasonal crop types for maize and cereals. Let's say maize, wheat, barley, and rye together. And then we also had seasonal irrigation in phase 1. With most of the products, we also deliver confidence maps that should give you already a bit of insight in how confident our models are to produce a crop type map in some region. So this data is there, globally available. The World Serial Viewer tries to help you also understand how seasonality works. But if you just want to use the data, the products themselves, they are on Zenodo to be downloaded. They are available as assets on Google Earth Engine, and you can also download them through the OpenEO platform. So now we entered in the beginning of this year into phase 2 to bring this into operations, and we really want now to refactor the whole system, which was quite a complicated thing, into something user-friendly and fully cloud-based. We will also expand the default product suite to 11 crop types. We also want to have a customizable crop type model training and application. And we also want to demonstrate a yield module that needs to be added to the system. This is not something that we'll do globally, but more as a demonstrator. And then finally, really important also is building capacity, so towards really an increased adoption of the system, that it doesn't just sit there until it dies. So we really want the community also to get to know this. So towards a cloud-based crop mapping system, we use OpenEO as a standardized processing backbone, and the default cloud on which it operates is the Copernicus data space ecosystem. So this really takes away all the installation burden and all the hassle that you need to do with getting data and pre-processing it. So OpenEO just loads your data, pre-processes it, does a feature extraction, model inference, and then you just get your final World Serial product out of it. It is high performance, it allows scalable processing, and it's also to be onboarded in the network of resources so that you can just apply for some funding from ESA network of resources, and once granted, you can get that product processed for free. As a backup, we will have also a standalone system, but we don't really advertise for that because we really believe that a cloud-based system should, in most cases, be the way to go. We also need to update the crop calendars because, of course, from 2 to 11 crops, we cannot have a single season for each single crop. So we decided now to identify 2 dominant crop seasons in every region and map all of the crops to 1 or 2 of these seasons. And with that, we also will redefine the agroecological zones. And instead of only relying on the crop calendars, we will start from the administrative boundaries so that the downstream products also are more intuitive to the end users. The classification approach, that's also something that is very exciting that we are updating. For this, we are collaborating with the NASA Harvest team who released Presto. This is a foundation model that really works specifically on time series data for remote sensing applications. It's a lightweight transformers. It's really meant to be upscalable for global applications. And so we are testing this method and we really get exciting results. We are already comparing this to the baseline, which were the phase 1 algorithms that we had. And we see that the spatial and also temporal generalizability of the method that we are now developing is much better. You see like a reduction of the well, just to say that if you take out a country and you want to train your algorithms without having seen that country to see how your algorithm performs in a completely unseen region, then we see that with Presto now, we get twice as good performance as that we had before. So this is really an exciting thing. We want to work with that self-supervised framework to have it pre-trained, to expose it as a feature extractor and not as a final end-to-end classification, so that on top of that we can still have our gradient boost, pixel-based cat boost method on top of it, because it's fast to train, it's fast to run. So this really allows to harvest what is trained in a self-supervised way, and then you as a user can really retrain or have your own your algorithm trained on top of that, which doesn't require any GPU or so on. So with that custom model training, we will have a system that will allow you to generate default world serial products for a custom year and AOI. For this, you just need to set a bounding box and choose a year. Then we will allow you also to combine public reference data with private reference data that only you have access to train custom models building upon the pre-trained Presto, and then apply that custom model to any year and AOI and whatever growing season that you want to define. Just as a sneak peek, so the upcoming V1 system will not have a full UI yet. It will first just be through a guided Jupyter notebook, but really to show the simplicity, we want just to have a functionality that allows you to connect with one command to the cloud, to the Copernicus data space ecosystem with OpenEO, define your processing range, your AOI, then you define the processing graph in OpenEO. If you use the default crop, no crop model, it's just there. You create a job, you wait for the result, and there is the result in a cloud-optimized GeoTIFF for you to download. And then, I should also say version 1 of the system will focus on inference using the default models. And then in version 2 for next year, we will allow to support custom model training and inference as well. So we focus quite a bit on capacity building activities, different learning formats to serve a diverse audience, from promotional package all the way up to technical trainings. And then finally, some recommendations. Specifically for this sessions, I think, and we also heard that already, that we need some more R&D on generalization through space and time. We learned that the hard way through World Serial Phase 1. We're now with Presto investigating that for Phase 2. But we really need to generalize or look into generalization of the methods that we expose in community support tools, because once we make them available to the community, they will start using it. And if it's not generalizable, then whatever comes out of that is not really of high quality, probably. We also need to see that already in the R&D projects, we have some upscaling requirements so that we don't develop fancy, nice methods which are very heavy and will cost maybe 2 to 3 million to produce globally. So this is really a requirement that we need to pay attention to. Then we heard that already as well, long-term continuity on harmonized and curated reference data repositories with easy and open access. Once World Serial is done, that reference data module is there. If we by then haven't found a solution to host it and to keep it alive, then it will die, just as so many initiatives already have died. So we really need to look into that. And then the emphasis should be on validated operational workflows. So we as a community have come up already with really, really good crop type mapping algorithms, but they never, or they hardly get into operations that really people can start using. So this is something that we really also need to pay attention to, so that your algorithms also really get used into operational workflows. And then in general, we heard that as well already, more emphasis on in-season mapping. There's been quite some work already going on, but in-season mapping really only works when you don't rely on reference data. And I think that there is still quite a lot to be done to go from the prototypes that are now there already to something that is operational. Maybe in the end, something like World Serial could also support in-season mapping, but we are really not there yet operationally. So still quite some things to be done. Finally, if you want to know a bit more, there is some information on a poster from Italo on the new crop calendars. So if you have any feedback or want to go into discussion, that's your opportunity. And then also on the reference data, we have a poster there. So see you at 6 p.m. And I'll stop there.
Thank you, Christophe. We have time for one question. Sven.
Yeah, Christophe, thanks for the presentation. Well, two questions. One, both on in-situ data. Could you elaborate a bit more on the quality? Because I know that there's lots of in-situ data coming from different projects, different research, and so how the difference in quality of the data was handled in World Serial, and if there's a new approach in phase 2. And second question is there already any new in-situ data coming in second phase?
So on that first one, if you upload, or if you are about to upload your own private data sets to the reference data module, nobody else will have access to it, but then it's also your responsibility. There is no quality control whatsoever. If you decide to make it publicly available, or at least in a restricted way so that the World Serial models can be trained on it, but people cannot download it, then a World Serial moderator will look at that data set and also do some sort of a curation. That is visual inspections on a stratified sample of the data set that you upload to see whether there is no obvious mistakes there. We also have an automated approach that intersects it with things like OpenStreetMap to see if there's no road intersections going through polygons and stuff. But then other than that, there's just that much you can do. There's no way from an in-situ point. We have to believe if someone uploads a point and says that it's a winter wheat, that it's not going to be a maze. We try to be a bit resilient in our algorithms to obvious noise in the in-situ data, but it remains a bit of a challenge. And the second question, that's an ongoing exercise. It still is quite difficult to convince people to contribute data. We now have already 75 million harmonized points in the reference data module, and we do have quite a few leads. But what we are now also putting much more emphasis on is, and we heard it already during the panel, I think from Stefan, that we want to incentivize potential data owners. So we are looking into, together with Cloudflare, CDSE, to offer, for example, free processing credits to create World Serial products if they contribute reference data to the reference data module. We need to give them something back, so we're looking into that, and we hope that that will help to stimulate people to upload some data.
Thank you very much. And maybe I'll just add that we use the World Serials as our baseline cropland extent in the analysis that I showed for Ukraine. And I think in terms of a rapid response, another is the World Serial Phase 2 actually has integrated into it, I think, the activation about 6 different rapid response where they can provide the input layers as the crop type maps into any response that comes. And I think, you know, the more we can have different agencies thinking in that way, I think will help us get there as well. Thanks very much, Christophe. We have 2 presentations left. We've been notified we have to leave this room at 2:45. So I'd like to invite Roberto Carrillo, leveraging EO data for environment, government, and business applications for agriculture, introducing the EO for EU platform.
So hello. Unfortunately, I'm not
Claudio. Sorry about that. Sophie's whispering to me.
Yeah, he's a cool guy. I would like to be like him, but no, I'm Claudio. And I'm a cloud computing analyst at the European Center for Medium Range Weather Forecast. And my presentation will introduce the EO for EU platform. The work that I am presenting is indeed the result of the effort of a consortium which comprises 16 partners from 11 countries, led by the University of Athens and funded by the European Union. As pointed out already in this workshop, we face currently some challenges to exploit EO data. We have diverse sources of information, different APIs, different access methods for different data repositories, and difficulties to find and retrieve the relevant data, lack of metadata on the datasets, or a standardized way to express metadata. This results in data fragmentation and in a lack of tools to download and process EO data. To address these challenges, our project, EO for EU, is developing an advanced platform leveraging machine learning, cloud computing, and high-performance computing. More specifically, the EO for EU platform allows for searching, discovering, processing, and analyzing EO data, and is based on a series of innovative technologies which allow to access EO data from different sources for example, Copernicus, Galileo, ECMWF. Leverage a knowledge graph, machine learning techniques, and intuitive user interfaces, including extended reality. We are working to make the EO4U platform available to the public before the end of this month, so stay tuned. This is a preview of the EO4U dashboard. You can see that we feature a knowledge graph, a workflow editor, a file explorer, and extended reality, virtual reality interfaces. Underneath, we operate the platform on two clouds, namely the Wikio and Shineka clouds. We bridge the two clouds to move the computation closer to the data, and we rely on state-of-the-art cloud computing paradigms. The platform provides also to users programmatic interfaces such as a CLI, APIs, including the OpenAO API, and so on. The key results that we expect are an integrated EO data ecosystem, semantic enhanced knowledge graphs, data fusion techniques, dynamic semantic annotation, and learned compression, augmented extended reality, and data analytics visualizations. And we are targeting a wide range of users, which covers the whole spectrum from researchers and developers to simple citizens. So we have researchers and academia, policymakers, EO data providers, the private sector, citizens and scientists, and finally, standards development organizations. The project leverages 7 use cases to demonstrate the use of the EO4EU platform. We are targeting personalized healthcare, ocean monitoring, food security, forest ecosystems, soil erosion, environmental pests, and civil protection. More information on the use cases is available on the EO4EU website. For the sake of time, in this presentation, we will focus only on 3 use cases, which we think are relevant to this workshop. So the goal of the food security use case is to analyze the impacts of climate change on agricultural crops, and in particular, to estimate the risk of yield loss over time. The target crop is industrial tomato. And we employed AG ERA5 reanalysis climate data. We identified adverse climate conditions to the crop yield, leveraging the normalized different vegetation index, or NDVI. Initial results from this use case show that the industrial tomato so far has not been affected by climate change on all fronts, and it may expand its geographical range in the future. And for more information, I recommend attending the poster 2 session of this workshop later at 6 p.m. We talk now about another EO4U use case, which is the forest ecosystem. The goal is to create a digital twin of forest and non-forest areas at national level. We leverage machine learning, in situ data, and EO data through the EO4EU platform. Use case results are expected to be available in the following months. But for more information in the meantime, I recommend visiting the EO4EU website. And another use case is soil erosion. This use case aims at producing an updated cutting-edge service for the evaluation of soil erosion induced by water. Through the EO4EU platform, we leverage and combine satellite data, artificial intelligence techniques, and empirical approaches. And we are just currently collecting and preparing data for this use case. We are also expecting results in the following months for this use case. And once again, please, if you are interested, have a look at the website. In general, I recommend subscribing to the EO4EU newsletter to be among the first to get access to the EO4EU platform and to be updated on the project activities and results. And finally, as requested by the workshop organizers, we provide some recommendations. That is that metadata should be ideally defined and be accessible for all the provided EO data. Currently, not all services have the same level of metadata quality. To the same, it would be nice to have semantic annotation, allowing advanced search and optimized data access and retrieval. Another recommendation would be to tackle standardized means of accessing and retrieving EO data. Typically, each service follows different access means. Okay. This is all from my side. Thank you very much, and thank you for hosting me. Perhaps I was a bit fast, but I think it's good at this time.
So we have time for one quick question. Yes, please. Can we have a mic? Here.
Thank you. Thanks. Sorry, I was curious. How did you map the distribution of tomato?
Okay, so as the slide says, I'm a cloud computing analyst, so I'm really on the AT part. But if you can attend the postal session at 6 p.m., you can ask my colleagues which will present.
Okay, so we will move to the last speaker with online, yes, remote speaker. So we welcome Jerzy Bochanowski from Cloud4. I don't know if he's connected, because it's, yeah, he is. So welcome, Jerzy, and the floor is yours to talk about the Copernicus data center ecosystem.
Thank you very much. Can you confirm that you can see my presentation and hear me well?
Perfect, both.
Okay, perfect. Okay. So good afternoon, everyone. I'm very happy that I can share with you this presentation. I had to cancel my trip to Rome in the last moment. So I will be talking about the Copernicus data space ecosystem, which was mentioned today and the previous days as well. And I will give you my hints why I think it should be the place where you can do the agriculture monitoring and a broader understanding on the large scales. So I represent a company called Cloud4. However, the Copernicus data space ecosystem, it's work of the big consortiums led by the systems. So until I speak in general about the ecosystem, I represent our whole big team working on this big project. So to start, I just want to say, for those that are not fully aware of what the Copernicus data ecosystem is, looking at for the aspects which are mostly relevant for agriculture monitoring. So the first thing is that it's the main reference access point to Copernicus data, meaning Sentinel imageries. So that's the best place where you can get the data up to date. So the second point, important point, is that it's a big change before the ecosystems, that now you can access all archive of Sentinel data immediately available, free and open. So you don't need to order it, you don't need to request everything. If it's there, it's currently more than 70 petabytes of data, and we expect to be much more than 100 petabytes in the coming years. It also depends on the new satellite systems data which will be added to the ecosystem. You can also get used to this ecosystem because it's a long-term project, at least until the end of 2028, but with a potential extension up to 2032. And the ecosystem is not only data, but it's the most important part of it, but it's also about various access interfaces, the ways you can handle the data, which are maybe not all new, but it's the first time that they are all together in one ecosystem attached to this huge repository of satellite data. What is also important is that in parallel, like next to the public data space where you can get all the data, and also you can get some pre-configured quotas for using the services for free. You can also easily switch to the commercial offerings, which are next in the ecosystem. And CryoDias was the first and one of the services, but this list will grow. CryoDias, you might know, is from the previous times where there were a few diases where you could commercially access and process the Sentinel data. And why it's so easy is just because the identity is federated, so you can have the same user to access both systems, and the data offering is exactly the same, and the access interfaces, like all the APIs, are also the same. So you can really easily switch between the two services, which I think it's crucial when you build some prototypes of services or analysis, and you know that you need to scale up, and then you need to use this commercial service. I think okay. So why should you use this ecosystem for agriculture monitoring in the sense of, various analysis? The whole conference is about this. So in like a broader sense. So first of all, is this data immediately available? So I'm not going to the details, because for the Sentinel data, you can just assume that everything is there, and the full spatial and temporal coverage. And also, if there are some reprocessing campaigns of ESA data, you all have there. There are just few examples of the data you need to order, which is, for example, level 0 of Sentinel-1. Otherwise, and on the full archive, otherwise everything is there. And of course, it's like I guess all the Sentinel data are used in agriculture monitoring, apart from Sentinel-1, Sentinel-2, which is obvious, but also Sentinel-3 for, I don't know, evapotranspiration or some global ski analysis, or even Sentinel-5P for emissions from agriculture and so on. But what is also important, that you have some of the Copernicus services data also available there. You would have to look into our documentation and data offer to see exactly which data sets are operationally prolonged. And also there are various complementary data sets, but apart from maybe the ones that would be more for some research oriented studies, like the old data like Envisat Maris or SMOS for soil moisture. We have also EcoStress data available. We also have Landsat data for European coverage, but there are plans in the near future to add the whole Landsat repository also to the CDSC. So you will have of Sentinel-2 and Landsat data to create some joint data sets. As you can see, the amount of data you can have there is huge, because there are like 40 petabytes of Sentinel-2 or 30 petabytes of Sentinel-1, and you can also see that like we have 100% of data which was actually acquired. So you can be sure that the data is there. But as I said, data is one thing, but the second thing are the tools and services that they are available attached to the data somehow. So I'm not going to the details here, but you have Copernicus browser, which is a graphical user interface where you can greatly search, access, and visualize, and do some basic analysis or create your indices, and so on in the graphical way. But you can have also the APIs to access to the data with the OData and Stack catalog and S3 API. For Stack, I can tell you that there is the one which is already available, which is with a limited usage because of no assets added, but there is a plan in the couple of weeks to publish the new Stack catalog in the development phase, but really the full catalog. You have Sentinel Hub and OpenEO API, OpenEO, which was also mentioned in this session and before, for the streamlined data access and serverless processing, which is like the main advantage of having all this data in an online form. So this would never be possible before without this approach. You have also the Jupyter Lab if you do want to do some prototyping directly in the browser, and which is also important, of course, that you can rent the infrastructure, so the virtual machines with various GPU or CPU. You can build clusters using Kubernetes, and importantly, everything is attached to the whole Earth observation repository. Which leads me to the conclusion, like so there are big differences. You can process the data at the moment, so you don't need to download the data. You don't need to use the predefined tiles as it was before. You can really search for data of area of your interest. This is also possible thanks to the cloud optimized data formats. So you can really limit your queries to the area you want to analyze. You can, and what is also super important, that if you work on even on a smaller scale, if you want to scale to the larger scale, it's just a matter of optimization probably, and money for the commercial offer, but there is no like technical difficulties that you can really need to switch to a new cloud or new system. And to show you one simple use case, so we had in Cloudflare, we had like a small project also from agriculture monitoring, and they were like popular aspects there. One of those was, of course, crop type classification as a starting point for many other analyses. And what I want to show you here only, as we implemented in the CDSC, it's a system that is based on LPIS, and actually uploading the vector files just triggers the whole system, which then works automatically. And for Sentinel-2 time series for 12 months, like from autumn to autumn, it was for Poland, so the season, like winter season, starts in autumn. Generating the field-specific zonal statistics for various indices, including cloud masking and interpolation, gap filling, smoothing, and so on. And building from this the PostGIS database for the whole Poland for 42 crop types and around 10 million parcels. Takes 14 hours, or like a decent size of machine, which costs around 20 euros in terms of just usage. So when you compare it to the legacy way that you would download the data, extract the fields, boundaries, calculate statistics, that's like, this you cannot compare. And then we use the graded recurrence units as deep learning methods to classify crops on the field scale. And the training took around 20 hours. And when we switched to GPU without even big optimization, it was 4 times faster. So you can see, like in less than 2 days, you can have crop classification at country scale, at field scale also. I mean, not pixel-based, and build this kind of map. We also extended that we have like a full crop probability distribution for each crop to make it more robust for various users, which was also a bit more processing power. The cost was a bit higher, but then you can really adapt to the user needs depending if it's a cap monitoring or you search for certain crops and so on. Although it's not my intention here to show you the results of crop classification, it's just to show you that the results were like comparable to what's in the market, so that the estimates of time of processing is true. So we had this kappa of around 0.9 with all the classifications along the season with the F1 score you can see here. So I mean, when we compare to other classifications that are in the market and published, or to other services like Sen4Cap or Sen4Stat, it seems it looks like similar. Not going to details. And with this probability, the idea is just to, as you see on this higher figure, the idea is that you can really increase the accuracy of the classification by selecting a smaller part of fields where you want to provide this classification. So it means that if you say that I'm interested only in probabilities are above 50%, it means that you will lose 5% of all the fields, but your kappa will not be 0.9, but your kappa will be more than 0.96 or something like this. And of course, it should be crop specific, so that's why there are these two low images for spring wheat, which is difficult to classify, and maize, which is easy to classify, as we all know. So to finish, so the Copernicus data space ecosystem provides you with all Copernicus satellite Sentinel data immediately available online, that you can use the API-based server-side processing in various ways. You can rent the infrastructure as a service, and you can build your systems there, and you can easily switch between this public side and commercial offering, because that's smooth, and you can scale up as needed with almost no limitations. And this is what the Copernicus data space ecosystem offers. And with that, I thank you for your attention.
We are up on time, but we will allow for one quick question. Everybody here is very hungry. Okay, well, with that, we'll wrap up, and thanks to all the presenters for this session. I think a lot of interesting and various applications, systems, projects, programs. So thank you, everybody.
Thank you.
on, but now it's, yeah. Okay. Hello, good afternoon. Thank you. We can start this session, so please take your seats. We are now starting the session on water resources intelligence, so please. And introduce ourselves, the co-chairs. I'm Livia Peiser, Land and Water Division in FAO, and I've been working on this topic through the Vapor project that was presented yesterday morning, but also through some posters that are also here today, one poster in particular. So, and yeah, co-chair.
Yeah, I'm Jacopo Dari from the University of Perugia. Don't want to spoiler on what I'm working on because I have a presentation during the session. So let's keep it for later. Before starting, just a communication from the organizing committee. The daily highlights are available on the website for each day. So for who wants to check, please go to the website, to the dedicated section.
So with that, I think we can start with the first presentation. So please, Chiara Corbari from the Politecnico di Milano. And it's already there, yes.
Okay. Thank you and good afternoon to everyone. Today I'm going to present you some monitoring and forecasting of irrigation water use by assimilating satellite data of land surface temperature and soil moisture into an energy water balance model. These are parts of the results of the ESA Africa project called AfriSmart. So, as I said, the idea here is to map the irrigation water volumes that we obtain using satellite soil moisture and land surface temperature data into an energy water balance model to be able to map at daily scale with the resolution of 30 meters these irrigation water volumes. And the area of study is a region in Morocco where they are facing several problems of water scarcity. They had a lot of several droughts period in the last years, which are also projected to further increase. So the problem is very relevant in this area. And in addition to the decreased water availability due to climate change, there are also a lot of issues related to inaccurate water management in these areas. But in contrast, in the last years, they observed an increase in the requests of water demand, especially for agriculture, but also due to civil and also industrial growth. And what is interesting in this irrigation district area, which is called Ducale Irrigation Area, the irrigation consortium, the ORMVAD consortium, was not able to provide irrigation water starting from the mid of 2020 to the farmers due to the complete lack of water available for irrigation. Going to the methodology, here we use the physically based hydrological model, which is called FAST-EWB model. Actually combines the water and the energy balance equation in an entire system. They are linked to evapotranspiration. And this model is not using as input the satellite land surface temperature, but is computing it, solving the energy balance equation. So that's why we are able to assimilate the land surface temperature. And I will show you in a minute how. So first we did a calibration of the model in periods where there was no irrigation and in areas which were not irrigated. And then we applied the 3 different irrigation strategies to try to understand the irrigated volume. So we applied the well-known FAO approach based on soil moisture thresholds, so that you apply water when you reach a certain threshold, which is characteristic of each crop and soil. So you obtain like a kind of optimal irrigation volume. And then we applied 2 simulation strategies on soil moisture using the downscale SMAP and Sentinel-1 product. And we updated and computed the irrigation volume into the model through the water balance equation, so considering all the hydrological processes to obtain a simulated soil moisture from the model, which is not considering the irrigation as input data, compared to the soil moisture from satellite, which should see the irrigation effect. And in a similar way, we did it for downscale and Sentinel-3 land surface temperature data to compute, that we used to compute in a residual way the evapotranspiration flux, which was then compared and assimilated into the hydrological model. So, and of course, we consider all the different irrigation systems that were provided by the irrigation agency. So first of all, we had to analyze and detect really where the irrigation happened. We had the irrigated areas provided directly from the irrigation agency. And you can see here the evolution of the vegetation fraction and its standard deviation from Sentinel-2. And what is interesting to know is that we know that starting from the end of 2020, they stopped providing irrigation, and we can see that the irrigated area, the first year, were still quite diffused. Instead, starting from 2022 and also from 2023, there was a strong decrease in the cultivated and irrigated areas. And so as I was saying, we first calibrated the model. This is a comparison with the land surface temperature, so that you see here the 2 approaches, the one that are not using, of course, that is not assimilated land surface temperature. We calibrated the output from the model of land surface temperature against the Sentinel-3 and the Landsat data, and you can see some results of the validation where the model was quite good, able to reproduce the observed data. And similarly, we compare then the output also of the model that is not using soil moisture as assimilation variable, so the FAO approach and the LST assimilation approach with the observed soil moisture dataset. You see here for the 4 main sub-districts of the Ducale irrigation area, and what you can see here is that especially during December to April, the evolution is quite in accordance, while starting the beginning of the summer season from May to July, August, there are some discrepancies considering both models. And probably we think that this is due to the low spatial resolution probably from the original SMAP dataset in respect especially to the field dimension in this specific area, which are quite very small fields, that also during summer the area is very dry, so if it is not irrigated, there is a strong contrast between the irrigated and cultivated areas and all the surrounding area. And what is also interesting here to see, these are the correlation maps. You can see that the results are quite good. I mean, there are positive correlations, but as you can see on the west part, there are lower correlations values, as there we have the oceans, so probably you will also have some issues with the soil moisture retrieval. And finally, before computing the irrigation volume, we also compare all the 3 configuration of the model with other two products of evapotranspiration, like the mode product and the vapor product, which are considering irrigation in a different way. And we can see that there is a quite good correlation and the errors during the years between the FEVB approach considering the FAO irrigation strategy and the assimilation of LST, while in the assimilation of soil moisture we see that especially during the summer period you have very low values of evapotranspiration. And this of course is visible also if you look at the entire area for these correlation maps. There is quite similar agreement between the two models and the two irrigation approaches, while the soil moisture one has lower correlation values. So with all these results, of course, we were able to follow the evolution of all the processes of the water balance, of the agricultural water balance through all the seasons. And of course, we were able to observe the clear differences in between the different years. And this analysis comes from, for example, the FAO approach, but if we compare the two approaches, in this case the FAO one and the assimilation of LST, you see that we have some differences, especially during the the summer irrigation season. And this is, and we will see why we think we obtained this. And this is, of course, reflected then if we now look and see the results in terms of irrigation volumes. These are aggregated or for the 4 irrigation districts. And you can see that in yellow we have the observed water allocation from the irrigation consortium. And you can see that in 2017, 18, and 19, both two approaches are quite in agreement. Instead, you see a strong decrease and in the last, especially 2 years, but of course in 2021 and 2022, the irrigation consortium didn't provide any irrigation water. So we observed that there was some irrigation, and the irrigation consortium told us that really the farmers had some private wells, so they really irrigated. And actually, what probably if in 2022, as it was a very dry year,
wrap up?
Yes, we have 2 slides, so very quickly. In 2022, as it was a very dry year, but we know that the irrigated areas were strongly decreased. Of course, also the irrigation volumes were less. And the last slide is that now if we add the comparison with the assimilation of soil moisture approach, as we have seen that we had a very low correlation, and the model was not able in this configuration to detect the changes in irrigation and also the satellite due to this, the problem of the spatial resolution that we have seen, but also the number of images that were actually available in these areas. We have seen these great, quite consistent differences. And very last slide, this is visible then also if you look distributed in space, not only in time, according to the different areas. Of course, you see differences according to how they are distributing the water and the real volumes that they use. And I think that with this I can conclude. Thanks.
Thank you, Chiara. We have time for one quick question, if any. Yes. Seems not.
Maybe I can
okay,
just take the opportunity, because
yes,
we are also one of the requests of the workshop organizer is to come up with recommendations for research and development activities. So what would be your recommendation for ESA or the community here?
Yeah, I mean, probably you're looking at this plot, the frequency of satellite data of both LST and then soil moisture would be the most important point. Yes.
Thanks. Okay, thanks again, Chiara.
Thanks.
So now we move to the next speaker, which is Boris Norgard, with a talk on irrigation mapping through Sentinel-2 images.
So thank you, and hello everyone. So I'm really pleased to have the opportunity to present our work that we did at UC Louvain to map irrigation in Spain using Sentinel-2. So to give a little bit of context, I work on the Sen4Stat project, which was already introduced this morning, so I won't delve too much into the details of the project, but as a small reminder, the aim of the project is to create a toolbox which ingests Sentinel-1 and Sentinel-2 time series in conjunction with agricultural surveys from users or from national statistical offices to create a series of products including spectral indices time series, biophysical variables time series, and crop type maps in order to improve agricultural statistics. Now, during the first phase of the project, pilot countries were contacted, and along with their national statistical offices, in order to design use cases that were tailor-made for these national statistical offices. And so I won't delve too much into all those use cases, but the one in particular that is interesting is the improvement of the sampling design, which was concrete requests from Spain. And so the Spanish National Statistical Office has a specific request to be able to update their sampling frame, which was quite outdated. And so to do so, they had a request that concerned irrigation, which became more and more important for them. And so they wanted to obtain an irrigation map in order to improve their stratification in their sampling design and better allocate their samples. And so here you have a visualization of the ESIRSTE dataset, which is the dataset that they produce yearly. Now, of course, irrigation mapping is also important for a whole series of other reasons. It's a great decision-making tool, and it's becoming more and more important in the context of agricultural pressure on water use. But for us, the main incentive was these specific requests from the NSO. So this, if we have a look at the dataset that we received, it's called ESIRSE, and it's composed of approximately 500,000 polygons, which are contained in squared elementary sampling units or segments of 49 hectares, sampled in an area and lease frame. And so you have here on the right an example of two such segments. And so obviously this is a really high quality data set, especially since every polygon contains a series of attributes, including the crop type and the presence or absence of irrigation on the parcel if the polygon is located on arable land. Now the question was, how do we link irrigation with in-situ data and Earth observation? And so we needed to account for the fact that different crop types had really different behaviors in terms of season, as much in terms of timing, so winter crops and summer crops, as in terms of phenological characteristics, but also taking into account the fact that irrigation can happen in multiple ways. So of course, irrigating an olive grove with drop irrigation would be completely different than irrigating wheat or barley using pivot irrigation. Now, to highlight this, here are the distributions of NDVI values obtained at different dates for 3 different crops. And this highlights the fact that creating one single irrigation model that would be able to distinguish irrigated from non-irrigated pixels without prior information would be completely impossible. So for example, you have the sunflower and barley NDVI distributions with the rain-fed values in blue and rainfed values in orange and irrigated values in blue. And you see that the distributions are kind of inverted. And so the irrigated pixels in June are higher for the sunflower, which is a summer crop, than for barley, which obviously grows earlier in the season. Now, another difficulty that's added in this differentiating of irrigation is that the peak of the cycle is also different. So the NDVI value you'll get for wheat will be probably higher than for a whole series of other crops. And so it becomes quite obvious that creating one single model without accounting for crop types would be close to impossible using Sentinel-2. So the initial solution that was designed to tackle this was to create one model for each crop type. So this worked quite well at the scale of Andalusia, but it was already quite intensive in terms of computing time. It was completely impossible to scale up. And so what we did was to include the crop type of each training pixel as a categorical feature in the model, meaning that we could obtain one model that could take the crop type into account and then try to distinguish between irrigated and non-irrigated pixel with this prior information. Now, of course, for training, we can use the data that we received from the NSO, so the ESRC dataset, but we need to obtain an exhaustive map at national scale, and so to do this, we used another high-quality dataset that is produced yearly in the context of the Common Agricultural Policy, which is the land parcel identification system, which allows us to obtain the delineation of each parcel in the country along with the crop that is declared by the farmer, meaning that we can train our model with prior knowledge using the NSO dataset and apply it on the LPIS datasets and obtain a 10-meter resolution irrigation map at national scale in Spain. So the architecture of the model is the following one. So the Sentinel-2 time series are pre-processed entirely by the Send4Stat system. So all the cloud masking and gap filling of the time series is taken care of by the system, as well as the spectral indices time series and biophysical variables. On top of that, we computed a set of metrics for which we expect irrigation to stand out. So for example, the date of the peak of the season or the amplitude of the peak of the season. And so when linking the satellite imagery with the in situ that we received from the NSO, we use a CAD boost model, which was already mentioned in other presentations, but which is essentially a gradient boosting model that accepts categorical features as input without prior preprocessing. And then we can apply this model to the land parcel identification system and obtain this exhaustive map. So 25% of the polygons were kept for validation purposes. But of course, since we give the information to the model about the crop type that is located under pixels, we cannot just look at the overall class C or the F-score of the model when looking at the differentiation between rain-fed and irrigated pixels, since we expect the model to be almost perfect for crops that are always irrigated or always non-irrigated. And so what we did was to look at the accuracy metrics by crop type. And so here the F-score is shown in blue along with the proportion of irrigation for each crop type. And they are sorted by crop prevalence. And so the most important ones in this context are barley, wheat, and olive graphs. And so the really good news is that the F-scores that are obtained for these crops are more than promising, even though they would be the crops for which we would expect to have difficulties to differentiate between irrigated and rain-fed pixels. For olive crops, because the irrigation is not as intensive as for cereals, and for barley and wheat, because the irrigation takes place for winter crops, and so there is not so much contrast as for summer crops. And so something I want to stress out that maybe I did not explain is that the model, we expect the model to work because it will detect a response in terms of phenology between irrigated and rain-fed crops at specific dates. Now, we have a map that is of good quality and in situ data that are sampled in a statistically valid way. And so the next step, which is still ongoing work, would be to try to derive irrigation acreage statistics. And so here, for example, you see the map in 3 autonomous communities, or a zoom in 3 autonomous communities, which are Andalusia, Castilla y León, and Aragon.
Could you please wrap up?
Yes. And so with these, we can try to unbias acreage estimation and obtain statistics at varying level of granularities. And so to conclude, this will be linked to the recommendations that I have for the R&D activities. I think it's really important to leverage the high quality in situ data set that we collect in Europe, especially since it allows us to do such kinds of processes. And so, of course, what comes with it is the harmonization of all these data sets that are collected to be able to use them as a scientific community. And I'll leave it to this. Thank you very much.
I think we can take one question from the audience. If there's any.
But so at the end, you made the dedicated area map for which? For 1 year or for a period?
Yes, so this is for 2020. And it's.
But in principle, you can get for every year?
In principle, you can get it for every year.
Okay, thank you. So it's now the time for my co-chair, Jacopo Dari, who presents on monitoring irrigation dynamics from space, achieve results and next step forwards.
Thanks. So, good afternoon again. Yes, the title of my presentation is Monitoring Irrigation Dynamics from Space, Achieve the Results and Next Step Forwards. And actually, what we did so far can be summarized into a kind of evolutionary step that we will see in one slide. But first, I would like to talk shortly about the importance in irrigation in hydrological studies, being I am an hydrologist, so focused on water resources. Well, we all know how much we as human beings are putting pressure on the water cycle. And among human activities, irrigation is the most impactful one, accounting for more than 70% of global freshwater consumption. But despite this, we actually know nothing about where irrigation actually occurs, when, and moreover, how much water is used for irrigation. These two are the key questions that led us to the development of the evolution path that I mentioned you previously, that can be somehow summarized in this way. Here, only milestones are actually reported. And everything can be summarized by the development of an irrigation mapping method, which is called CMAP, and of an irrigation quantification approach, the soil moisture-based inversion approach, that are actually the topic of this presentation. Before going into details, I would like to highlight that this path is some milestones of this path actually are ESA projects that were essential for the development of this path. Irrigation Plus and 4D Med Hydrology, in which we developed the first ever high-resolution datasets of irrigation water use. Then we have another project running now, CCI anthropogenic water use, that is looking at the climate perspective. But again, these steps were essential to develop our methodologies. So first, the CMAP method, which stands for Temporal Stability Derived Irrigation Mapping Method. It's a methodology that we originally developed with soil moisture, satellite soil moisture as input information, and that exploits the temporal stability concept for irrigation mapping. The core idea is very simple, is that during the irrigation season, if a satellite soil moisture product is able to detect irrigation, we expect higher values over irrigated areas, of course, with respect to the rain-fed areas. So how did we try to translate this simple information into some statistical feature? Thanks to the temporal stability theory that was originally developed for another reason, to optimize actually in situ monitoring, but that relies on a couple of statistical indices that are at the basis of our analysis. If we consider the soil moisture value recorded at a certain pixel during a certain observation day, we can compute the relative difference expressing how much that value differs from the spatial mean of that day. And then the temporal anomaly, which is well known and quantifies the discrepancy of that value with respect to the temporal mean. Well, we use these two statistical indices as an input to a k-means clustering algorithm because we know that irrigated areas are characterized by higher values of these two statistical indices, while rain-fed areas by lower values. So we feed the k-means clustering algorithm with this information, and we are able to classify irrigated areas and not irrigated areas. We developed at the beginning, as I said, this method with satellite soil moisture at different resolution in a couple of studies. But recently, in order to show the flexibility of the method that can be actually applied with any variable that can be used as a proxy of irrigation, like for instance NDVI, we carried out an exercise with NDVI from the Copernicus Land Monitoring Service over the Ebro Basin in Spain. And you can see in the bottom of these slides, there are the maps for the seasons 2015 to 2020, the average, relative difference, and temporal anomalies. And you can see that there is an agreement of patterns of higher values of both indices, and the same happens for the reddish areas. That is where these indices are lower. By using these maps to force the k-means clustering algorithm, we produced this irrigation map for the seasons 2015-2020, where rain-fed areas are represented in brown and irrigated areas in green, that we have compared with an in situ data set, and we achieved an overall accuracy of more than 90% on a local scale in the red box, which is an area that we know pretty well, and for which we have a very detailed data set to validate, and of 75% on the Wool Basin scale. Now moving to the quantification of irrigation, we have the soil moisture-based inversion approach that basically relies on the inversion of the soil-water balance for estimating the water entering into the soil. That of agricultural areas is expected to be rainfall plus irrigation. So we implement this simple equation that is actually the soil-water balance, and we invert it. So we write the soil moisture variation in time equal to irrigation plus precipitation, the input, minus drainage, surface runoff, and evapotranspiration. We write each term of the balance as a function of the soil moisture, and we estimate the total amount of water entering into the soil. We remove rainfall from this amount of water, and we obtain as a residual irrigation. Within the Irrigation Plus project, with this method, we developed the first ever regional scale high-resolution irrigation products. We have two products over European basins, Ebro in Spain and Po Valley in Italy, relying on RT1 Sentinel-1 soil moisture from TUVN at 1 kilometer resolution, We have a first version covering 2016-2020, later on extended up to 2021 in another ESA project for the MED. For the product over the Po Basin, I also invite you to check the poster from my colleague Dr. Liaquat later on this afternoon. We have also another product over the Murray-Darling Basin. Here we are in Australia. Period is 2017 to 2020, 6 kilometer spatial resolution, because this one relies on signal soil moisture produced by Spire. All these datasets are available in Zenodo, freely available for further validation from the community, because we validated them a bit. We had 4 pilot districts over the Ebro, a couple of districts over the Po Valley, and 5 districts over the Murray-Darling Basin, Australia. And these are some metrics, root mean square error, correlation, and bias. But of course, further validation from the communities is highly encouraged. Next step, and some, let's say, collateral activities. We have extended within the 4D MED project our estimates over 2 more basins in the Mediterranean area, Yero Basin and Megerda, France and Tunisia, respectively. These datasets are not available so far because we are trying to somehow validate them with some in situ information, which is not so easy to collect. And last update on this kind of activities, as an exercise, we implemented the method in an operational way with operational data, Sentinel-1 from Copernicus, and evaporation and rainfall, the other 2 required inputs from ERA5 land. And as a proof of concept, we applied the method in the area that was fed by in Ukraine by the dam that collapsed last June. And what we observed, if we look at the violins plot in the bottom of the slide, it's a reduction up to 60% of irrigation volumes of season 2023 with respect to the average of the past seasons. So basically, this operational implementation of our method is able to catch some socio-political dynamics occurring there. Final slide with recommendation. I have a couple of recommendations that concern main issues in this research line. First one is the spatial and temporal mismatch between satellite products and irrigation dynamics. That is a problem if we want to monitor irrigation. And in this case, the continuity of current missions or future missions can surely help. And probably the main one is the lack of in situ data, which is the main driver of this research line, because since we don't have data, we try to estimate from satellite, okay? But we need some reference data for calibrating and validating. So a support through research projects that foster the construction of reliable in situ datasets will be helpful. And that's all from my side.
Thank you. Is there any question from the audience? No? Okay, then maybe I can ask you, so what's the next, you're now focusing on the Mediterranean and Australia, but what's the future operational?
Yeah, surely the plan is the extension in space to try to cover as many areas as possible. Very next step is Europe. We are trying to extend to whole agricultural areas of Europe our irrigation estimates. So switching to the presentation of the next speaker, just a moment. It's now time for the talk from Michael Engel on multi-resolution analysis-based assessment of agricultural effects on groundwater levels.
Hello. So, as you've already heard, the soil moisture index is corresponding to the irrigation requirements of some areas. And what we can see here, I think here's the point, huh? to the southeast, you see that the southeast area is kind of more reddish than the northwest area. And if we did some research, and it's in north of Germany, precisely it's Lower Saxony here, and here it's Sachsen-Anhalt, and here's the Uelzen, and the share of irrigated area is 60 to 75%. And however, the need for irrigation will even increase. I think we all can agree on that. But where does the water come from? Actually from the ground. But from the groundwater levels do not have a strong lobby. So we in the Cumodus project, we try to assess the effect of agriculture on the groundwater levels, actually in the northern part of Germany. So what did we do? For that purpose, my colleagues from the Federal Institute for Geosciences and Natural Resources were trained and tested the so-called neural hierarchical interpolation for time series forecasting by Chalu et al. We already discussed it at some conference. So what we need to know is we have a forward model, and that forward model is fed with the characteristics of all monitoring wells across Germany. Not all, but many monitoring wells across Germany. So it's already been trained. As an input, we have multiple features, namely 22, which are written on here. I hope you can read it. But in any case, we think if you understand it, you have an input period of 25 weeks, 52 weeks, and 16 weeks prediction period. So, as a proxy of agriculture, we use the leaf area index and the land cover. But now we have a forward model, and the question is, can we get more out of a model than just the prediction of our groundwater levels? And yes, by feature attribution. But for the purpose of feature attribution, we have to define on the first stage what we want to analyze actually. And it looks a bit theoretical, but actually the only thing you have to remember from that slide is you define what you analyze. And it's really crucial, because the function f, oh, now I don't have a pointer. The function f is depending on the model by a distance vector, and it could be some mean squared error, it could be some mean absolute error, or it could be the sum of all variables or the sum of specific variables. And if you define that, you could do both. You can do optimization, or you train your model, or you do, as in our case, feature attribution. But let's start with the easiest thing. We sum everything up. What comes out? Yesterday, we already heard about Shep values. We did something very similar for Shapley value sampling as by Capdom AI. And we did it for a subset of 20 monitoring wells. It sounds not too much, but actually we did it for 500 samples, so 500 permutations for 22 features. And we only assess the total attribution. So everything's positive here, actually. So what we see here, the most important variables are precipitation, temperature, and groundwater levels. And our weak proxies for groundwater, for agriculture are leaf area index and the land cover. They are existing somehow, but they are not too strong, and we don't know what they do actually. So can we get more out of our data and our regression models? And I would say yes, but we have to reconsider our setup. So as I mentioned, we have a model with some input and some nice colored patches for the agriculture proxies, and it returns some time series. We already seen the standard feature attribution denoted by the black lines here. So you take the whole bunch of this, and you take some kind of gradient, and you make an assumption about the input features. But what if I take that line and draw it next to each other again and again and again and again, such that I can compute kind of the feature attribution for each timestamp? That would be per prediction horizon, so per week. If I predict for week 1, for week 2, how important are the variables? The next idea is, I have now vertical lines, but I want to have horizontal lines. So I split up the signal into these parts. So, and these are, you know, maybe Fourier decomposition or Wavelet decomposition, and we decompose the output of a model or our data, depending on the function we choose, into the frequency parts. As you can see here, we have a lower frequency and a higher, and here the highest frequency. Then, we do exactly the same as for here, but for each frequency part separately. So, to sum up, we have a standard per prediction horizon and per prediction frequency, and finally, we also thought about regional clustering per NUTS-free region. So, what did we get? Actually, we got quite some interesting results. The first thing you should see is that the importance on the mean, which is denoted by the red line, increases with the prediction horizon, which is actually quite interesting because if you have a look at the groundwater levels, it decreases. So the input is the observation of the groundwater level up to the date of prediction, so date and then 16-week predicting groundwater level, and it's decreasing, which means that the amount of prediction, kind of, is increasing with the prediction horizon. So I read it out. The farther away from the last observation, the feature importance increases, so do our weak agriculture proxies, so leaf area index and land cover, but the last observation itself becomes less relevant. So far, so good to our vertical lines. What about our horizontal lines? So recall the frequency parts here, and each number on the x-axis corresponds to a frequency, to one time series here. And namely, the first one is the one with the highest frequency because it's the decomposition level, so not the frequency itself. But like this, it's harder to interpret and it's not so easy as the figure before. So we normalize them again, and we normalize each line such that the maximum is 1. And what we can see here now is pretty interesting because we definitely see some dynamic for our variables or features within the frequency space. And we can say here the 4 is corresponding to the mean value of a time series. And we see that the precipitation is, of course, important for that, but it's also important at the highest frequency. But our leaf area index is getting only, it's here, that's not very significant, but here you see it's increasing, so it's more relevant for on a long-term period. So it's kind of damping, one could say. And here we also see something interesting for the land cover that on the high frequency, and it has a drop, and it's important for the low frequencies or the mean again. But still, let me emphasize, it's very hard to interpret these figures. And it also has something to do with that the monitoring wells, we do not know from every well in which depth it is and what exactly the characteristics are. So it would be good to have more data on this. So if we then we could think of assessing, so we don't have the data, but we could think if we don't have the data, the depth of the monitoring wells, we might cluster by the results of these analyses. So, but these are future ideas. So, but what to the NUTS-free regions? At the beginning we thought it would be easier to interpret, but we figured out it's even less easy. We wanted to attribute or find a similar pattern from the left to the right, but as you can see, we didn't so far. Here we actually, I want to emphasize that we used all measurement sites per NUTS-free region now, not only for the standard feature distribution. And so it's very hard to interpret because the groundwater bodies do not align with the NUTS-free region and stuff like that. So it's hard to assess the effect of agriculture on the groundwater levels. But we are pretty confident that if we strengthen our proxies for the agriculture, we might come up with better results. And what means strengthening the proxies for agriculture? Our idea is that we, for example, do crop classification. We do a time series of the leaf area index in raster format. So currently we did some time series and we aggregated it, but we want to implement it as a raster format. So then we have to bring them to our original model again. And it's because we want to apply gradient-based methods, we have to ensure that the computational graph is not broken. That we will do by the FlexMod. And then, in the end, we can do our analysis again.
Can you please wrap up?
Yeah. So, to the last slide. That's really on time. We developed a framework for multi-resolution analysis-based feature attribution. We showed that by these techniques, we can actually reveal previously hidden importance patterns. And we will further expand our methodology, especially regarding the strength of our agricultural proxies, which is kind of the heart of the matter of the next months and years, maybe, but let's see. And we would really like to see ESA and EC campaigning for spatial explainability projects, and especially enable people to use geospatial cloud computing in this context, because these types of analysis really ask for computational power. Thank you very much. We are very open for discussion, so please reach out if you want.
So is there any question? 2 questions. So first.
Hello, thanks you for this nice presentation. Just a question about your input data sets. You have mentioned that you have incorporated 22 input variables.
Yeah.
So how you decided it, I mean like these 22, and did you also apply some sensitivity analysis, like which variable have more influence on your target variables? Did you consider it?
What do you mean, which variable?
I mean like the 22 input that you have incorporated.
Yeah, actually we feature attribution is kind of a sensitivity analysis. Okay, now it takes a very long time. Might you jump to this second slide?
Yes, that's the second one where you have mentioned that, okay, you have incorporated the 22 input.
Yeah, so that study is this. So we put into all features we actually thought which could be useful, but not too much, such that we are computationally able to deal with it. And now we started to analyze which features are relevant actually, and that's what we do actually, yeah. So you're right, it's the way to go.
Thank you.
Like this, yes, okay. No, probably it's a very ignorant question, but isn't there any irrigation from surface water in Germany?
There is, of course.
But wouldn't that then be, shouldn't you put that in take that also into consideration? You have rain that's explaining a lot, but then probably surface water irrigation will also explain quite a bit, no?
Yeah, actually it's a really good question, and it's precisely what we want to figure out. So by these methods, we want to assess, and actually we want to have multiple studies in areas where we know we have irrigation, like for example in northeast of Lower Saxony. In other areas we know which are rain-fed or, for example, surface-fed parcels. And then we want to show, okay, in that area we can attribute something from the groundwater levels decrease or increase, let's hope it's increase, to the agriculture or not. And if we can show that in this area we can and in that area we cannot, and we know the ground truth, we know, okay, we validated ourselves and we're happy. So it's actually precisely what we want to do.
Thank you. I think we should now move to the next speaker. So the next speaker is Corné van der Sande from ELIF, who will be showing some results on water stress monitoring in Tensift Basin in Morocco again.
Yes, thank you, Livia. Yeah, we go back to Morocco. I present on behalf of ELIF and my colleagues at Racing, our partner company in Marrakesh, Morocco. there's been a lot of science, presentation, scientific approaches. Now we go for a more application because the numbers are quite depressing and that calls for action. And to give you an overview of Morocco, the statistics of 2023, well, they really reflect that Morocco is one of the most affected countries of the drought in the Mediterranean basin. The rainfall dropped to 43 millimeters, an average that's 150. And the average rise in temperature is already above the Paris Agreement of 1.5 degrees, so 1.8. And what you also see, there's less snow melt from the Atlas mountain areas and the Rif. So that results in dams that are being empty, as you can see on the lower right. So the water per inhabitant is really dropping from 600 cubic meters with the average, the long-term average of 2,500 cubic meters. And of course, everybody knows that agriculture is using the most amount of water, 14 billion cubic meters, and drinking water is 1.7. What happens is that there's an over-exploitation of water resources, and that mostly comes from declining groundwater. There are, however, some measures, and to give you an idea on what the government is doing, it's like the king in Morocco, he has his speech every year, and in 2022 he urged for the need to launch more ambitious initiatives and projects through the use of innovations and new technologies in field of water saving. And they set up a government plan called the Strategy Generation Green, is that they want to modernize all irrigation schemes with drip irrigation, ban subsidies on certain crops that are water intensive, and very important for us to digitize agriculture. One last action from the government is that the Minister of Water said in February this year that 80% of the wells are illegal. And he announced to meter them all in this a newspaper item. However, there is no effective means for monitoring agricultural water consumption. What we can, however, quantify water consumption with evapotranspiration and biomass. We can monitor the trends of water and biomass, water consumption and biomass development. We are using FAO's open WAPOR database, I think well known to you all, at various scales, decadal data, ranging from basin to field level. And as you may know, eLeaf is producing this kind of data for FAO. We have our own factory for that, and much of our factory is actually open. Our model is open, so everybody could reproduce. But we have a factory, and that is able to manage a lot of inputs and produce data after the decade is finished and the inputs have gathered within 3 days. And nowadays we are on continuous development on speed and quality checks, and that will even increase the latency. Of course, we offer the data also to commercial clients. One note, we are happy with open data because it enables the use of this kind of data. So going to Tensive Basin in Marrakesh, the Marrakesh region, we are working with Racing, and they are our local partner, and they are specialized in water resources management and agricultural development. And what we have done, we have developed a tool, which I will show you in a bit, in co-creation with our clients, which is the water board or the basin agency and the irrigation office. And what we discovered during well, some ongoing projects that were partially they were done from 2022 onwards, the user needs are centered along planning and monitoring of water resources. They want to go into law enforcement, and they want to work on the assessment of the interventions that they do. And these interventions are the conversion to drip irrigation, for example. On the latter two, I will show you some examples later. So what we developed is the water consumption dashboard, which is an easy-to-use tool that shows the trends on evapotranspiration, biomass, and precipitation. and it's made in business intelligence software tooling, which makes it easy to use because everything is downscaled to maps, graphs, and tables, and so you do not need any prior GIS experience. This BI tooling that we use is commercial and also partially open. We can combine it with client data, but because it's light, we offer the possibility to make our products easily accessible, but also to let the customer take it up into their own system. We have been doing quite some projects, and we started now a demonstration phase, and that's needed because it takes a lot of time to adapt these kind of data in daily operations. So what we aim for now until 2025 is to upgrade the TRL level of 5, which is the prototype, to a tool that is ready to scale. I now show an example, and if I click again, it should start the animation. So for directing the water police, we can zoom into a sector and see the overview of all the parcels, which shows the water consumption in red higher than in green. We can adjust the time slider, and for all the parcels, we can see the ranking. There are also, in blue, there are some observed values that are the total volumes of water consumption and precipitation. Oh, if we zoom into a parcel, we can see actually if there are authorized bore wells. We have got these from the irrigation office. Also see the water storage ponds, and we can even change the water allocation that's been given to the farmers, and have some settings on irrigation efficiency and rainfall efficacy. And then we can actually see the water consumption and see if it's actually conforming, if they're obeying actually the water allocation they got. Could also be not the case, and that way we can actually pinpoint and plan a visit using Google Maps. Another example that I want to show you is the assessment of a conversion to drip irrigation. There have been several projects carried out in Morocco, financed by the World Bank, to modernize the irrigation schemes. And we've been asked to do an impact study using remote sensing. And what I show you now is the example of a scheme of which from 2012 to 2016, the conversion took place with a water station, pressurized pipes, and drip irrigation at plots that for farmers that have applied for this modernization. If you look at this assessment, this irrigation scheme with drip irrigation got operational starting in March 2018, so later than was planned. And what we did is we analyzed the period from 2009 till 2022. This is an example at block level. You see in different colors, brown, green, and yellow, the parcels that have been modernized. Yes, is in green and partially in yellow. And no, the parcels are in brown, and these are not modernized. These are traditional olive fields. What we have learned is that looking at these data, and also knowing that there was a halt in water supplies from the dam because it was not giving water anymore to agriculture, we could observe some trends. And then I can see over here, you can see the change in water consumption with -4 and a change in precipitation with -12%. We also see an increase of the water productivity with 6.7%. But we have to be careful in drawing conclusion because the period of analysis after conversion is rather limited. And as well, the drought period was becoming more intense in Morocco. We also observed other things, is that farmers are coping with drought And at parcel level, we can see that the cultivated area has dropped. So in 2018, in the season of 18-19...
Please wrap up.
Yes. Most of the parcels, all parcels were cultivated, but on the right you can see that this has been diminishing. And you can also see which parcels have been using, in the images on the below, which parcels are using water, and these are serviced by groundwater, of course. So if I come to recommendations, these should be R&D related, but I rather put them to operational, because that's needed. So I would say as a first recommendation, take into account the long time it takes to adopt digital services at water authorities. And as you can see what we're doing now, we did a feasibility study and a prototyping, and now we're in a demonstration phase. It takes a long time. Fund projects, so with a local partner. And the partner knows the local ecosystem of universities and companies and institutes that can enable. And third, that's like support the community in uptake of digital services. It's like we are happy with the open access data as in WAPOR. And what we have seen is that our products are being used. You've seen quite some examples, but there's always still a bit of a reluctance to use it. And is the quality good enough? That's the main question. So local validation always needs to be accompanied with that, with in situ data measurements, with flux towers, for example. And as well, the open source tool development. As a company, we benefit from them. And I think the community itself is happy with capacity building by reusing tools over time. And I think the last recommendation I want to put is like, can WAPOR be in the Copernicus data space ecosystem? We hear it's nice, it's in Google Earth Engine, but we hear that there is more people are happy in working with Jupyter notebooks in Python, and that works a lot better in the CDSE. That was my presentation. Any questions? And in the meantime, you can click on the QR codes if you want. And I also must say that part of our work has been financed by Dutch government, NSO, Netherlands Space Office, and Partners for Water. Thank you.
Is there any question? Seems not.
Oh, there's someone waving over there.
Ah, I couldn't see it. So please. It's too far for my eyes.
Some glasses.
Thank you very much for the presentation. Roshanak Darwish from University of Twente, the Netherlands. Since the title of your presentation was on vegetation water stress, I missed the link. Where did you get, or how did you get from the water consumption to water stress? And so this is first question, first part, and the second part is that why don't you just directly use like remote sensing data to get to the water stress?
Okay, yeah, maybe the title was a bit too general. It's water stress monitoring, it was. Actually, I already said from the beginning that I want to put actionability in it. And that maybe also relates to your second question, is that we have a tool developed for water authorities to use, because we see that there is little adoption of direct data sets that they could monitor themselves. As an example, we have been working in Morocco since 2019. That was a project where we delivered actually GeoTIFF files. And actually the water board and the irrigation office had limited capabilities to work with it, with these time series data. So what we actually did is make it easy to use. I hope that answered the question. No, not yet.
Okay, thank you very much. We can discuss after the presentation.
Of course. Yep.
Thanks again. Now we move to the last speaker of this block, which is Michael Thomas Marshall, with a talk entitled Drought Assessment in Drylands with Hyperspectral Vegetation Index-Based Evapotranspiration Methods.
Hi everyone, last presentation after lunch. I hope I can keep you excited. Today I'm going to present the results of an experiment which is the first of its kind. So hopefully that'll pique your interest. This project, our study is largely supported by a EO Africa Earth Explorers project titled High Relief. Also, ASI is supporting this project. Two of the representatives from CNR are here today, Monica Pepe and Mirko Boschetti. So I'd like to provide some motivation of why we're looking at water use, evapotranspiration in drylands of Africa. Drylands account for about 80% of the agriculture in Africa. They're extremely sensitive to climate shocks like droughts, and you can see that here in this FuseNet forecast. The situation in South Sudan is dire at the moment, as indicated pixels in red and orange, and also southern Ethiopia. Kenya, where our study area is located, is relatively less stressed, but you have to understand these are chronically food insecure areas. So one good year doesn't mean that everything's fine. Right? So historically, droughts were monitored with weather satellites that afforded high temporal resolution and precipitation-based indices. Precipitation-based indices in drylands are problematic because much of the water is evaporated before it's absorbed by the soil, or much of the water is diverted through the soil as base flow or overland flow. And so we've seen with the emergence of polar satellites, more demand-driven indices, and as this West review paper in 2019 points out, the lion's share of indices are based on NDVI. I circled this very small one here, ESI, the Evaporative Stress Index, which is an evapotranspiration-based index and represents a number of newer indices that have been developed. Evapotranspiration is probably the best way to monitor drought because it not only accounts for transpiration, as I illustrate here, through capillary action from the roots through the plant and out through holes or stomata, and then also water that's evaporated from the soil or the plant surface. So it really captures the water demand, as many of my colleagues have pointed out in the last couple of days. What we don't know is, a lot of work has been done on thermal. Obviously, everybody's talking about thermal. More recent studies have actually shown that SWIR and microwave regions are probably more reliable for ET estimation, particularly soil evaporation. And what we almost have nothing on is the contribution of hyperspectral narrowbands and related vegetation indices to improving ET models. There are only two papers of note. One was published in 2016, where we collected field spectra and ET measurements from surface renewal systems across many crop types in the Central Valley of California. And as you can see here, we saw sizable improvements in ET estimation using hyperspectral NDVIs for transpiration and water absorption features in the SWIR for soil evaporation, the most important of which actually was in the near infrared at 950 nanometers. The other study was by Wim Timmermans, who's also on this project. They used inverted radiative transfer model and hyperspectral narrowbands to estimate the vegetation fraction, which is the main component of the two-source energy balance, or TSEB model, Norman 1995, I think. Or 85, I think. So what are we trying to do? We're trying to use the NASA implementation of EcoStress, which uses the Priestley-Taylor PT-JPL approach to estimate ET and ESI, and then the European EcoStress Hub, which uses TSEB and SEBS, and to see how we might improve these two technical workflows using hyperspectral information. And then, of course, compare. Unfortunately, I don't have the comparison here. You'll have to go to IGARS in Athens this summer if you want to see the full comparison. Our study area is Kapiti Ranch, which is a typical dryland in Machakos County, southeast of Nairobi, Kenya. We have a number of instruments. Ooh, it's stuck. Oh, number of instruments there, and this is what makes the experiment particularly unique. We have 3 LICOR covariance systems measuring ET and other micrometeorological data. We have this over a historical period, 2019 to 2021, also the modern era from 2022 to present, for not only a savanna site, but also a cropland site, a cropland representing dryland crops, legumes, and tubers outside of the Kapiti Ranch. Now, what makes this particularly unique is the EC tower collects measurements, as many of you know, every 30 minutes, but we also have what's called a FLOX, F-L-O-X, very confusing, but so it is, that takes hyperspectral measurements from 400 to 950 nanometers every 2 minutes. So if you recall from the first day, a guy from Hydrosat said, models, ET models are usually evaluated at a monthly or coarser resolution time step. We actually can evaluate the ET models at daily or sub-daily time steps, and that's what we did. We also collected, thanks to Monica Pepe, a number of images, EcoStress, Prisma, and Sentinel-2, and NMAP, which we will use further for validation. Of all of this wonderful data we collected over the last year and a half, we have 12 image pairs of Prisma and EcoStress, and that's due to logistical challenges of acquiring precursor data, but also cloud cover. So this is the methodological approach. I focus on the top one here. We basically looked at several thousand combinations of 2-band hyperspectral vegetation indices in the Priestley-Taylor implementation, which you can see there's kind of 3 logical fits: the soil moisture, canopy, and green fraction component of the PT-JPL model. So these are the results. The time series is on the left, the scatter plot is on the right, using a multispectral broadband NDVI. So this is the baseline, right? You can see R-squared 0.7, but it tends to overpredict, as Tian Hu in his paper, Water Resources Research, pointed out, I'll talk about in the last slide. It overpredicts evapotranspiration during the primary growing season. That's bad news, because if you have a drought, it probably will miss it. Now, once we use hyperspectral narrowbands, you can see that the estimations improve significantly, or sizably, I should say. Significance is statistical, sizable is vague. And you can see here the pink line, this is simulated, matches well the black line, which is the observed. The green line is simulated transpiration, and the orangish line is simulated soil evaporation. So you can see the narrow bands in the canopy make quite a bit of sense. These represent the red edge and near-infrared, which correspond to leaf senescence and other biophysical processes. But then the soil component probably makes less sense, and that's because we didn't have narrow bands beyond 930 nanometers. I told you the tower goes to 950. It gets a bit noisy at 950. So we sacrificed the spectral range to get this higher temporal resolution, but still quite promising. So where do we go next? We're going to use the historical flux and flux data to evaluate the calibrated model. So that's our sort of temporal validation. And then probably the most exciting is the spatial evaluation, where we use the EcoStress implementation using thermal and multispectral broadband NDVI, and then we replace the multispectral with hyperspectral to see how they vary. And then we have this sort of third holdout tower representing a cropland site to see how well it does. Again, IGARS, Athens, if you're there, hopefully the results will be there. Fingers crossed. So recommendations to the EC and ESA. I'd say probably the most interesting, and I put Tien's paper here. I've never met you, I'm sorry, but I just happened to come across your paper a few days ago. They compared the European EcoStress Hub, which uses TSEB and SEBs. Obviously, they showed an overestimation in water-limited areas of the NASA implementation. That makes sense. But what we need to do now is see if hyperspectral narrowbands change the results of this, because to be honest, the PT-JPL model is much easier to implement. And then Sentinel-2 next generation will offer hyperspectral or optimal narrowbands. If these narrowbands are placed correctly, this could facilitate particularly improvements in soil evaporation estimation. And then finally, the 11-day revisit time that's proposed for the KIME mission obviously is insufficient for doing studies in the tropics. We had hundreds of images, and in the end we got 12. But there's not much we can do about that, but that's the proposal. So anyway, thank you.
So this is, so first let's see if there is any direct question for this presentation. You were right on time. And then, yeah, and then we can also get more questions in general on the recommendations for water resources intelligence. But while the mic is the microphone on its way? Yeah, thank you. So also think if you want to start thinking about what type of recommendations you would like to share in addition to questions to this specific presentation.
Thank you. A very basic question on droughts. How do you how can you, it's about drought assessment. So, but I saw the methodology, but I did not understand how you assess when something is a drought and what you're going to do with it.
That's a very good question that a lot of people that talk about drought monitoring don't know how to answer. All I can say is we are looking at the relative differences as predicted in ET from eco-stress versus our new implementation, and then seeing differences between our estimates of the evaporative stress index. So we're not really concerned with, yeah, what is a drought, what triggers the drought, but the tools that are used or supposed to be used for drought monitoring. We just want to see an evaporative stress index. If you don't know, it's the ratio of ET to potential ET long term. So that's all I can say.
Yeah. Well, I asked the question because we would be interested to see what would be the damages caused by drought and so on. So you have to define somewhere when is something a drought and
absolutely.
Not a drought.
So to my knowledge, these kind of indicators are mainly just used to sort of show if a drought has been triggered or to predict droughts. So the Palmer Drought Severity Index, I think, is probably the most famous PDSI. So it's more for information. I don't know much more like how you can use those other than to just determine when a drought is triggered and when it sort of ends. But it's a very good question, but beyond my expertise, let's say. Yeah.
Hello, hi, my name is Sheila Baber from University of Maryland and NASA Harvest, and this is more of a generic question about water intelligence and water consumption. If there is a standardized way to define irrigation and monitoring irrigation, when we were talking to the State Statistical Services of Ukraine about the Kakhovka Dam and the irrigation afterwards, their definition of irrigation ranged from a cup of water applied to a field, that is irrigation. And when we're classifying irrigation and trying to monitor irrigation, what threshold are we using to define what irrigation is?
Wow. Really out of left field. Let's see. I think there are probably other people here that are more qualified. There were some presentations. It's a great question, obviously. There were some people here that I think presented, actually, they translated ET to water consumption, and yeah, no, I can't answer that, sorry.
Thank you. I think that's that was more a general question, so thank you for, for your presentation. I can share, I mean, I share your concern, and indeed it's important that we agree on what we mean by irrigation. In FAO Aquastat, for example, there's different definitions. For example, in vapor, we apply a general definition of water managed cropland. I mean, because it can vary between a very few millimeters per season to a lot, and so we try to come with some definitions, but indeed it's a complex topic. My co-chair would like maybe to...
No, just to add a comment, it's another way, and another reason why it's important to look at this topic by looking not only at irrigation quantification, so it's not only an amount of water, but by crossing information and look also of where, I mean, when I say monitoring irrigation in its entirety, it's if we start collecting information on when it occurs, where it occurs, and how much, all this information altogether can give us more detailed information rather than setting a threshold and say this is irrigation or not, of it's water used or not, it's water applied or not, this kind of stuff. If we start merging more kind of information, when, where, and how much, and we see that things begin being somehow consistent, we can have a picture of the situation probably.
Yeah, and this maybe translates into a recommendation when it comes to we heard many times that irrigation mapping is one thing, but indeed it can be irrigation mapping at different time steps, so dynamic irrigation mapping every 10 days, monthly, or so it's not about only knowing where irrigation is, but when in time and what type. Yeah. Other recommendations or suggestions?
This one from Luca here. Is there a mic? Please, a mic. There is no mic. Yes. Magdalena with the mic. Thanks.
Yeah, I'm not presented before, but Luca Brocca, CNR Italy, and the easy recommendation from the session that we had today is that this morning many people machine learning Sentinel-1 plus Sentinel-2 for mapping. This afternoon mostly process-based modeling, so probably I guess that an easy recommendation is to make the two people talking each other to make something together. But we are here for that, no? I can give the mic to the people.
Is there anybody else that wants to add something? Yeah, seems not. So thanks again, everybody, for being here attending this session. And I think that we can now close the session. Thanks again.
Attiviamo la registrazione.
Sì. E poi tolgo il tappo perché Riccardo mi ha chiesto. Stop recording, no? Mica loro.
A questo punto vuole la sala e togliere il tappo, giusto?
Sì.
Ce n'ha uno sotto.
Sì, dovrebbe.
Okay. Hello, hello, hello. Don't be shy. Come back. We have 1 hour, and then you have an icebreaker again. Maybe even less. Thanks for coming. We all know that it's 5 o'clock, so I had the experience yesterday having another panel at 5, so I kind of know what I'm facing here, yeah. So, again, thanks for coming. Actually, when I was thinking how to introduce the session, I was like, okay, I'll start with a quiz. I pick someone from the audience, and I ask who can say which sensor is what. But then I realized the EcoStress says it up there, so it's kind of like, you know. Anyway, which is Nmap? Anyone knows which is Nmap from there? I'm not asking the panel here, okay? Who is brave enough to say which is Nmap? No one? Okay, let's turn it around. Which is Prisma? Okay, okay, fine. Never mind. We'll talk about that. Anyway, thanks a lot. So my name is Zoltán Szántói. I run as Zolti here. I'm a land application scientist at ESA. And mainly I deal with agriculture or the agriculture domain, any kind of earth observation, putting research into applications actually. Just very briefly about the agenda. I'm doing the first part. The second part will be, I introduce the panels very briefly, and then I give them you already have your microphone, so I just give them the time to introduce themselves in a little bit deeper manner, so they will say what they do, especially in relation to one of those sensors, and hopefully some relations to agriculture as well. And then we will see how fresh you are. If you are ready to give us questions after their introductions, then we can go ahead to audience questions. If not, I have some here, so we are all safe. So without further ado, we have a very nice panel here. We have my dear colleague from ESA, Anke Schickling. We have Monica Pepe from the Italian Research Council. Am I saying the right thing? We have Simon Hook as a research scientist from NASA JPL. And we have Heike Bach from Vista, which is a super good company from Germany. And I stop here and I give the floor to, who want to start? Anke?
Okay, I will start. Good afternoon, everyone. My name is Anke Schickling. As Zoltán just said, I started to work at the European Space Agency 6 months ago as a hyperspectral application scientist. And before that, I was responsible for the mission exploitation program of Nmap, which is, by the way, the golden sensor in the middle. This is also why I ended up at this panel. The mission exploitation program of Nmap was not only related to agriculture, but all main fields of application that hyperspectral is suitable for, so also the soil and geology applications, urban science, and so on. I have a bit of a background in agriculture, as before I was working for Nmap, I was working with the FLEX, the Fluorescence Explorer mission. I think you also had a talk yesterday about this. So this was my scientific field I worked in before. And I'm happy to be here at the panel and also tell you a bit more about Nmap and ask all your questions.
My name is Monica Pepe. I'm a senior researcher at National Research Council of Italy. And I work actually with a research group of remote sensing, of natural resources monitoring, and especially agriculture and sustainable agriculture and food security as main topics. And from March 2019, my life has changed because Prisma was launched. And I was firstly involved because to CNR has been assigned the external scientific validation of a mission. For that, I'm in charge of one of cropland sites, which is Yolanda. You have seen a lot of times during presentations. And And after that, my agenda turned to be filled up with Prisma. I have started in the 90s to work with aerial hyperspectral data and field data collection, but this has been a revolution also in my life. And so I've started working to several projects, some of them for the National Space Agency, and that has been presented the first day by Mirko Boschetti regarding crop traits and NPV, non-photosynthetic vegetation, which is my main topic. But also ESA projects. Two of them has been presented by Michael Marshall, one on the nutrient content of crops yesterday, and one about evapotranspiration in the EU-Africa Explorer framework today. And so I'm happy to be here. Thank you for invitation, and I give the floor to Simon.
Thank you. So good afternoon, everyone. My name is Simon Hook. I'm from the NASA Jet Propulsion Laboratory in California, and I'm also the principal investigator for EcoStress. So we came up with the idea for EcoStress back in 2013 or 14, I think it was. And so I have a question for the audience. Does anyone know what EcoStress stands for? It's a tough one. I'll tell you the answer. It's the Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. And what happened was, when we came up with the concept originally, we called it water. But my management thought that water was too grand, and I had to come up with a different name for it in 2 days. And so that's why we ended up with EcoStress. But the other thing that people said about EcoStress is you should never put the name stress in something because, you know, it'll be stressful, whatever it is that you do. And in fact, EcoStress was quite a challenge. And we did have a few bumps in the road, but we were able to build the instrument and launch it in 2018. And the idea behind EcoStress was always to look at agricultural applications or look at ecosystems. And at that time when we launched, EcoStress was the highest spatial resolution thermal infrared instrument in space, and it still is the highest spatial resolution instrument. But one of the things that's changed is that we always knew that the data could be used for agriculture, but we expected that other people would find other uses for the data. And that's one of the things that's really happened over time. So the data have been used, for example, to look at urban heating, among other things. The other thing I'll just mention is EcoStress is kind of a pathfinder for a whole series of new instruments that are coming along. Things like LSTM, which is being built by ESA, Trishna, which is being built by India and France, and then SPG, which is being built by the US and Italy. So there are several new instruments coming along that are all very similar to EcoStress, but they have some important differences. And what that means for all of you here is that you'll be able to get these kinds of data for the next decade. And so it's really sort of an exciting time, because I know one of the questions the applications people always ask us is, well, how long are we going to get these data for? Because they don't want to develop an application and then the satellite's only around for a couple of years, and so they can't really effectively use the application. So there's a great future as well for the thermal as well, and so I'll pass it on now. Thank you.
Thank you, Simon. Yes, thanks for the invitation. I'm Heike Bach. I'm director of Vista. I founded the company in '95, and since then I run it, and so that my daily business is really running a company. But what I really like to do is doing science and understand how we can get information from the new satellite data, that they can be extracted, that our users, our customers can really make value out of it. And that is, it's changing from year to year, and it's really an exciting journey that I followed during these years. My background to hyperspectral is that I did my PhD with average data taken in '91 For the young people, yes, it's true. Sometimes you have to wait for your instrument for a long time until it's launched in orbit. And since then, I'm enthusiast of hyperspectral data. And of course, I'm German, so NMAP is a little bit closer. I was following NMAP and supporting it when I could. But when Prisma was the first to launch, I was very happy with you that you succeeded with this, because most important is, I found this in the shop, everybody was in, so just launched. So hyperspectral data just launched. So it feels like it's not too long ago that it's launched now, and we are all in the learning phase how to make use of this data, and I think that is quite an interesting journey. My connection to agriculture is that nowadays the company is mainly working for agriculture, for agri-businesses, for farmers. We have smart farming services since more than 10 years on seeding, fertilization, irrigation, harvest management, carbon farming. So we are very close to the farmers and their needs. And at present, I'm also working within the SHIME Mission Advisory Group that we really have the operational instrument very soon.
Thank you very much. Before jumping to any questions, so we had a very nice intro here, but we didn't really hear much about the instruments themselves. So could you say a few words, which is your instrument up there, and what they can do, what they cannot do, and again, a little connection to agriculture just for the sake of the community here.
Yes, as I already mentioned, NMAP sensor is the sensor in the middle with the golden foil on it. NMAP just had its second birthday, so on the 1st of April, it was launched 2 years ago. And we had a commissioning phase of half a year, so we are operational for one and a half years now, and we are actually quite happy how the sensor performs. So it has over 240 spectral bands from 400 to 2,500 nanometers, covering the Wisny and the sphere. There's a very good signal-to-noise ratio. NMAP data are freely available for everyone. You have to register, then you can browse through the archive or also try to have special targeted requests. Always keep in mind, also from the application side, it's a targeting mission. So the data rate we get is not comparable to a Sentinel. So we can have like 1,000 kilometers as a maximum stripe. This is all why we are waiting for chime eagerly. But nevertheless, I think also especially for agriculture, but also for other applications, I think it's a very powerful tool to have a look at those data, to learn how to use hyperspectral data. As Heike said, just launched, so we need to learn how to use this data, also how to use the tools with it. Also for NMAP there, we have it's called HyperEDU, so it's an educational program for everyone, freely available, who wants to learn how to deal with hyperspectral data. We also produced the NMAP toolbox, which already has some tools available for level 3 or level 4 data for people who want to start to work with it, all freely available, and just pointing that out to the community to start to work with hyperspectral data and with the sensors.
Thank you. I expect the same good news from Monica.
Mine sensor, Prisma is the one here, and it is quite similar as the configuration to NMAP, but is a little bit older. It is a precursor, so it's the first one, let's say, in a new era. It has 270 bands, but when you get rid of overlapping, it's around 230. And it covers the visible to shortwave infrared from 400 to 2,500 nanometers. Again, the swath is 30 kilometers, so it's not so large. And the revisit time is 29 days, but there is a possibility of another acquisition, which would improve and increment the revisiting time. And there is also, like in MMAP, the double possibility of a spot acquisition of strip acquisition, strip map, up to 240 kilometers. And again, it's an experimental mission, of course, but as Anke said, it's really important. It's something that has been said also in the other panels, that one thing is to have idea of what we need, of what the user needs, but in advance we have to demonstrate things, to play with actual data and to understand potentials and limitations, because we have great expectations, but not always the higher the better. Because for sure, having higher spectral resolution is also really tricky by a calibration point of view and processing point of view, and also amount of data. And so I think this one of the pillars of Prisma was agriculture. And the goal is reached because in the 2,500 users, around 20% are connected to agriculture. And so the community is quite interested in agriculture. And in fact, in 5 years of operation, we had something like 90 research works indexed dealing with Prisma and agriculture, and this work proved that there is a lot of people working and facing also the type of sensor data.
Thank you, Monica. Now we know what EcoStress stands for, but we don't know much more details. So maybe Simon can enlighten us.
Yes, okay. So it's the highest spatial resolution thermal infrared sensor in space at the moment. It has 5 spectral bands between about 8 and 12 microns, and a swath width of about 400 kilometers. So much, much wider swath width than the hyperspectral sensors that have been talked about, which are more like sort of 30 to 50. Now, because it has that much wider swath width, it means we get a much higher revisit. So we can typically see somewhere every 3 to 5 days. And we are always on global mapping. So that means every 3 to 5 days you should get an image over your area. And then for all the data that we acquire, we produce a set of standard products. So these standard products include things specifically for agriculture. So there's an evaporative stress index that you can download and use. There's evapotranspiration that you can download and use the products. And for these products, we actually produce them using different flavors of the algorithm. So in some of the talks today, maybe you heard of the Priestley-Taylor approach to calculating evapotranspiration. And so we have a PT-JPL version of from EcoStress. Similarly, you may have heard of Alexi and Disalexi, which is a disaggregation approach. And we have evapotranspiration versions using that algorithm as well. So we produce a lot of standard products, so they're very easy to use by the community. The products are typically available, 3 to 5 days after we've actually acquired the data set. All the data are freely available. You can get them from the land processors DAC in the States. But similarly, there's also a European hub where some of the data have been gathered specifically for Europe and collected to make them a little bit more accessible from there. So we were launched in 2018. It was supposed to be a 1-year mission, and after 1 year, NASA decided that things were going well and extended us to 3 years. And then after 3 years, NASA decided we were still doing okay. So we were actually being extended until 2029 now. So what was a 1-year mission has become a 10-year mission or more. So obviously that's very exciting, and it hopefully means that people are using the data and getting some value out of the data.
Thank you, Simon. So the 3 colleagues here, they are really directly connected to the sensors, but I invited Heike for the reason because I know that her company actually works with all of the 3 data flows. So the question would be to Heike, how do you see the use of these 3 data sources separately or together, as you wish? And again, what are the applications for agriculture?
Very well. I just want to comment on Prisma. I just read the message that now the data is also free for commercial applications.
I was one, yeah, from
Exactly.
2nd of May.
Yeah. So it's just, I mean, we use it now at present for scientific projects, but still it's very good to know that this is now allowed.
Yeah, it is allowed to sell, let's say, to business, for derived products.
Exactly. That's just for your information also.
Yeah,
I found this quite interesting.
Thank you.
Okay, so we are really allowed to use the data. It's excellent. No, I mean, hyperspectral and the thermal data is very essential for agricultural applications. Up to now, we only had multispectral data. And the benefit that we can use for our services, I told you about the smart farming services, is just give you examples for this. Number one is we hope that the product that we up to now use, like leaf area index, will be provided in better quality. That's number one. That we saw before, these hyperspectral indices can be more accurate, more sensitive to information. So there's one quality gain. But more important to me is that we can see features that we could not see before. And that is, for example, with the thermal data, it helps us, of course, for irrigation. We had just had the irrigation session before for irrigation planning, so we will use it for the irrigation advice. We use it for drought monitoring. We complement it with hyperspectral data where we see this water absorption that is for the crops at the 970 nanometer, that we can combine these two and really have better information of the moisture status of the crops. And hopefully soon also with Flex, that we also can understand the fluorescence when I see Jose there. And then there is the big field of fertilization. For fertilization, you have to understand how much nitrogen is already in the crops. And now with the hyperspectral data, we can really see the chlorophyll absorptions, and the nitrogen content is now available in radio transfer models to be derived. And we can use it now, then that's a plan for fertilization advice. Or if you look into harvest management, we have to find the right time in the year to give the best time for harvesting, which mainly depends on moisture conditions. It should not be too wet, because that is concerning illnesses. It can be a problem, the fungicides, and it's also a cost factor. If you have to dry it, you need a lot of gas for this. So to find the right time for the harvest is quite important. And so these are just examples where we can use the satellite data very efficient and improve the services by new information sources. Oh, I forget one important field. I just forget it. Carbon farming. That is also, I just was in a conference in the US. Carbon farming was one of the 2 main points. The other was generative AI. But what it's about, with the hyperspectral data, you can really see the soil organic content much better, in a better quality, and you see crop residues, which are quite important for this. And this is, again, new information, that you can see much more detailed than you could before with multispectral data.
Thank you. Now, as promised, any questions? I have my preset, so I don't get scared if you don't, but I would really like to see if the audience has any questions to the colleagues here. Don't be shy. No questions? Okay. I thought to start perhaps with Anke here. How do you see, it's a little bit close to what Heike was saying, but how you see the Nmap usage in agriculture? Do you have any statistics, how much it was used, being scientific output, being used in a business model, although I am not sure if that's possible there?
Okay, so as I said, NMAP is now in a launch 2 years, so we have a bit less registered users than Prisma, I think around 2,000, and agriculture is one of the main applicational fields, also one of the main pillars. NMAP, let's say, the commercial use is not restricted. However, commercial providers are not allowed to task yet. That is to come, just because the acquisition rate is so limited that it was designed as a scientific mission. We wanted to give the scientific users first priority. And we see that also the output from the scientific community is quite high. So they are really happy with the data quality. As Heike said, chlorophyll content, LAI products, everything that is also included in the NMAP box yet. We just had, I think the publication is out on the first SOC maps that can be produced in a very good quality from the NMAP mission. So I think this is really interesting sensor and really interesting tools for the agricultural community, always keeping in mind that the global coverage is still to be recorded, honestly, for NMAP. So Prisma has global coverage, NMAP not yet. So this is really something from the field of application where I know that this is quite a limiting factor, because with that, for the application side, you need reliably every 14 days the same amount of data recorded. And this is still something that is a drawback from the current hyperspectral missions, but this is hopefully to be solved with the CHIME mission coming up.
So that's my next question, and it's going to Monica, actually. So she just mentioned CHIME, Simon mentioned SBG. How do you see, especially the hyperspectral spectral sensors, in connection for this, I guess we should call fully operational upcoming satellites such as CHIME, such as SBG?
No doubt that we need operational satellites, it has been said, and people is expecting not only for that, but also for analysis-ready data for products, for traceability of them, so there are a lot of things. And for sure, everybody is asking for a better temporal resolution. In fact, one of the limitations of both sensors is that, and something which was, I think, quite unexpected is that this on-demand and off-nadir mechanism was a drawback, really, because, for instance, for Prisma, just 1/3 of requests for the programming orders are successful because of conflicts. And so this is something that was unexpected also because it was not expected as so important and huge programming tasking of such data. So on one side is good, on the other is difficult. So for sure, going to operation is really important, and CHIME for sure will benefit also, the mission will benefit of all the years of experiments and demonstrations with Prisma and MAP, and so I think that also the LSTM will benefit from the experiment with EcoStress, and so I think also anyway we will try our best, I think, as a scientific community in the meanwhile to try to find synergies between sensors also for demonstrate this, and because for the hyperspectral part it is something is really complex signal on one side, but the good thing is when you have almost continuous spectra, it's easier to find out if the two sensors aligns quite well. And in my experience, EMAP and PRISMA have a good potential for alignment with some, of course, the spatial problem, of course, to be solved, but after that, because PRISMA has no good accuracy, spatial accuracy, should be refined, geocoding. But after that, I think we could learn a lot from the current mission, and for sure, all the science and algorithm efforts we are doing now will be a benefit for the next coming mission, and also for the lesson learned from mistakes, let's say, for failures and for every kind of problem. And so for sure, it's, but the kind of exploitation that has been done till now, I think, has shown the very big potential, as Heike said, in several. Some things have been increased in accuracy, like crop traits, because there is the possibility of fully exploit radiative transfer models. Moreover, we have also machine learning and so on. But some applications like crop residues and soil are also unlocked by the availability of shortwave infrared high-resolution data. So, and there are new challenges like the ones of nutrients, and so I think we have the chance to have a good chance to study in the perspective of have operational data.
Thank you. And before I jump to Simon, just a comment from my side. Yeah, the first 1-2 days here, I was like relatively surprised not to see actually many works, and correct me if I missed one or two or many, using these data sets. But as you could see, okay, today I think there was 1 or 2. But what you hear that, yeah, these satellites are being built. Things are still, not necessarily the sensors and stuff, but things can still be at least listened to. So I think we really encourage to use this data very strongly, and we'll do listen. So I belong to ESA. Benjamin is here, the mission scientist for LSTM, or TERMA mission. Simon is here for SBG. I think I can say on behalf of you guys that we do listen, and we want to hear your experience. If it's agriculture, excellent. If it's something else, also excellent. So anything, so we really want you to please use the data. It's for your and everyone's benefit. But then jumping to Simon, you said so many nice things about eco-stress. Anything negative, especially since, as you guys can see, it's not a satellite per se. It's flying on the International Space Station. So anything in that regard?
One of the interesting things is that eco-stress is in what's called a precessing orbit, which means that instead of flying over at the same time every day as most of the satellites that you're used to, which are in a polar orbit, it goes over at different times of day. And because it goes over at different times of day, it means we can measure the surface temperature at different times of day, and then we can see how evapotranspiration is changing throughout the day. Now that's an advantage, and it's a disadvantage. It's an advantage in the sense that we can do just that. We can look at ET over the day, but on the other hand, a lot of models are designed such that they get a measurement at a certain time of day, and they expect the crops to be behaving a certain way at a certain time of day. Now, what's interesting is that when SBG, LSTM, and Trishna come along, there you've actually got 3 satellite systems, and each of those systems has 60-meter spatial resolution. Each of them has a very, very wide swath. And they are all going over at exactly the same time at 12:30. So they're very well suited to these models. They're going over at 12:30 because when we looked at the eco-stress data, we determined that's when it was the maximum stress. So we wanted to look at the stress, so these future systems are all going over at 12:30. Now, interestingly enough, they weren't all going over at 12:30 to start with. One was going over at 12:30, one was going over at 1 was going over at 1:30. What happened was we got together, the different missions got together, and we agreed that we'll all go over at 12:30. Now, by going over at 12:30 makes it much more easy for end users to be able to work the different data sets together as opposed to individually. The other thing is they all have a 3-day revisit. That means full global coverage every 3 days. Now, it could be that we planned things such that everything went over all on the same 3 days. So we didn't get any coverage in between on the second, on the second day. But of course, we are working together. And so by working together, the plan is to get daily, by staggering the 3 missions, is to get daily 60-meter data. So looking forward, we're going to have daily 60-meter data everywhere in the world. And in fact, we'll get it twice daily because we'll get it in the morning and we'll get it in the evening as well. So a daytime and a nighttime scene. So very, very exciting. Now, why is that important that we get such high coverage? Well, obviously, if we're trying to monitor how something's changing, we really want to get as many images as we can. And we know that roughly, 1 out of every 3 images is clear. So you have to take 3 images before you get a good one. So this means that, we'll be getting images several times a week. So it means that we can derive a good weekly evapotranspiration that people like farmers can use. And it also helps with certain applications that really need high-frequency coverage. Now, what's one of those applications? I happen to quite like it. It's winemaking, okay? And as hopefully some of you know, the wine industry is big business, and the flavor of the wine is determined by stressing the grape during the period that's called Horizon, which is a French name, and I'm probably pronounced it incorrectly, but there we go. And during this period, the farmers monitor the amount of water that they put on the grape very, very carefully. And so one of the things that became apparent after we launched EcoStress was by combining Landsat and EcoStress together, we were able to get much more coverage through this Horizon period. And companies like Gallo and things like that found the data extremely valuable from that viewpoint. Now, obviously, when LSTM, Trishna, and SPG come along, then it's going to be even better. We're going to have that daily coverage. It's going to allow us to look at applications that we just couldn't hope to look at before. So, that's sort of one of the advantages of being in a polar orbit where you're going over every day, as opposed to a precessing orbit like on the International Space Station. But personally, I would still like to keep up EcoStress up there, and who knows, maybe there'll be an EcoStress 2, because I think you get a lot of information about the diurnal cycle by looking in the precessing orbit, as well as looking at the polar, in a polar orbit and going over at the same time of day.
I love the wine example, definitely, especially before the icebreaker. I think we have just a little time left, but I think we are scratching really the new sensors here, the ones we are expecting to go up in a few years' time. Heike, any recommendation based on the research, but also from the business side you guys are doing at Vista? And then, yeah, as I said, Simon and Benjamin is right here. Anything you would upfront recommend that you guys must do this or must not do this?
Well, maybe one lessons learned, maybe at the beginning, when we worked with the hyperspectral data, we were aware that now everything is much more, not data volume, also computationally it's much more demanding. And that, so we need new solutions. For example, an inversion with a lookup table, with the many bands, you often have problems with memory, for example, with the Nmap toolbox, for example. So we need new solutions, and when we then try to use AI and neural networks to solve this, so our first results with it was that we succeeded in maybe 90% of the cases. We were successful and it looked okay, what we retrieved, but in 10% not. We don't know why, because we cannot explain AI. But I cannot give to 10% of the farmers a non-perfect result. So we decided we could stay with the lookup table to be on the safe side. But this just shows we really have to better understand the physical modeling and the AI model, as Luca also said, work together. Everybody has strengths in it, but if we combine it, I think then we would come a step further and do the data analysis more effective. I think that is quite helpful. And what Simon said with the more frequent observations, you're right. Of course, if you have more sensors, you have more observations. That's true for thermal and hyperspectral, but both have problems with clouds, and that will not change. So that is, I think we need not a solution, but we have to work with the clouds. And for this, we will still need data fusion. I think that we have more temporal, higher resolution data and combine them with thermal and hyperspectral data. And here also we need some methodological developments to make it a better way. We tried it with, for example, with the solutions that we have now for Sentinel-2 and 3, but they don't fit really completely. So there must be new developments to really put the hyperspectral information together. Multispectral, that was one lesson that we learned. And I think also a good potential is that you really assimilate the data into the physical models again. That makes it somehow easier to do this temporal interpolation using the process model. But on the other hand, we have to learn how data assimilation in this process model work the correct way. Again, give you an example. If we now can see the nitrogen uptake in a very good quality, the question is how can we tell our nitrogen model that now it should react differently to really mimic the nitrogen that is seen. It's not an easy task to do this, so we have to change now our data assimilation scheme or increase it. So there are a lot of challenges that we have to fulfill.
Mentioning the clouds, of course, I think all of us nightmares, most of us nightmares are the clouds for the research work. Otherwise, we of course many times welcome the rain. But I think Simon had some comments when we were discussing about clouds. How do you see any solution for clouds from your side?
Well, I think that there's sort of two solutions, if you like. One solution is more frequent data. The fact that we are getting data every day really, with these three sensors, really increases our chances of getting cloud-free data and getting enough scenes to create something like a weekly evapotranspiration. The other thing, of course, is passive microwave. Passive microwave sees through clouds, but generally speaking, it has very coarse spatial resolution, but you can get a surface temperature from passive microwave. So it would be at a few kilometer scale. And then really, it's a matter of combining the higher spatial resolution data with the lower spatial resolution passive microwave data that would be available globally and trying to downscale it to get something where you could see what was going on even when it was cloudy. So I think there are some possibilities there, but that would be, that's really sort of cutting edge research, you know, next generation satellites.
Talking about cutting edge research, let's see who does cutting edge research. Any questions regarding hyperspectral? Finally someone, thank you. Everyone is, I don't know if tired or scared. Which is it? Yeah, I have to bring the microphone, I'm sorry.
Thank you very much, panel, for the nice discussion. Actually, I do not have a question about the data. I think all this data from Prisma, from Nmap, from EcoStress, they're fantastic. And but I would like to make a comment about, we are just talking about how useful these data are and how they can be incorporated into AI and radiative transfer model, which is also where my hearts go. But don't forget the importance of the field validation data, which is a tough thing to do. I mean, all these parameters, if they are going to be fed into these models correctly, they need to be correctly measured in the field. And that's really, really a difficult work. For someone who has worked for more than 20 years in the field work and collecting these type of parameters, I can tell you that the accuracy actually of your field data will only value this type of remote sensing data. So it's all on the field data. So my recommendation would be for these satellite data to perhaps to formalize a kind of validation teams. What Sentinel-2 did a few years ago, the Sentinel-2 had a validation team, and perhaps, organize a kind of validation team for Nmap and Prisma, which can actually collect some field data and perhaps better, also show the usefulness of this data. Because to me, if your field data there's an issue with your field data, no matter how good is your hyperspectral data, you will not be able to get a good estimation of what's going on the ground. Thank you.
Yeah. Thanks a lot.
Thank you,
Excellent.
Roshanak.
Jump, Monica, please.
Okay. Thank you, Roshanak. But we have the Nmap is more than 100 validation sites. Prisma is not so large, but we have validation sites in for different applications in different landscapes. And so also the changes in processors, in both agencies, is based also on this validation work. And so, as I told at the beginning, I am in charge of one of the validation sites, which is Yolanda, that you know. And so there is ongoing work, because this is really important, because it's important to keep on validating hyperspectral data all the lifetime of a sensor, of course. And there are also initiatives in order to find a way to measure the uncertainties and of products and of different levels, to have a common agreement on what to measure, how, and about the metrics to be used for validations. So it's something that is going on, but will have also some improvements in the future.
Simon, from the thermal side, anything?
There is a global network of stations that measure evapotranspiration or various fluxes, and we obviously tap into that network. We also have custom validation sites for the level 1 products, the radiance sensor or brightness temperature sensor, and then the higher level products. But I completely agree, you can never have enough validation sites. I think the other thing that we have to think about with the validation sites is more does not necessarily mean better. It just means more. If you get more of bad data, you just get more bad data. So, a great deal of effort needs to go into making sure that the instrumentation at the validation sites is well calibrated, and resources need to be spent in order to make sure that those validation data that we produce are truly truth, if you like, as opposed to something that also has some artifacts in it. So we end up correcting one thing to something else that has some problems with it.
Thank you.
Let me just add something.
Please.
I just want to be provocative. I think we should work that in 10 years we don't need any field measurements anymore. That should be our target. And I think we are on the way forward to it. I mean, it cannot be that we go out in the field and measure at 8,000 fields for yield to later on predict 2,000 other fields. That cannot be our way. We must find other solutions, and that should be our target. Still, of course, we will do some detailed studies and so on, but the system itself, the satellite systems, should explain what happens on ground. As if we would look at the Mars or the Moon, where we understand what happens there, it should be the same on the Earth.
Not a bad point. I don't know if anyone have a comment on that. There is someone. I'm coming.
Yes, maybe a follow-up on the topic on validation and what was just mentioned, because what I so far have been missing here, we cannot validate any pixel in space and time, that's clear. But what I've been missing here is the quantification of uncertainty. I believe by quantifying uncertainty, that's the way to know whether your model is working or not, whether it's a lookup table based, whether it's a hybrid based. Uncertainty is crucial, the propagation of it from one product to another product. That's the way forward, how to know whether your model is working in space and time. And I think we should work especially in that direction if you want to achieve the objectives that Heike, that you just mentioned.
Yes, there is this. Yeah. Okay. on next June, there will be a meeting about that, about the uncertainties and how to propagate them and the different levels of sensors, and to have agreements about also, as I said, a common way to do it, in a way also that if you combine different sensors, you have the same kind of information, the same kind of traceability, otherwise you cannot look for synergic use of them. Do you want to add something?
Anke, you wanted to add something? Any other question? So actually I have one to Anke. We had only 2 comments or questions, and I think we really should push the community. I want to see people working with, I'm coming, want to see people working with hyperspectral and thermal data, how we should push these people to do that.
The only thing I can say, the data are freely available, so just, register. As well for Prisma data, as well as for Nmap data, and have a look at the archive. Many people already say like, okay, but the tasking is too complicated, and I tried, but I didn't get any data. Well, yes, this is true for some areas, especially for Europe. For Nmap, of course, for Germany, we have a high demand on data. Huh? We switched now to a foreground mission to not to eliminate the fact that many of the proposals block each other, actually. So this is a lesson learned. But have a look at the archive. All the data recorded, which have a proper quality flagging, will be available in the archive. And it happened for many of the users that when they browsed the archive, they thought, oh, there are already data available I could use for my studies. I didn't need to request new recordings. And then download the data available, level 1, level 2 data, have a look at the Nmap box, for example, and look at the MOOCs. They guide you very nicely through how to open the data until how to arrive at your LAI map, and just start with that. In case, of course, you're interested, you can also use this for teaching purposes, for example, and this is really just something to get started. This is all I can say to this community. It's kind of fun.
And then we have at least one more question.
No, your worst nightmare, probably, because I am an agronomist. And, okay, so you laugh. Okay. I'm Manos, I'm from Greece. We had an experience working with Prisma and EcoStress in Neo Explorers tender from the European Space Agency. And I think that we found some findings of ours needed to be, pushed a little bit from our side, like, for example, do follow some machine learning approaches to, upscale the spatial resolution of Prisma, and also to do whatever we could, of course, by using MODIs and to enhance the spatial resolution and the temporal resolution of EcoStress. And why? We addressed both food safety and food security. So concerning food security, there was, at least from what we have seen, there was no way to use Prisma for rust disease detection, which is very important for Africa, because there were no images, or there were a lot of it were covered by clouds, so we had a lot of cloud cover. But consider that the spatial resolution, and I'm speaking now as an agronomist, consider like the spatial resolution is 30 by 30 meters, okay? The final spatial resolution of Prisma. We have the red edge, 175 channels, I guess. But when we see a fungus on a 30 by 30 meters resolution on a field, that means that the field is already, we have a disaster, okay? So this needs to be taken into account. Apart from that, we have a very big revisit time. And this is also another problem in eco-stress. You are talking about evapotranspiration. Because we use evapotranspiration, we use the evapotranspiration also in the Euro Explorers, a free forecast project. We used it to run the most simple, let's say, crop growth model, okay? It requires two measurements daily of temperature, okay? The temperature mean and the temperature max. We could not derive this from eco-stress. In any case, we used a fusion of, we made the fusion framework to enhance the spatial-temporal behavior of eco-stress in order to find two daily temperatures to put in the model. So I am thinking that, are we sure about the final products? Also, you talked about Flex. When I heard that Flex will be available at some point, I said, wow, we are going for a high throughput. But this was not the case. 1,000 meters resolution of stress depicted by the Flex, this is not high spatial, this is not high throughput. And I'm not sure the reason for bringing such a satellite, such a product. So these are my only comments, just to see whether the final spatio-temporal resolution of all these products is actually fit for agronomists, for agriculture, and to push science forward in the case of agriculture. Thank you.
Yeah, I think it's a fair question, but you actually answered it in the thermal case, because you said that what you did was fused MODIS data with the eco-stress data, and that got you the daily coverage, which MODIS has. But going forward with LSTM, Trishna, and SPG, you will get that daily coverage that you want. Now, in addition, the 60-meter spatial resolution means that you'll be able to look at the ET not just over several fields or over an area. You'll be able to look at the ET variation within the field, which is also something that is very desirable. And then the last point I'll make on it is that even though I say these satellites have daily coverage, they actually have more frequent than daily coverage depending on the latitude. They have daily coverage at the equator, but as you go further north, the amount of coverage will increase because you'll get overlap, to extreme overlap if you get all the way to the poles. So I think that you've pointed out the problem in the case of evapotranspiration, but you've also sort of pointed out the solution through fusion and the solution through these new missions that are coming along, which will give you the data that you want.
Any other comment?
I just want to comment that I don't sell hyperspectral and thermal high-resolution data to my customers, because they would not understand that it is a science mission and that the data is not always available, it's not optimum. So it's really, at present, it's for science and development of algorithms, and later on, if we have the other missions that are following, then I think we can think about really operational services, and until then we can prepare for it.
Yeah, and just to add to that point, you can download, it's a European app, you can download IRIWatch on your phone now, and basically what they do is suck in all the thermal data from EcoStress and other thermal missions and put it all together and come up with a schema for farmers to irrigate their individual fields. So there are, the work has been done to move away from having the individual have to process the data to being able to get some, if you like, commercial product. You may not want that commercial product, you may want something else, but you know, it is there to do it as well.
And that's the last word. Thank you very much. Thanks for finally a lively discussion here. Thank you very much for participating, and please give an applause to our panel members. Thanks again. And ice-breaking, second time or whatever.
Yeah.
Whatever.
Time for. We can.
Thanks a lot. Huh?
You're welcome.